Hello everyone, Dr. Data Science here, and I'm excited to welcome you to our comprehensive Python programming course designed specifically for data science and machine learning enthusiasts. Whether you are a beginner stepping into the world of coding or someone looking to refresh your skills, you've come to the right place. Today, I'm excited to guide you through 15 interactive Jupyter notebooks hosted on the GitHub repository. These notebooks cover everything from the very basics, such as crafting your first if statements and navigating for loops, to more advanced topics like object-oriented programming and so on. We'll also dive deep into essential libraries such as NumPy, Pandas, and Matplotlib, which are the backbone of data manipulation and visualization in Python. But that's not all. In the final segments of our course, we'll explore the fascinating topics of machine learning and deep learning. You'll get hands-on experience using powerful tools like scikit-learn, TensorFlow, and Keras. These sections are crafted to give you a solid foundation in both theory and practice, preparing you to tackle real-world data science challenges. Our goal is to make machine learning as interactive and effective as possible. Each notebook is designed to be self-contained and emphasizes experiential learning, allowing you to apply what you have learned immediately. If you find value in this course, please don't forget to hit the like button and subscribe to Dr. Data Science channel. For easy access to all the course materials, make sure to check out the link to the GitHub page in the video description below. Hello everyone, in this video we talk about the basics of Python programming, such as setting up working environments, assignment logical and comparison operators, as well as different types of errors that you may encounter while running Python codes. Each lecture note in this course is a Jupyter notebook. When you use a Jupyter notebook, you are essentially interacting with your code through a web browser. And your Jupyter notebook is organized into cells. Each cell can contain code or text. For example, if I click here, you can see this blue bar here, which shows that this is one cell, and the type of this cell is markdown. And markdown is a style of writing documents, which in simple terms means that this is a text cell. And basically, this is a cell that provides some information in the form of text, figures, and the idea is that we don't want to run or interpret this cell as a Python code. Now, if we click on the next cell, you can see that this cell is bigger than the other one. And if I double click on this cell, you can see that now I can see the markdown language that we are using. For example, here we have these 3 hashtags to have a header. This line creates a horizontal line that you saw when I run this cell. And then we have this asterisk here for itemizing what I am writing here. And also we have some figure that we have inserted here from the web. And you can see that therefore Markdown is very powerful in terms of providing rich text documents. And now you can run this cell or use Shift Enter, and you can see that now we have this very nice form of this text cell here. And by clicking on here, you can see that again, this is a markdown cell or text cell. But if I move to the next cell that we have here, you can see that now this is a code cell, which means that here we have some form of code here that we want to run this cell. So that's how you can recognize the difference between markdown and code cells. Okay, so let's move back to the second cell that we have here, where we talk about setting up working environments in Python. And the way that we do this in this course is using Anaconda. So what is Anaconda? Anaconda is a comprehensive distribution platform and package manager, which is designed to simplify the process of managing Python environments and libraries that we use, especially in the context of data science, machine learning, scientific computing. And the very first step to use Anaconda is to download and install the Anaconda distribution by visiting anaconda.com/download. And you can see here in this figure or in this image, that we have, by installing Anaconda, we have access to Jupyter Notebook and a lot of powerful tools and libraries such as NumPy, SciPy, Matplotlib, etc. So let's talk a little bit more in detail about what Anaconda is. So Anaconda, what it does, it incorporates a powerful package manager called Conda. And Conda, what it does, it simplifies the process of installing, updating, managing various software packages and making sure that their dependencies are handled efficiently and correctly. What this means is that, for example, when you're using Pandas that you can see here, you may need some other libraries or packages, such as NumPy. And obviously, we can install these libraries one by one and manually, but the idea is that there are some dependencies between them, and we may ignore these dependencies, which will definitely cause some serious problems. So in this case, the idea is that we want to have these package managers where they can understand these dependencies and be able to handle them automatically rather than we worry about all these dependencies. Therefore, Anaconda and Conda, they work together and they provide a very nice and user-friendly platform with some pre-configured Python environments and libraries, especially in the context of data science and machine learning and artificial intelligence in general. Therefore, my recommendation is to download and install the Anaconda distribution, and you learn how to run these notebooks locally. Okay, so let's move on to the next cell here. So you can see that we start this cell by these hashtags here, right? All these 4 lines, they have these hashtags. And what this means is that these lines of codes that we have here, they're actually comments, and they're just for readability and providing some information, right? So when you write some code, you probably, don't remember what you have done, before, in the past month or so. So you want to put some comments so that both you and if other people are really like looking at your code, understand what you're supposed to do in those sort of like lines of code that you have here. And for that, use these hashtags. So now you can write anything you want, provide some information, and this will not be interpreted as Python code. So here I'm explaining and saying that, well, for a cell, we can start with exclamation mark. And what it does, it indicates that that line should be executed as a shell or terminal comment rather than a Python comment or a statement. So why is this useful? So let's say, after installing Anaconda, you want to make sure that you have Conda and Python installed on your computer. And one way to do this is to always check the version of the, Python or Conda that you have installed. And if you can get the version information, this means that everything should work perfectly fine. And in order to do this, you can use the -- version flag. So in this case, you type conda -- version, and you can just write this if you're using terminal in Mac or command prompt in Windows. But because we're in a Jupyter notebook, you have to use this exclamation mark. And if I run this, you can see that we get the version number here. And this is great because this means that we have conda installed and is working fine. And the same thing with Python, right? So maybe we are curious to know what version of Python we are using, right? So we run this and we can see that we are using Python version 3. And obviously we have these 2 numbers here, but what we really care right now is that
we want to make sure that we are using Python version 3. Okay, so in the next cell, which is a markdown cell or a text cell, you can see that we talk about different ways of running Python code. So the first one is Jupyter Notebook, what we are using right now. And in this case, we talk about the fact that, when you're running a Jupyter Notebook, you're essentially interacting with your, code through a browser. And you can have different cells where you have live code, rich text elements such as equations, images, figures, links, etc. And then for running each cell, you can use the run that you can see here or use Shift Enter. So I usually like Shift Enter because it's just much easier and faster. So this means that in this case, if I want to run this line of code, which simply says print this text here, data science, if I run this, you can see that, we get the result, which is printing data science. But we can do a lot more. So for example, we can do arithmetic operations, right? We can use Python as a calculator, plus for addition, this dash for subtraction, asterisk for multiplication, and a slash for division. Something which is not trivial is exponentiation in Python, where we have to use double asterisk, right? So if you use double asterisk, this means that this is exponentiation, right? So in this case, we have print 2 raised to the power of 3. And obviously, if you run this, we get 8. And we can write this as just multiplying 2 3 times, right? So 2 times 2 times 2 is the same as 2 raised to the power of 3, and we get 8. The same thing with division. We can have print 2 divided by 3, which we get 0.66. And the nice thing about Python, as we said, is using packages and modules. For example, the math module provides a wide list of mathematical functions, allowing you to perform complex operations without having to implement them from scratch. And in order, for example, to use the math module, you start by importing math. And then inside math, we have this function called sqrt, which stands for a square root. You have to use this dot here. This is called the not dot notation. This means that from math, we want to use a square root function. And in this case, we are finding the square root of 25, assigning the result to the variable result, and then we print result. And in this case, we get 5 as we expect. But the nice thing is that the math module has a very wide range of mathematical functions. And sometimes you want to really know what functions are included. And the way that you can do this is by just typing the name of the module and dot, and then use tab. So you can see that now we have all these trigonometric functions, finding the ceiling, finding cosine, exponential function, factorial, etc. Right? So you can see that this is a very long list of functions for different mathematical operations, logarithmic functions, etc. that we have here. So let me erase this line that we have. So in this case, we have a very simple example where we want to find the sine of pi over 2. And we know already the result is 1, but if we don't know, we can just run this cell and you can see that we get 1. Okay, so now we have seen one way of running Python code, and this is our preferred way in this course. But there are other ways too. The other option, which is option 2, and I would say this is more advanced or professional, is using Python script with the extension .py. If you recall, for Jupyter Notebook, the extension is .ipynb for IPython Notebook, but for Python scripts, we use .py. And in this case, you need to either use a text editor or an integrated development environment or IDE, such as Visual Studio Code or VS Code. I definitely recommend you to, install this if you want to, do more exercise about, working with Python and different IDEs. And once you work with Visual Studio Code, you can create a new file with the .py extension. Let's say we call this myscript.py or any other name. And then you open terminal or command prompt if you're in Windows, and you navigate the directory or folder that your script is located using the cd command. Cd stands for change directory. And then you can run the script using the command Python and then the name of this script that we have, which is myscript.py. And then the other option which is option number 3, is to directly open a terminal or command prompt and type Python. And in this case, you have an interactive Python shell. So let's see how these two techniques work using Visual Studio Code. Okay, so in this case, now we are in Visual Studio Code. And what we do here is that we want to create the script myscript.py. In order to do this, we can go to File and then New File. And in this case, we just type the name that we want, myscript.py. And now we have to save this. So I save this script where I have my lecture notes. And here we have this file where we can type any Python code we want. And I want to keep it very simple here. So I'm just saying print. And you can see this is one of the nice things about using an IDE such as Visual Studio Code, because it helps you to actually figure out what functions you use. In this case, it's very simple, it's print. But if you forget, that, well, there are all these functions that they start with, PRI, or they include this. So in this case, I say I want to print, and it tells you the syntax or the way that you can use print. But in this case, I want to do something very simple. I want to, let's say, find 2 raised to the power of 3, right? This is what we talk about exponentiation. So I'm gonna save this file, right? So right now it's not like Jupyter Notebook. I cannot directly run this here using Shift-Enter. But what I can do is that I can come to terminal that we have here and just write Python and my script.py. Right. And if I enter now, you can see that we get the number 8 as we expected. So this means that now we were able to run that Python script. And this is very helpful if you have a very long script file where you have many lines of code. In this case, it's just much easier to put everything in one script and then just use this Python and the name of the script. So this explains the approach 2 or option 2 for running Python code. And for approach 3, we just have to type Python in terminal. And you can see that here we have Python version 3.10.9. And now we can use Python. So I can say, I want to know what is 2 raised to the power of 3. And we get 8 as expected. But I really do not recommend using this if you want to write more than one line of code, because it's not a very nice way of interacting with your code. And Jupyter Notebook or just a Python script, as we saw, is a much better option. And here also we can close Python by typing quit. And as you see here, now we are outside this Python interactive environment that we have. Okay, so now let's close our terminal and talk about the 4th way of running Python codes, and that is using cloud-based platforms like Google Colab. So in this case, you can go to colab.research.google.com and either create a Jupyter Notebook or upload your Jupyter notebook and be able to write Python code. And the nice thing is that in this case, you don't have to do any configurations because all these packages and libraries are already available. In many cases, what already is installed there is sufficient. And if you look at here, at the beginning of each lecture, we have this button here that says Open in Collab. So if you click on this, you should be able to directly open the lecture in Google Collab if you want to use a cloud-based option. But as I mentioned earlier, I do recommend understanding the process of using Anaconda and being able to managing different packages, especially if you want to really develop your strong skills in data science, machine learning, etc. And what this means is that, we can continue this lecture using Visual Studio Code as what we do here, because you can see that now we are working with actually the Jupyter notebook that we have, or we can switch to the web-based browser that we have. So in this case, let's just continue using Visual Studio Code since we are already here. Okay, so now let's talk about assignment operators. So what does this mean? So in general, let's say you want to store some information. You want to store the value 5. This will be stored somewhere in the memory of your computer, and the address of that location in the memory is usually complex. So one way is to remember the exact address, but that is, kind of hard. And the idea is that we can just assign this value 5 to some variable, let's say here x. And from now on, if I know what is in that location, in that memory, I can just call x or print x. And this is important because when you say equal sign here, equal sign is assignment operator, right? So x equals 5. We are not trying to solve an equation, as in some other math courses. We are trying to say that assign the value of 5 to the variable x, right? And in this case, also have to select a kernel for running this. And you can see that we run this cell here. And now if I print x, you can see that I get 5, right? Because x refers to the location where we store that value 5. But something to keep in mind is that we can change the value that we have at that location. So let's say in this example, I assign 10 to variable y, and then I'm using this line of code where I'm saying y plus equals 3. So what this means is that I want to add 3 to the y, that variable that we have, and then assign the result to y, right? So in many cases, we just want to change the value of this variable that we have, and we want to add 3 to whatever value that we have already stored. So in this case, either we can use this, y equals y plus 3, or we can use the more compact notation or Python notation of y plus equals 3. So in this case, if I run this cell, I expect to get 13 because we have 10 and we add 3. And you see that that's the case here. We get 13. Okay, so now that we talk about assignment operators, the next one we have to talk about is comparison operators. Comparison operators in Python are used to compare values and return Boolean results. So Boolean results are either true or false. And I want to emphasize that the first letter should be uppercase, right? So we're going to see later, this is right now text, it doesn't matter. But once we get to talking about more these comparison operators and Boolean results, you'll see that this uppercase letter is very important. So what are these comparison operators? For checking equality or equal to, we use two equality signs. Not equal to, we use exclamation mark and equal sign. And then similarly, greater than, less than, greater than or equal to, less than or equal to, right? So these are the main comparison operators that we need to know. So what this means is that, let's say, we have assign value of 5 to x, assign value of 5 to y. And now we want to see whether x is equal to y or not, right? True or false, right? In this case, it should be true, right? Because x is equal to y. And if I run this, you can see that we get true. How about the next cell that we have here? So we have a equals 8, b equals 8. It looks like a is actually equal to b. But what we are asking is that, is a not equal to b, right? And this statement is obviously false because a is equal to b, right? So that's why you can see that here we get using the comparison operator. How about the next cell, right? So we have two variables, m and n. M is 10 and n is 7. Is 10 greater than 7? The answer should be yes. Or in programming terms, it is true, right? So that's the Boolean result that we get, true or false. And in this case, it is true. But obviously, if I experiment with these, right, and say like m less than n and run this, we get false, right? Let's put that back the way that it was originally, and we get true. Okay, so we talk about assignment operators, comparison operators, and the next one is logical operators. Logical operators in Python are used to perform logical operations and manipulate Boolean values. And the main logical operators that we need to know of are AND or NOT. So the AND operator returns true if both conditions on its left and right are true, right? So the both conditions on its left and right should be true to be able to get true. On the other hand, with the OR operator, we need at least one of the conditions on its left or right to be true, right? So this means that if one of them is true, then we get true. And the NOT operator basically returns the opposite Boolean value, meaning that if we get true and use not, then it's false. And if it's not false, then it's true, right? Because we only have two options. So let's look at this example that we have here. So in this case, we have a equals 8, b equals 3, right? The first part is that is a greater than 5? And that is true, right? Because 8 is greater than 5. And then on the right side, we have b less than 2. And obviously 3 is not less than 2, so that's false. But here, since we have at least one true, we get true for the result of this OR that we have here, right? Because remember, for OR to return true, we need at least one of the conditions to be true. But if I use the exact same example and use AND this time, we can see that now we get true and false. And in this case, we get false because both these conditions should be true for this AND operator to return true. And let's finally look at the example for NOT. So in this case, we assign true to the variable C, right? So this is a Boolean value. And we say not C, which means that not true. And the opposite of true is false, right? So that's how we get that. And then for next cell, we want to talk about something which is very important, right? We talk about arithmetic operations and we talk about logical operations. And remember that arithmetic operations will be executed before logical operations. So this means that in this case, we are not asking whether 1 is greater than 4 or not. We are saying that whether 5 plus 1, which is 6, is greater than 4 plus 1, which is 5. And if I run this, we get true. But in general, to avoid any confusion, make sure to use parentheses, right? So in this case, it is very clear that we want to first add 5 and 1, which is 6, and then 4 and 1, which is 1, and you avoid any confusion or misunderstanding. Okay, so now that we talk about different types of operators that we really need in Python programming, let's talk about different types of error, right? As a programmer, you should be very cautious of different types of error messages that you get. And we can classify them into three groups: syntax errors, runtime errors, and logical errors. So what are the syntax errors? Syntax errors is like grammar errors that we may make when we are writing. In this case means that we didn't follow the complete rules that we have, and violated some of the rules that we have. And that's the exact same thing with programming languages, right? So syntax errors means that the code that you have violates the language's grammatical rules. And these errors prevent the interpreter or compiler from understanding what the code is supposed to do. On the other hand, with runtime errors means that grammatically your code is correct, but you run into some problems during the execution of the program that you have, right? So these types of errors are usually not detected by the compiler or interpreter, but rather it will cause some problems during the program's execution. And the third type, which is the most, I would say, difficult one to recognize, is logical errors. In this case, this means that your code is syntactically correct or grammatically correct and run without any errors. You actually get some results, but they are inaccurate or incorrect results due to some flawed logic that you had once you had your implementation. So let's look at a few examples to understand the differences between these, right? So in this case, we have a cell where we have print 2 plus 3, and for some reason, we don't have the other parentheses to close the first one, right? So you have a missing closing parentheses, right? So this is something, even here you can see that in this case where we use Visual Studio Code, it is telling you that something is wrong with these parentheses, right? Because it's not closed, right? Even it's very smart and can recognize this easily. So if I run this cell, you can see that we get syntax error, incomplete input, and even tells you where the missing parentheses is supposed to be. Okay, so now let's look at runtime error, right? So in this case, we have 10 divided by 0, right? So in terms of the syntax or the set of rules that we have for Python, this seems okay, right? You have two numbers, you're dividing them, everything's fine. But you can see that we have a problem, right? We are doing division by 0, and you get this 0 division error, right? So this is a type of runtime error, right? Because this happens a problem during the execution. How about this one? We want to add hello, which is a text or a string here, and then add it to 1, 2, 3, right? So again, you're using addition, you're using the right operator, it looks like it. But once I run it, you can see that you get type error, right? It tells that you can only concatenate a string to a string and not integer, right? So it doesn't like the fact that you have a string here and then you have an integer and you want to add them together, right? So that's a problem that happened when running this code that you have. And now let's look about logical error. So in this case, you can see that, let's say you want to find or calculate the area of a triangle. You have the base and height. And for whatever reason, you believe that or you think that the area is just base plus height, right? So I can run this cell and I get the result, which is 9, the addition of base and height. But that is not the definition of the area of a triangle, right? So this is a logical error. And as I said, this is the most difficult one to recognize because you usually get some results, but the result is inaccurate, and that is a problem. So we will talk about these types of error messages and how to fix them more thoroughly throughout the semester. But something that you can always use when you get errors is what is called as type checking. And in Python, type checking refers to the process of verifying and enforcing the expected types of variables and objects in your code. So think about it in this way, that any variable or object that you have when you're using Python has a type. And in order to find the type of that object or variable, you can use the type function, like similar to print, where you can use for printing. You can use type to find the type an object or a variable, right? So in this case, if I run this, you can see that we get this message and obviously telling us something about types of these variables or objects that we have, right? So let's use type, right? So that's the function that we talk about in Python, and you can use it anywhere, and find the type of hello, which tells us is str or a string, and then type of 123, which is integer, right? So now we can understand that how this relates to the error message that you have. And as I said, the cool thing about type is that you can use it anywhere. Like, right, we talk about like math module and some of the functions there. So if you use type math.sign, right, as you can see, this is a built-in function or method. So it's very powerful in understanding the type of anything that you have in Python. Or you can say type true, right? So this is Boolean, BOOL, right? So that's something that has been recognized here. And here you can see why it is so important, that uppercase T that we have there. If we don't do that, then that's not anymore a keyword or a recognized variable, and you just get this error that says name true is not defined, right? So remember that this uppercase T, or if you're using false, uppercase F, is something that you have to use, and you can see here the difference in color. One is blue and the other one is just a normal variable or object in Python. Okay, and then the other thing that we have type of like, variable or object in Python, which you should know is something called none. So what is none? None is a special constant representing the absence of a value or a null value, right? So when you say here result equals none, so we assign none to result, and we can look at type of it, and it actually has a special type. It's called none type, right? So remember that none in general means that the absence of a value or a null value. And then in the next lecture, we're going to talk more about data structures, the way that we can store and organize values in Python. For example, here we are using the type function, and inside that we have these square brackets 1, 2, 3. So it seems that we want to store 3 values. And if you look at the type here, this is a list. So we're going to talk about what a list is in Python and other data structures. And finally, you can see that at the end of this lecture, we have this part which is labeled as homework 1. So this is your first assignment. And in this case, you have 10 problems that you should work on them. And the idea is that these things are not necessarily something that's been exactly explained before, but what you have already seen should be enough to be able to get started working on these problems. And this is very important for improving problem-solving skills using Python. For example, in the first case, you want to compute this ratio or fraction 3 times 2 over 2 raised to the power of 3 plus 4 divided by 2. And what you do here, you can create some cells here. So you can insert a cell below this one and write your code, and then you submit your Jupyter notebook on Canvas. So my expectation is to at least have 10 cells where you have the solution to each problem, and your grade will be calculated based on the level that you have completed each problem. Hello everyone. In this video, we talk about basic data structures in Python. To get us started, let us quickly review the definition of a variable in Python. A variable is a symbolic name that represents or refers to a value. So let's say you want to store a number like 2 or 5 somewhere in the computer's memory. When you store this information, you have a specific address for that location in the memory. So one way to access the information about the value that you have stored is to remember the address for that location, but this is usually very complicated and it's not an easy task. Instead, what we do, we assign a label for a piece of data that we have stored in the memory, and that label is what we call it a variable. So therefore, variable is like a container that holds information. With this in mind, now we can define a data structure. So a data structure is a way of organizing and storing data so it can be used efficiently. This is particularly very useful if you have multiple pieces of information that you want to store, meaning that you're not just want to store one value like 2 or 5, you want to actually store, let's say, 100 different numbers, and you want to make sure that you can access them in a very efficient manner. And Python provides several built-in data structures that you can use them, such as lists, tuples, sets, and dictionaries. These are the very common data structures in Python that we need to know for machine learning and data science applications. And these structures allow you to organize and manipulate data in different ways. And although they are similar in some ways, but there are some subtle differences between them. For example, we are going to see in this video that lists in Python are ordered collection of items. So what order means that we have an index that shows the location or position of each item that you store. But on the other hand, a dictionary is an unordered collection of key value pairs, meaning that you lose that notion of location or position. And this is sometimes very helpful, as we're going to see. So therefore, we need to know different data structures to be able to handle different scenarios depending on the specific requirements for each problem. So let's just start with the basics, right? So let's just start with the variable. So we talk about this, that the equal sign is assignment operator. So this means that the value to the right of the equal sign is going to be assigned to the variable on the left side. So in this case, we are going to store this value to and give it a label or like a container, which is called x, right? So now when we type x here, we can see that we see the value that we have here. We can also do some operations on the right side of the equal sign. So here we are saying that we want to add 3 and 2, and then assign the result of this arithmetic operation to y. So in this case, you get y is equal to 5. Sometimes it is useful to know the list of all the variables that you have in a notebook. You want to, for example, see if you have used a variable name before or not. So in this case, you can use this % sign and then WHOS. And this, if I run this cell, remember for running cells, I can use Shift-Enter, or I can use the run option here. And in this case, we get the variable names, X and Y, their types, these are integers, and the value that we have for each one. So X is equal to 2, Y is equal to 5. So now let's talk about naming variables in Python, right? So as you expect, there should be some rules about, what a variable name can be. And it is recommended to follow these general rules that we have here. So variable names must begin with a letter, uppercase or lowercase, or an underscore. So this is something interesting. Actually, a variable name can start with an underscore, as we're going to see. And it is also a common thing to use underscore if you want to use multiple words in a variable name. And this is what we call it as a snake case, meaning that you have one word, underscore, and then another word, right? So this doesn't really mean anything. It's just more like remembering the general way of defining a variable name. But there are some restrictions, right? So when you define a variable name, please do not use Python keywords or built-in functions. For example, we talk about the type function that we can use to find the type of any object in Python. You can say type equals 2, which means that you want to assign the value of 2 to type. But the problem is that now you lose all the functionality of type from now on, and you cannot use type for type checking that we discussed in the previous lecture. And the same thing for other keywords like if, else, for. We're going to see these in future lectures. So please do not use these keywords or built-in functions to define a variable name. And as I mentioned earlier with the snake case that you can see here, it is common that variable names are written in lowercase letters, right? So you obviously have the right to choose uppercase letters if you want, but it does really help to be consistent and follow several general rules about that are especially the ones that are adopted in the Python community. And in this case, it is better to use lowercase letters for Python variables. And something else that we need to keep in mind is that a variable name in Python cannot start with a number. So you cannot start a variable name with a number, and that's something very important to consider. So let's look at some variables, right? So let's say we want to store the value 25. We assign this to age variable. We can have a string or character strings, like we use this double quotation to show that. And let's say we call this user underscore name. So now we know what this variable is actually username. You may want to, for example, store total score. That's what, again, we use this snake case convention. But you can also have multiple words, as you can see here, right? So you want to say something is a valid input or not. So you define this variable and assign some Boolean values, true or false. And you can see that I can run this cell with no problems. I can retrieve this information for any of these variables. In the next cell, you can see that we have this snake case, and then we have also a number at the end. This is totally fine. You cannot start a variable name with a number, but you can end it with a number, and there's no problem at all. And you can see it here, right? So in the next cell, that's the case that it's problematic because we are starting with a number, and this is not allowed. And you can see that we immediately get this error, which is called syntax error. So if you recall from the previous lecture, syntax error means that you're not following the grammar rules that you have in the programming language, right? And this error here means that you cannot start the variable name by number. But as mentioned earlier, you're more than welcome to use an underscore. This is actually something very helpful at some points. You can see that in this case, we can have a variable name that starts with an underscore. Okay, so before moving on to talking about data structures in Python, let's also talk about the fundamental data types. And there are 5 of these, right? So the first one is integers, or int, and this represents whole numbers without any decimal points. We have floating point numbers, which is called float, and this represent numbers with decimal points. The strings or character strings, which represent sequence of characters, such as text. Like, for example, we had before username equals Christina. So Christina is a string. We have Booleans that we saw in the previous lecture. BOOL represents either true or false values, right? This is very helpful with comparison and logical operators. And non-type, and that's, none represents the absence of a value or a null value. And as mentioned before, one thing that you can always do to check the type of a variable is using the type function, right? So this is something you can always use. Here, 5 is obviously an integer because we don't have any decimal points. A is 3.14, and this is a floating point numbers, right? So that's why we get float. And then we get the strings, right? That you can be either in single or double quotes, right? I personally usually use double quotes, but either way is correct. And when we check the type, you can see we get str. We can also create a new cell here. So you can go to insert and insert cell below, and now check the type of, for example, true. So this is a Boolean, and you can see that we get BOOL, or we can create another cell here and type none, and this is when we get that none type, right? So which means that the absence of a value or a null value. The other thing that we can discuss here is that the len function, len in Python, is used to get the length or the number of items in an object. And if you're using len with the strings, in this case, it returns the number of characters in this string. So in this case, I defined my underscore string, which is hello world. So this is the string that we have here. And if we count the number of elements here, so we have 13 elements here, right? Starting from H, going to the exclamation mark that we have at the very end. So this is very helpful, right? Because in Django, you may have a string, you don't know how many characters you have. And in this case, you can use len, and you immediately get the number of characters that you have here. Something to keep in mind here is that when you have this string, now you have this notion of ordered collection of items, right? Meaning that this H is the first element, E is the second element, then L is the third element, which means that now we can actually index them and use that indexing system to access them, right? So for example, you want to just, let's say, look at the second element, right? What index we have to use to select that element. So that's what we want to discuss in the next cell. So the way that indexing works in Python is that the first index is actually index 0, right? So this means that this P here, we are now changing the string that we have. We are calling it Python. And in this case, the first character that we have here is P. And the way that we can access this is using these square brackets, and then we put the index here, which is 0, meaning that the first element. Now, if you want to look at the second element or retrieve the second element, that element is index 1, right? Because indexing starts from 0. And now we can print these two characters that we have accessed. And the way that we can do this is using something called the print F double quotation syntax, which is called an F string, which stands for formatted string literal. So what does this mean? It means that we want to print something, and what we want to print really depends on the variables that we have before this print statement. And in this case, this means that we have to wait to see what those variables are to know exactly what it should be inside that print statement. In this case, you can use this F and the double quotation, and then you have these curly braces or curly brackets, and inside that, you put the variable that you want to print, right? So this means that when you use this print statement, Python is going to look at what this first character is, and first character is defined here, and it's going to print whatever that first character is, right? So you can see that if I run this cell, now we have the fixed part, which says the first character is, okay, that's always fixed. But what we have here really depends on this variable that we are accessing or defining here. And that's P, because it's the first letter, index 0. And then the second one is the one at index 1, which is the second element or second character, and you get Y. So this F string or formatted string literal is very, very important and convenient way to embed variables within a string in a concise and readable manner, right? So in this case, everybody knows that you want to print this first character, and first character is defined in a few lines above that, where it is the element or character at index 0. So in this case, we only picked one element, right? But what we can do, we can actually pick multiple elements. And in this case, this is called a slicing, right? So a slicing is a technique used to extract a portion of a sequence, right? So it can be one, but it can be more than one. And you can use it for strings like we do here and later with lists, tuples, etc. So we're going to talk about lists and tuples soon, but we know right now about the strings. And the syntax or the way that you can define this slicing operation is using these square brackets, a start index, colon, end index, colon, and then the step that you want to use. So start is the index of the first element you want to pick. End is the index of the element just after the last element you want to pick. So what this means is that when you're using a slicing, you have the left side and the right side, and the left side is inclusive, which means that it's included, but the right side is exclusive, which means that you want to go up to, but not including the end index. So in this case, if you want to pick something, the last one that you pick is at index, let's say 4, then you have to set this end to be 5 because it's exclusive. This means that automatically you will stop at 4, including 4, but you will not include 5. And also you have this step argument here, which is the number of indices between each slice, right? So when you start from the start index, do you want to go one by one, or you want to skip one element and pick the one after that, right? So that will be then step equals 2. But usually the default value is 1, meaning that you want to pick all elements. So to see how this works, let's look at my string, right? So you can see that here we have Python. That's the string that we are working with. And again, this single or double quotation really doesn't matter. This string is Python. So what is my string 1 to 4? Remember, this is the start, this is the end. And in this case, we have not defined the third one, which is a step. You can just leave it empty. And in this way, you know that the default value is 1. So what this means is that you want to pick elements from index 1, and remember indexing starts from 0, and up to index 4, not including the one at index 4. Okay, so now if you look at here, we have Python, and I'm showing the indices for each one. So it starts from 0, 1, 2, 3, 4, and 5. So in this case, we are saying that we want to start from index 1, which is this one. So this means that the first element or character that we are selecting is Y. And then we go to 2 and 3, but not 4, because that's exclusive. So what this should give you is YTH. So let's run this to see whether we get this. And in this case, we can see that we get YTH, right? So that's exactly how this works. The start index is inclusive and the end index is exclusive. However, if we want, we can really use that step parameter or argument too. In this case, it wouldn't make any difference because we are selecting all these elements from first to end index. But if you want, for example, in this case, to increase the step from 1 to 2, you can see that we will pick Y, and then we jump over T and we select H. And that's what exactly we get here, right? So this is the idea behind the slicing, where you have a start, a stop, and a step index. And our default values for each of these arguments in the slicing operation. For a start is always the beginning of the sequence, if you don't specify it, meaning that index 0. For end is always the end of the sequence, if we don't specify it. And for step, the default value is always 1, meaning that you want to pick every element from a start to end index. So you can see that here we have another example that we are saying that we want to pick everything up to index 4, but excluding index 4, right? So that's the thing with always with the end index. And you can see that we include this time this P, so it would be PYTH. And then similarly, we can start from the second character and go to the end of this list, right? So in this case, you can see that we get Python without P, right? Because P is at index 0. And here we want to say that we want to start from index 1. Something which is very interesting about Python is that you can actually use negative indices. And negative indices indicate that you want to count from the end of the string or end of the sequence. For instance, -1 represents the last character in a string. -2 denotes the second to last character, and so forth, right? So here we have the string Python. What this says is that you want to select the element at index 2. So P is 0, Y is 1, T is index 2, and go up to -2, right? So this time you're going to count from the end of this sequence. So N is -1, O is -2, and that's excluding because it's a stop index or N index. So in this case, if we run this, you can see that we get only T and H, and we do not get O, right? Because O is -2 index, and we go one before then, right? So which is like the H here. And this negative indexing system is very powerful. Like one thing that you can use, which is really cool, is this notation. And just to put this in context, what it is here is that, remember, you always put your start index here and the end index here, and then the step here. And in this case, we put the step -1, and we do not specify a start or end indices. So what this really does is going to go pass through the sequence in reverse order, right? Because this means that you have included everything from the beginning to end of this sequence, but instead of having a positive steps where you go from left to right, now you go from right to left, right? And if you can see that, you see that you get this, first N, then O, then H, then T, Y, and P. So now you have this sequence in reverse. So this is a very cool trick that you can use with negative indexing. The other thing which is very important in Python, and here we are showing all these examples with the strings because it's very easy and straightforward to use these strings, is that because it's an object and we are following the principles of object-oriented programming, you can use very special functions or methods for manipulating these types of objects. For example, for strings, you can use this method which is called upper. And the way that you use this is that you have here your string name, whatever it is, and then this dot notation, and then the method name or function name. And don't forget the parentheses because this is a function. And for functions in Python, you have to use parentheses. And what this does is that, as you can see in this comment, it turns your strings to uppercase letters, right? So now we have all uppercase letters. So let's say you want to do some data analysis with some emails, and you want to make sure that all letters are uppercase, you can use that upper. You can see that this doesn't necessarily change your original string. It just creates a new version of it. So it's not stored yet. Our string still is Python. Since you have dot upper, this means that we have dot lower. Now everything is in lowercase letters, right? So if it's not case sensitive, you want to make sure that you can use, for example, dot lower, so that if somebody use uppercase letters, now they're converted all to lowercase letters. There are also many other cool methods that you can use with the strings. For example, you can check to see if a string starts with a specified prefix, like dot starts with. And in this case, we're saying that is this a string that we have? It starts with uppercase P, and the result is this Boolean true. Yes, that is the case. And you can also, for example, find the index of the first occurrence of a substring. Is there TH in the string that we have? The answer is yes. And if you want to know when that happens, is 0, 1, 2, right? So it starts at index 2, where we have this TH or this substring. And this is what you can see here. And this is just to show that we never really changed my string. So that's saved in somewhere in the computer's memory. You have this label for it. And all these methods, they just create a new version of that string, and they are not stored. unless if you assign them to another variable and you want that way you can store it. But otherwise, we never really changed the original string that we have. Okay, so now that we know about variables, fundamental data types, and also this indexing system in Python, which is something that we can also use for other data structures, let's just start with the most important data structure, or the most common one, which is list. So what are lists in Python? Lists are ordered collection of items, which means that you have an indexing system that you can use to find the position of items. They are mutable. What this means is that you can modify their elements by assigning new values. You can add or remove items. So you have all the options to modify the list as you wish. And there are heterogeneous elements, meaning that you can list can contain elements of different data types. You can have a list of numbers and strings, or even list of lists. And also the way that you define lists is using a square brackets, right? We have seen this before, that for creating lists, we need to use the square brackets. And you can use common operations such as concatenation, which is the plus here. So this is not an arithmetic operation here because you're not working with just with like numbers. You're working actually with list here. So if you use one list plus another list, really there's nothing to add there in the arithmetic sense. This means that you want to concatenate the two lists. You can use repetition using asterisk, or you can use the len function to find the number of elements in your list. And also there are specialized methods or functions that you can use for manipulating lists, like adding, removing, sorting, etc. And we cover some of these here, but whenever you need these methods, you can always search online and find what an appropriate method is for the task you want to do. It's very likely in many cases that you can immediately find some built-in methods or functions. And also lists in Python, they have dynamic sizes, meaning that they can grow or shrink, and also you can add or remove items and elements as needed. So let's look at a few of examples of what we just talked about, right? So here we create this list one, has 3 elements, 1, 2, 3, right? So this is now a container for multiple variables, not just one. We can look at the type, and you can see that we get list as expected. We create a second list. We call it list underscore 2. This list has strings, right? Apple and orange. We have this double quotation. Now we can use this plus sign here. And then remember, this plus sign is not an arithmetic operation here because you have list. And what really happens here is that when you add these two lists, you concatenate them. Now you have a list which contains the 2 other lists that we have that are elements, right? So now we have 5 elements here. And you can always find the number of elements using the len or len function, right? So 5 elements. So what is the difference between using this plus sign for concatenation or defining another list which contains the 2 lists that we just talked about, right? So if I run this, you can see that this is a different type of concatenation because we really do not have one list that contains all the 5 elements. We actually have a list, right? So these are these outer square brackets that contains 2 elements. And the first element is another list, which contains 1, 2, and 3. And then the second element is another list that contains the 2 strings that we have. So now, based on what we said, if I just use what is the length of list 4, is actually 2, right? Because I have a list. Look at the outer square brackets that we have that has 2 elements. That's element 1, that's element 2. So this len function is not going to look at the inner list that we have. It just looks at the outer list that we have and figure out the number of elements that we have. And as mentioned earlier, the slicing notation works here too, right? So I want to, for example, pick up elements up to index 2, right? So remember, it starts with index 0, index 1, index 2, but index 2 is excluded. So this means that you're going to just have another list which contains the first 2 elements, 1 and 2. And similarly, we said that we can use like negative indexing. So in this case, if you say -1, means that pick up the element that is at the end of this list, which is orange, right? So this is very helpful if you don't know the length of this list and you just want to pick the last one. You do not have to count all the way from beginning to the end of this list. You just say that pick whatever it is in the last one. Or we can, for example, say here that I want to look at this list 3 and pick the element which is at index -2, right? This means that from the end of this list, not the last one, but second to last one, right? And that's Apple, right? So you can see all the principles we talk about for slicing strings, they apply here too for lists. And now let's talk about some of the methods or functions that you can use for lists. And in this case, we're looking at list 3, which was the concatenation of the list 1 and 2 that we had. And you can use this .append, which is very useful. This means that you want to add something to this list that you already have. So in this case, if I run this cell, you can see that I have my original list. And now I appended or added this element, which is 4. Right. So in this case, now you have a list that contains 6 elements, right? We had originally 5 elements. We added the 6th one, and that's the length of this list 3. And something that is very helpful when you're doing machine learning and data science sometimes is to create an empty list, right? And then add new elements to this list later on using the append method, right? So this is the power of Python list, that it's dynamic. So it means that it can grow or shrink in size. And the way that you can create an empty list is just by using the square brackets here, but nothing inside it. This means that this is a list, but it's an empty list. And now you can, for example, append 1. You want to store the value 1. And now you want to store the string 2. And if I look at my list at the end, has 2 elements as expected, right? So you can do something multiple times, and every time you get some result, you can use .append. Similarly, maybe you want to add something to a list, but at a very specific location rather than just adding it to the end of the list. In this case, you can use the insert method, right? So in this case, the syntax or the way that you can tell this to Python is using this method or function insert index, which shows you at what index and what is that element that you want to put in that index, right? So that's something important to remember, right? The first one is index, the second argument is element. It's not the other way around. And obviously, when you do that, then you need to make sure that to understand that the existing elements at that index and after that index they need to be shifted to accommodate the new element, right? Because you cannot have 2 elements in one index, right? This means that everything at that index and to the right side needs to be shifted by 1, right? So in this case, we had the my list, which was 1 and 2. We are saying that at index 1, which is this index here, we want to put the string 3. This means that now I have 3 in index 1, which is the second location, and this 2, which was at index 1, now is at index 2, right? So remember, indexing starts from 0, 0, 1, 2. There are also a lot of other things that we can do with this. For example, you can check whether an element is in the list using the operator in. That's why I really like Python. It's very readable. It's almost like the way that we talk and explain things in plain English. So you can say, is the string 3 in my list, right? So the answer to this is true because yes, it is here 3 here. And then is the string 4 in this list? I cannot find 4 here. So the result should be no or false. And you can see that that's what we get here, right? So these are very useful operations that you're going to see a lot in machine learning and data science applications. Okay, so now that we talk about lists, now let's talk about tuples. So what are tuples? Tuples are also ordered collection of elements. So this means that you can use the same principles of indexing each element. But here is the first main difference. Tuples are immutable. This means that once they are created, their elements cannot be modified or changed, right? So if you say that I want to change the element at index 2, and before it was 2, now I want to make it 5, you get a very nice error message that you cannot do this, right? And this is a good thing in some cases. You may want to make sure that nobody changes what you have stored in a tuple. And that's when you have to use tuple, compared to, for example, like a Python list. And similar to list, tuples can have heterogeneous elements. You can have elements of different types, strings, floats, integers, etc. And the way you can define them is using these parentheses, right? So for lists, you use square brackets. For tuples, you just use parentheses. And there are also methods or functions that you can use, such as concatenation. If you want to concatenate two tuples, you can use the len function. You can repeat a tuple. Something which is very important is when you have a tuple that has only one element. Obviously, you're allowed to do that. But something to keep in mind is that in this case, you must use a trailing comma. So what this means is that in this case, I have a tuple that I want to store the value of 42, but I do have to use this comma here. If I do not use this will not have the tuple data structure. And we're going to talk about this in the very next cell. And obviously the other nice thing about tuples, you can use packing and unpacking. And what this means is that you can pack multiple values in a single tuple, and you can unpack multiple values that you have in a tuple when you need to. So this is what is known as packing and unpacking. So it's very much like what we really, say in plain English when you want to pack multiple things together and you want to unpack them, right? Think of that as packing and unpacking your luggage. Okay, so let's just start with the examples for tuples. The very first thing is that if you want to define a tuple with one element, if we don't use that trailing comma, and you look at the type, this is an integer. This means that these parentheses that we have here, they do nothing for us to define a tuple here. So how you can make it a tuple? By using this trailing comma here, right? And if I look at the type here, you can see that now this is a tuple, which is great. Now let's create another tuple, which is 246. We use parentheses. You can check the type of this, and you can see that this is a tuple. Let's say for whatever reason, I want to change this third element, which is at index 2, to be 8 instead of 6. And if I run this, you get this very nice error message that says tuple object does not support item assignment. So that's what we meant by tuples being immutable. And then you can also look at the length of a tuple. So in this case, we have 3 elements, and that's what we expect to get 246. So let's talk about the packing and unpacking we said. So packing refers to the process of combining multiple values in a single tuple. And in this case, you can see that I have 1, 2, 3, and I just assign this to this variable called pack tuple. And in this case, recall that we don't have only one value that we want to assign to this. Actually, we have 1, 2 integers and a string. And therefore, if we do this operation here, you can immediately see that now we have this parentheses, which is a sign that this is a tuple. And you can always check the type of this object, and you can see that yes, it is a tuple, right? So this is what is known as packing. You assign multiple values to a single variable, and by default, this will be a tuple. So what is unpacking? Unpacking is the opposite of packing, right? So in this case, you want to extract values from a tuple. So in this case, we define a tuple such as 1, 2, 3, and now you want to unpack it, right? You want to access these individual elements. And since we have 3 elements, I'm using 3 variable names here, A, B, C, and assign my tuple to these. And Python is smart enough to know that, well, I have 3 elements in my tuple, and I have 3 variables here, A, B, C. So I'm going to assign the first one to A, the second one to B, and the third one to C. So this is what is known as unpacking. And now you can see that if I check type of A, because now it's just 1 by itself, this means that this is an integer, right? Or if I check type of C, you can see that we get a string. Okay, so let's put this back where it was. Something which is really powerful when you're using unpacking, you can use the asterisk operator. So what does this mean? So let's say in this case, you have my tuple, which has 5 elements, and you want to separate the first element from the rest of them, but you don't want to individually unpack the remainder of elements that you have. So in this case, you use something very similar to what we used before for unpacking. So you have this variable called first. And if you wanted to follow the same like principles, now we have to call like second, third, fourth. Basically, we have to have 5 variables here. But I do not really want to separate the rest of them. So you use this asterisk here and you give it a name. I just call it rest here or something else. And once you run this, you can see that now we have this very nice way of selecting the first element and letting the rest of them to be still together. So this asterisk here is very important because if I don't have this, obviously Python doesn't know what to do with it because it says that, well, I have too many values to unpack, right? And you have like 2 variables here, right? You need to add more variables on the left side of this equal sign. But if I put this star here, Python knows that, well, we want to use this trick where we want to pick the first element and then the rest of them all like pack together during this unpacking process. And that's how it works. Okay, so now let's go to the zip function. So my goal here is that to slowly introduce you to different very useful functions in Python. You know about print, you know about len or len, you know about type, type, where you can find the type of any object. Another thing which is very useful to have in your toolbox is the zip function. And what zip function does, it combine elements from 2 or more iterables. We're going to very precisely define what iterables are, but iterables are things like lists, means that you can iterate over the elements of a list, right? You can start from index 0, go to the end of the list. And what this zip function does, it creates tuples from corresponding elements from the 2 lists that you have, which means that it pairs elements at the same position and create tuples combining these elements from this input list that we have. In this case, we have list 1 has 3 elements, 1, 2, 3. List 2 has A, B, C. So when you say zip list 1 and list 2, what this does is gonna look at 1 and A, so because these are both at index 0, and put them together in a tuple, and then move on to the next one, which is 2 and B, put them in a tuple, and then 3 and C. And what it does, it creates a list of these tuples, right? So if I run this cell, you can see that I have a list because I have these square brackets. And then the first element of this list is a tuple, which contains 1 and A, 2 and B, and then 3 and C as the third element in this list. So this is sometimes very helpful that you might have, think about it in this way, in a mathematical sense, you may have like X, Y coordinates, a 2-dimensional plane. And in this case, you want to have each X coordinate to be paired with a Y coordinate, right? So you can have a list of X coordinates, list of Y coordinates, and then use this zip to have this 2-dimensional coordinate system that you need. Next, let's move on to the third data structure that we have here. So far we talk about lists and tuples. Now we talk about sets. So what is the main difference here? Sets are an unordered collection of elements, right? So this means that now you don't have any more the indexing system that we talk about. We said that index 0, index 1, that's when you have an ordered collection. But in this case, we have an unordered collection of elements. And what this means is that, or what this implies is that each element in a set must be unique. In that sense, means that you cannot have, let's say, 1 or 2 like multiple times in a set, right? So all the elements in the set must be unique. But sets are mutable, meaning that you can add or remove elements after this set is created. You cannot have duplicate elements, as we said. And in order to define them, you can use curly braces, right? So that's reserved for sets. And as we said, because we have an unordered collection of elements, there is no indexing or slicing you can use here. In this case, we are using these curly braces. We define the set mySet. And you can use the add method to add an element here. So you can see that now we added 5 to this set that we have. We can use the len or len function. And we have 5 elements as we expect. You can say that you want to remove 2 from this set. That's using .remove. And you can see that 2 is now removed. It's not there anymore. And let's say what happens if I add 1 to this set that we have. Since already I have 1 here, right? So you can see that really we cannot add it one more time. It's already there, right? So you cannot have duplicate elements. And you can see that if for whatever reason you want to do indexing here, you get a message here, error message, right? The type error that says that set object is not subscriptable, right? So this means that you cannot really do indexing here because there's no notion of location or position between these elements that we have here. The last data structure that we really need a lot, or we use a lot in machine learning and data science is the dictionary. So what is a dictionary? Dictionaries are unordered collection of key value pairs. So there is no more indexing here, like what we had with list or tuples. We could use indexing and slicing. In this case, we cannot do those things. Dictionaries are mutable, meaning that you can add, remove, modify key value pairs. And again, the key thing here is that because of the way that dictionaries are structured, using these key value pairs, now you can access values using corresponding keys, right? And the way that this works is that you can have, let's say, a dictionary here that we define, and we have a key, which is name, and the value, which is John, right? So that's what we call a key value pair. They are separated by a colon. That's how you notice how you define key value pairs. And then you have age 25, right? So in this case, we can define a list that contains John and 25, but then you have to memorize or remember that John is, or the name is the one at index 0 and age is at index 1, right? So it's kind of like hard to remember that, right? And let's say you want to do some data analysis, you need to retrieve that information. In this case, when you define a dictionary, you don't have to remember the location, right? You just need to know what key you used before. Use the name key. So now just retrieve what is included or in the name key. So that's how the information retrieval works. And the way that you can define dictionaries is using curly braces, like very similar to what you did with sets. But remember, in this case, you need to have these key colon value pairs, right? So that's how you can distinguish between them. And as we said, in order to accessing values, you just use the name of the dictionary, you pass the key, and then you get the value, right? So this is something that makes it much easier, right, than remembering the location or the index of elements. In this case, we have a dictionary. We're using curly braces or brackets. We have this key value pair. So this is key value pair number 1, key value pair number 2, and number 3. But again, we do not have indexing here. Just remember that. So this means that now, let's say, look at the type of this, and you get a dictionary or DICT. And now if you want to look at the name of this person, you have the information in this dictionary, you just use my_dict and then use name, right? And in this case, we should be able to get John, right? Because that's the key value pair that we have. And you have a lot of interesting methods here. Let's say you want to know what are all the keys that you have in a dictionary. It is likely that somebody gives you a Python dictionary. You don't know what keys they use. You want to know, do like exploratory data analysis. So in this case, use .keys, and this will give you a list of all the keys, right? Name, age, city. Is that true? Name, age, and city. Yes, these are the keys that we have. And then you can pick these keys and look at the corresponding values as you want. We can also look at all the values too, if you want. And in this case, you can say, what are all the values that I have in my dictionary? And you can see that we have John 25 and then New York, right? And you can also use like len, that we have used before. So in this case, this means that we have 3 key value pairs. Remember, we are not counting these individually because these 2 things are actually together. It's a key value pair. So we have 1, 2, 3 key value pairs. And very similar to dictionary to Python lists, for dictionaries, we can create an empty dictionary using curly braces with nothing in it. And in that case, you can add key value pairs to this empty dictionary later by assigning values to a specific keys, right? So in this case, I create this empty dictionary, and then I'm gonna say that I want to have this key and this value. So this is an assignment operator. I want to have this key, which is age, and this value. And if I look at my dictionary, you can see that, yes, we have created these 2 keys and we have the corresponding values stored there, right? Which makes it much easier to retrieve this information later on. But let's say with this dictionary that we want to see whether the key cd exists in this dictionary or not. And again, we use the in operator that we saw before with list. And in this case, this automatically looks for all the keys that we have in this dictionary and returns true if city is one of those keys. And if not, you get false. So in this case, it's false because this dictionary only has name and age keys. But for name, if I run this, you can see that we get true. The last method or function that we want to talk about with dictionaries is .items. This is very helpful because what it really does is that it returns a list of key value pairs in the dictionary as tuples, right? So this is my dictionary that I have, right? You have these key value pairs. And this, what it does, these items, so you can see that you have this thing that looks like a list because you have these square brackets. And now you have these tuples, right? The first element is a tuple. You have key and corresponding value. And then you have other tuple, which is the key age and the value. So if you prefer to work with tuples, you can always use the name of dictionary .items. And in this case, you get a list of all these tuples, which they contain key value pairs. And you can see that here we only have 2 key value pairs, so we have 2 tuples. And similar to lecture 1, we have homework assignments for this lecture. In this case, we are going to look at some of the basics of what we just mentioned about slicing, indexing, working with tuples, and be able to modify or change values. And also we have a very interesting problem here where you're given a list and you want to divide these into 3 equal parts or chunks, right? So here, for example, you can use the len function to find the length of this and then divide it possibly by 3. So this means that you know what should be the size of each part or chunk. And based on that, you can do indexing and so on. So I hope you found this video helpful, and please let me know if you have any questions. Hello, everyone. In this video, we continue our discussion on data structures. A data structure in Python is a way of organizing and storing data so that we can handle them efficiently. In particular, we talk about built-in data structures in Python, such as lists, tuples, sets, and dictionaries. And although these data structures provide a lot of flexibility, but in many machine learning and data science problems, we need to be able to store multidimensional arrays of data. So what does this mean? So let's say we have a data set where we have 1,000 houses in this data set, And each house has multiple features or attributes, such as the number of bedrooms, the square footage, etc. In this case, we cannot simply use a Python list because then we have to store multiple pieces of information for each house in our data set. What makes more sense is to have a two-dimensional array where one dimension corresponds to different houses that we have in our data set, and then the other dimension corresponds to features or attributes for each house. In order to implement this, we can use NumPy, which is a fundamental library for scientific computing and data science with Python. And the very special thing about NumPy is that it provides support for large multi-dimensional arrays, such as matrices, along with a collection of mathematical functions, random number generators that you see in probability and statistics, linear algebra routines, and a lot more. The fundamental data structure in NumPy is known as ND-array, which stands for n-dimensional array. ND-arrays can have multiple dimensions, allowing for the representation of matrices and hard dimensional versions of matrices, which we usually call them tensors. ND-arrays are very memory efficient and faster than built-in Python lists, especially for large datasets. And this efficiency is crucial for numerical and scientific computing and in general for data science and machine learning problems. And the other thing that we need to consider here about the importance and significance of NumPy is that many other libraries in the Python ecosystem, such as Pandas, scikit-learn, TensorFlow, they build upon NumPy. So this is about the dependencies between libraries and packages that we discussed in lecture 1, where we said that we need to have some sort of package manager, such as Conda or Anaconda distribution platform. But NumPy comes standard with Anaconda distribution. So if you have followed the instructions to install Jupyter Notebook and Anaconda distribution, you should be able to have access to NumPy. And very similar to math module that we used before, and we had to import math to be able to use math module. Here is the same thing. We first have to import NumPy. However, we can also make this a little bit shorter, this name, and we can import NumPy as, and here we assign the name NP as an abbreviation for NumPy. So this part is really optional. You can just import NumPy, and anywhere else here where we have NP, you just have to replace that with NumPy. But it is a good practice to use the abbreviated name, which is NP. And one way to make sure that you have NumPy and it's working well, very similar to what we did before with Python and Conda versions, is to see what version of NumPy you have. And we can do this here using this np.__version__. If I run this cell by using Shift-Enter or using run here, you can see that we have version 126.2. Okay, so that's great. It means that we have NumPy here. So as I said multiple times before, the nice thing about NumPy is that you can have multi-dimensional arrays. So what does this exactly mean? In this context, an axis represents a specific dimension along which the array or the data is defined. So this means that in this case, we have a one-dimensional array. This is very much like a Python list where you have these values stored across this one axis that we have. And remember that indexing in Python always starts with 0. So this means that this axis that we have is axis 0. And what is the shape of this array? Which means that we need to count the number of elements we have along each axis. So here we have one axis and we have 4 elements in it. So the shape is 4, comma, and these parentheses. And if you're wondering why we are using this, remember that if we use parentheses, this is what is known as the tuple, right? That's like one of the main data structures we covered in the previous lecture. And we said that in order to make sure that we have a tuple with a single element in it, you need to have the trailing comma that you can see here. So you can see now how all these different pieces of information that we have, they relate to each other. So the shape is a tuple that counts the number of elements along each axis. Here we have one axis, so we have one element, and we have the trailing comma to make sure that this is actually a tuple. One thing that is used very, very frequently in data science and machine learning problems is the 2D array. This is the example that I said about houses and the attributes and features that we have for each house, right? So in this case, you have a two-dimensional array, meaning that you have two axes. So axis 0 is this vertical one, and axis 1 is this horizontal one. And I really want you to remember, take a snapshot of this and remember this, the way that we index these axes that we have here, right? So axis 0 is this vertical one, and axis 1 is this horizontal one. So what is the shape here? So you can see that we have two elements along axis 0, right? 1, 2, and we have three elements along axis 1. So the shape is a tuple where we have 2 and 3, right? So in some sense, the length or LEN, length of this shape, gives you the number of axes that we have. And we can do the same thing with this three-dimensional array that now we have. So you can see that now we can expand what we know about these ND arrays, right? So we have axis 0, we have axis 1. So what we have in the front face here is exactly that 2D array, but now we can have this third axis, which is axis 2, and now we put together all these different two-dimensional arrays, and the overall structure is a three-dimensional array. So what does this mean, this evolution from 1D to 3D array? So let's say for 1D array that we have on the very left, you can have one house in your data set, and there are 4 features associated with that house, right? For example, the number of bedrooms, the number of bathrooms, square footage, etc. For the middle case, where we have a 2D array, you can have 2 houses in your data set, so that what that axis 0 corresponds to, right? This means that the first one you can see here is house number 1, and the second one is house number 2. And then the axis 1 corresponds to the features for each house. And in this case, because we have 3 elements, means that we have now 3 features for each house. What is the 3D array on the right side referred to here? And you can see in this case, you may have, let's say, 3 different regions in the United States, and each axis element in axis 2 corresponds to one region, right? And in each region, you have 2 houses with 3 attributes, right? So we can create these multi-dimensional arrays that can contain a lot of information about the houses in each region, and then how this expands to different regions in a country. And now we can also have a 4th axis here that can be like different countries, right? So you can see that we can create these multi-dimensional arrays that contain a lot of information, and we cannot typically do these types of data storage and handling using like Python lists or dictionaries, etc., that are built in Python. Something else to keep in mind here is that the number of axes in an ND array is referred to as its rank, right? So in the left array here, the 1D array, we have 1 axis, so it's rank of 1. And then the middle one is rank of 2, and the one on the right side is rank 3. And something that we can also practice here, since this is not included here, what is the shape of the 3D array that we have here? So you need to count the number of elements along each axis, right? So the shape is 2, 3, 3, right? So because we also have 3 elements along axis 2. So once you remember the way that we re-index these axes, it becomes very easy to find the shape of each array. And in particular, as I said, we really care about 2D arrays or matrices, right? In this case, the rows are the horizontal lines in the table, and the columns are like the vertical lines or columns that we have here. As you can see here, in this case, we have the first row, which is shown here. And then because we have these indices 1 through n for the rows or the first index here, you can see that we have n rows, right? So that's the last row, which is row number n. And then similarly, we can define the columns that we have here, right? So we have column 1 up to column m, which is the last column that we have here. So these rows and columns corresponds to axis 0 and axis 1 that we have there. And in this case, we call this matrix of size n by m because we have n rows and m columns. And we will talk about indexing these two-dimensional arrays, but you can already see now in order to retrieve each element here, we need 2 indices. One that shows that the row number and the other one the column number, right? And in a programming Python programming language, this means that we have to give the index for axis 0 and the index for axis 1, and we'll be able to retrieve the corresponding element. Okay, so now let's see how we can actually create NumPy arrays in these cells that we have. So we're going to start with a one-dimensional NumPy array using np.zeros. So what this does, it creates a one-dimensional array of all zeros with 4 elements in it. So if I run this, you can see that we have a one-dimensional array. So this looks very much like a Python list where you have 4 zeros here. And we know that this is a NumPy array because it shows here array, right? So if it was as a Python list, we wouldn't get this array here. And as we said, for every NumPy array, we have an attribute which is called shape. So if I say a.shape, you can see that we get 4, the trailing comma, and these parentheses, right? So this shows that we have 1 axis here, or the rank is 1. And remember, here we shouldn't use parentheses because shape is not a function or method here. It just gives some feature or attribute of this array. The same thing with this ndim attribute, which is the number of axes or rank. So if I run this, we get 1. And if you're not sure, you can always use the type function in Python, and it will tell you the type of the object that you have. And in this case, if we run this cell, you can see that we get numpy.nd array. Okay, so now let's make this a little bit more complicated by looking at a 2D array, right? So in this case, I'm using np.zeros, but now I pass this tuple, right? So what this means is that now I want to create a 2D array of size 2 and 3, 2 elements along axis 0, 3 elements along axis 1. And this is exactly what we expect, right? There are a couple of things here. First of all, note that you have 2 parentheses here, 2 square brackets here. And what this means is that this is a 2D array. And then you can see that along axis 0, which is the vertical line that we have here, we have 2 elements. And then along axis 1, which is the horizontal one, we have 3 zeros. In other words, if I want to put this in the terminology that we had, this matrix has 2 rows and 3 columns, right? So this is a 2 by 3 matrix. And we can look at the shape attribute. You can see that now we have this tuple 2 and 3. And we can look at ndim, which gives us the rank or the number of axes, and we get 2. We can continue doing this with higher dimensional arrays, right? So in this case, we are creating a three-dimensional array. And why is it three-dimensional? Because we're using np.zeros. And then what we are passing here is 2, 3, and 3, right? So if I run this cell and print this NumPy array B, you see that you get 3 square brackets here. So this is a sign that this is a three-dimensional array. And the way that it works is that you can see that in the first element of axis 0, you have this 3 by 3 array. And then in the second element of axis 0, you have this 3 by 3 array. And now if you put these together, you get 2 of these 3 by 3 arrays, which means that it's 2 by 3 by 3. So once you get to three-dimensional arrays and higher, you need to really practice a lot to make sure you understand the way that NumPy organizes these arrays. But you can see that with two-dimensional arrays is much easier because we have the concept of rows and columns, and we don't have the third dimension. Okay, so moving on, now let's look at the shape of this array B, and you can see it's 2 by 3 by 3, and we can look at ndim, which is the number of axes, or rank, which is 3. And as we said before, one way to find this ndim method, which is the number of axes, is looking at the length of b.shape, right? Because if we count how many elements we have here, that's the number of axes. So you can see here that we can use also retrieve this information using the shape attribute. So far we have created arrays filled with zeros. Now let's create one filled with ones, right? So you can see here we have a 3 by 4 array. So we have 3 rows and 4 columns, and we have all elements 1. There are multiple ways to create NumPy arrays. For example, the other way to do this is using np.full. And what this does creates an ND array with a specified shape and fills it with a constant value. So let's say you want to create a 2 by 3 array filled with the constant value 7. So use np.full. And inside, the first argument, which is this one, is the shape, which is 2 by 3. And then the second argument is the constant that we want to use to fill this array, right? So in this case, we get this 2 by 3 array, and we have all 7s. The other thing that you can do is to actually have a Python list and convert or transform it to a NumPy array. In order to do this, you can use this np.array method or function. So in this case, use np.array and you pass a Python list. So in this case, our Python list is 143, and it's a Python list because we are using square brackets. And we pass this to this np.array, right? So in this case, if I run this, you can immediately see that it says array. So this is a NumPy array, but you can also use type if you want to. And you can see that it is indeed a NumPy ND array. If you look at the shape, you can see that the shape of this is 1, it's the rank of it is 1, but the shape of it is 3, comma, and these parentheses, because we have one axis, and in this one axis, we have 3 elements, right? But if you look at x.ndim, that's what was originally talking about, you get 1, right? Because we have one axis, or the rank of this array is 1. Now, how can we create a 2D array using Python list? In order to do that, it's a very simple idea. You have to provide a list of lists. And what this means is that in this case, I have a list where the first element is another list, which is 245. And then the second element is another list, which is 927. So what this means is that if I create a NumPy array using np.array, you actually now you get a 2D array where 2, 4, and 5 are placed in the first row, and then 9, 2, and 7 are placed in the second row of this array, right? And therefore we have 2 rows and 3 columns, we can confirm this using what.shape. So you can see that we get 2 by 3. And we can look at endim to find the number of axes, and we got 2. NumPy also comes with a lot of other useful ways of creating NumPy arrays. And one of them is this np.arrange. So what np.arrange does is that it creates an ND array with regularly spaced values within a specified range. So the syntax for np.arrange, if you go to the documentation page of NumPy for this method or function, is that we have the start, a stop, and a step points. And obviously we also have this other argument, which is dtype, which is the data type. So this is if you want to, for example, create an integer, floating point numbers, etc. You can specify this. But the main part is this first part, that we have to have a start, a stop, and a step parameters. And if you look at it, for a start and a step, they are in these square brackets. And what this means is that these two parameters are optional, meaning that if we don't specify the starting point, by default is 0, right? Which is the first index or first location that we have in our array. You always have to provide the stop, because wherever we have to stop, right? In this case, you want to create regularly spaced values, so we can always start from 0, but it should stop at some point. So that's something you have to specify. And remember, very similar to the slicing technique that we mentioned, the stop is always exclusive, meaning that it is not included. And then for the step, the default value is 1. Right, so it's a very much similar to the slicing technique that we discussed in lecture 2. So let's see how this works, right? So I'm saying np.arrange 10, and if we see what's inside Z, so it's a NumPy array because it has array here. It starts from 0 and it goes up to 9, right? So 10 is excluded. But what is cool here is that because it starts from 0, if you count, you actually have 10 elements here. Right, so from 0 to 9, we have 10 elements. But it starts from 0 and it goes to 9. Now, if you want only the even numbers from 0 to 10, obviously exclusive 10, then you can set the step size to be 2, right? So now you start at 0, you stop at 10, and the step size is 2, right? So 0, not 1, 2, 4, 6, 8. And then if you want to add 2 to 8, we get 10. And remember, 10 is exclusive. So that's where we have to stop at 8. And if you want to start at location other than 0, you just have to specify that, right? So here we say that we want to start at 1. And we want to go up to 5, exclusive 5, right? So you get 1 through 4. So that's one way of creating these evenly spaced values or regularly spaced values, and this is very useful for indexing. But something else you can use is np.linspace. So np.linspace is kind of similar to that, but it creates a specified number of evenly spaced values over a specified range. And in this case, the main difference is that both endpoints are inclusive, meaning that np.linspace, what it means is that we want to go from 0 to 10, and we want to include both of them, and we want to have 5 equally spaced points. So if I run these, you can see that we get the 5 points that we want: 0, 2.5, 5, 7.5, and 10. And actually the length of each of these intervals, if you look at it, is 2.5. And the reason is that if you have like here 5 points, you actually have 4 intervals: 1, 2, 3, and 4. And then if you divide the entire length, which is here 10 minus 0 or 10, by 4, you get 2.5, right? So that's something to keep in mind here, that in this case, you get whatever number you mentioned here, like for example 5, you get 5 equally spaced points. And this means that now the number of intervals is always that number that you have there minus 1. But NumPy has a lot of really interesting applications. One of them is creating random numbers, right? That's something that We see a lot in probability, statistics, and obviously data science. And inside NumPy, we have a submodule which is called random. So the way that we can access these is np.random that provides functions for generating random numbers, right? And there are, several key distributions that we, really use them a lot in data science. One of them is uniform distribution, right? This is something you have in your calculators too, right? So you want to generate a uniform distribution in the interval from 0 to 1. And in order to do this, you can use np.random. And because we want the uniform distribution, we just use rand. And you specify the number of elements you want. So in this case, we get 5 random numbers from 0 to 1. And this is the distribution we have. So here you can, for example, make this 10. So in this case, you get 10 numbers, random numbers. You can make it 100. So you can see that now we have a larger list of or array of random numbers. But remember, still this is a one-dimensional array because we have one square bracket. It's just we cannot have all this information in one line. So you can see that it's in multiple lines. But other than that, it's really a one-dimensional array, meaning that everything is along one axis. So let's put this back to 5. It just makes it a little bit easier to see the output of this line. And then we have other distributions too, like normal or Gaussian distribution. And if you want to work with the standard normal distribution, and the standard means here the mean is 0 and the standard deviation is 1, you can just use np.random.randn. So you have this extra n here. And in this case, if I generate, let's say, 5 numbers, as you expect, because the mean is 0 and we have this standard deviation 1, we should get both positive and negative values, and we do get that, right? So you can see that we get 2 negative values. And something to remember is that every time you run this, because it's a random number generator and has a different seed, it gives you a different result. But overall, this is a random number, set of 5 random numbers coming from or sample from this standard normal distribution. Now, the nice thing is that you can also control a lot more about the parameters of these random numbers. So let's say instead of working with the standard normal distribution, you want to have the flexibility to change the mean and a standard deviation. And NumPy has already built-in ways of doing this. And instead of using randn, you can use normal. So np.random.normal. And you have multiple inputs that you have to provide here. This log or LOC is the mean of your distribution. Here we set it to be 10. The scale is the standard deviation. We set it to be 1. And the size, meaning that how many samples we have to draw from this distribution. So you can see that now, obviously, these numbers are closer to 10 as we expect, because that's the mean or average of this distribution. So you can see that now everything looks to be centered around 10. So we have a lot of nice ways of working with these. And like before, the most important thing is to look at the documentation page. So you can see that here is part of numpy.org, the official web page for NumPy. And if we click on this link here, you can see that here explains everything that we need to know about np.random.normal, right? So there are random samples from a normal Gaussian distribution. And if you look at the parameters here, you can see that it is mentioned that this LOC or log is the mean or center of the distribution. The scale is the standard deviation, and size is the output shape, right? So for example, you can give a tuple with 3 elements if you want a 3-dimensional array, or whatever dimension that you're looking for. So we have a lot of options here. Now we can also have some discrete distributions, right? So if you want to have a uniform integer distribution, you can use np.random.randint, right? So that means that it's an integer distribution. And what happens here, you specify a range here. So this is the low number, this is the high number, and this is the size that you want to have for your output. right? So this says that we want to have a 2 by 5 array. So this is a matrix with 2 rows and 5 columns. And you want to fill these elements by a random number, which comes from a uniform integer distribution from 1 to 5, right? So that's what you can see here. I can, for example, change the number of rows to make this 3 by 5. And a quick experiment here, it shows that this 5 here is exclusive, right? Because I'm increasing the size of this array, and you can see that we never see 5, right? And this tells us that this starting point is inclusive and the stopping point is exclusive. Okay, so let's put this back 2 and 5 as it was before, and you can see every time I run this, we get different results. The other thing, for example, that in terms of discrete distributions is binomial distribution. So the way you can think of binomial distribution is that you repeat some experiment n times, and each time the probability of success is p. So in this case, each trial or experiment has binary outcome, meaning that it's either success or failure. And the probability for success on a single trial is p. And you want to find the probability mass function, which can be found using this formula. So in this case, if you want to have k successes, what you do is that you have this n choose k, so the number of ways that you can have k out of those n experiments or trials. So this is the combinatorial problem. And then you have to multiply this probability of success k times, because each time the probability is p. So that's where we get this exponentiation, p raised to the power of k. And because you only have 2 outcomes here, so the probability of failure is 1 minus p, right? Because you know that the sum of probabilities must equal 1. And in this case, you have 1 minus p raised to the power of the number of failures, which is n times k. So this is the probability mass function for a binomial distribution. But if you want to draw samples from binomial distribution, you really don't need to implement this from scratch, because you can just use np.random.binomial. And you provide the total number of trials or experiments, the probability of success, and then the size of the random array that you want to have. So if we run this, because the probability is greater than 0.5, this means that it is more likely to have more than 5 successes in these experiments. And you can see that we get 8, 7, 10, 5, 7, right? Because we do these random experiments 5 different times. And we can see that the first time we get 8 successes, and then 7, 10, 5, and 7. And we can obviously run this multiple times. So each time we get a different result based on the seed that you use. And that's what we have in the next cell here. So if you want to get reproducible results, meaning that still you have a random number generator, but a random number generator that gives you the exact same result every time you run it, and this is very useful in terms of reproducibility of your code, you can set the seed of the random number generator. And the way you can do this is using np.random.seed. And the number here doesn't matter. You can use 42 or any other number you want, but you can see that in this case, if I run this cell multiple times, then you can see that I'm running this again and again, you can see that we get the same exact result. But if I change the seed, this will be obviously changed, right? And in this case, I'm running this multiple times and I'm getting the same results. So this is something very helpful later on. If you want to make sure that your code is reproducible, you can set this seed value for the random number generator. The next thing we want to talk about is reshaping an array. So once we have an array, can we change its shape? And the question is yes. Altering the configuration of an ND array is easily achieved by adjusting its shape attribute. But you have to make sure that the total size of the array must remain unchanged during this operation, right? So let's create these numbers from 0 to 11 using np.arrange. Remember, 12 is not included, but we obviously have 12 numbers from 0 to 11. And in this case, this is a one-dimensional array, right? So if I just put, for example, a.shape, right, it's 12, and then the trailing comma, which means that this is a one-dimensional array. So now if you say that a.shape equals, so now you want to assign something to a 3 by 4, obviously we can't do this, right? Because for a 2D array of size 3 by 4, we have 12 elements, and we originally had 12 elements. So in this case, you can see that we get a 3 by 4 matrix. Great. And if I use ndim, the number of axes of the rank is 2, and the shape now is 3 by 4, right? So we assign a new value to this shape attribute, and this is a tuple. The other thing that you can do is to use the reshape function. So this literally does very, very much the same thing. And what it does, that's something important to remember, is that it creates a new ND array, which is pointing to the same data. So remember that we said that whenever you have a variable, this information is stored somewhere in the computer's memory, and you're just assigning a label or container for that specific location. So when you're using this a.reshape 6 and 2, right? So obviously we have 6 rows and 2 columns. That's great. But remember that this B is referring to the same location in the memory. So what this means is that if I change A, for example, I change the element of A, where we have the first row and first column, and set that to be 20, right? So here I'm changing this element of A. Now you can see that we have 20 here. And if I check B, you can see that I also have 20 here, right? So this means that when I use that a.reshape here, we didn't create a completely separate copy of it. It's just the same data that we are referring to, but with different shapes. And in this case, if we change A, we are changing B as well. So that's something important to keep in mind. So the other thing also it's useful to know about reshaping is that in some cases you may have like a two-dimensional array, three-dimensional array, and you just want to simply create a one-dimensional array, meaning that this is what is known as like flattening, meaning that you want to have a flattened view of your array where you have a 1D array. And in this case, you can use this .rabble. And what this does, it takes B and make sure that now everything is flattened to have a one-dimensional array, right? So you can see that 20 and 1, 2 and 3, 4 and 5, they all get put together in a one-dimensional array along one axis, and then the last two elements are 10 and 11. So what is nice about NumPy is that, well, we have this very nice way of organizing data in terms of multi-dimensional arrays, but also we have a lot of interesting mathematical and statistical functions. For example, we can perform element-wise operations like np.power for exponentiation. In lecture 1, we talk about like comparison operators. When you have two, let's say, Python variables, we could compare them together. In this case, we usually have different arrays, right? So it's not just like one variable. We have multiple values included inside an array. And so np.equal, np.greater, what they do, they provide comparison operators, but in a sort of like a multi-dimensional way where we can compare different values element-wise, right? So if you have two one-dimensional array and use np.equal, then you can see whether the first element of the first array is equal to the first element of the second array, and similarly, if the second element of the first array is equal to the second element of the second array, right? So that's how this works. You also have universal functions such as sine, cosine, hyperbolic sine, exponential, logarithm. This is actually NP, not NO. So you can see that we have all these universal functions. You can also find descriptive statistics, finding the mean or average, standard deviation, mean, max, percentile. So if you have any statistics courses, you're probably familiar with these different ways of finding descriptive statistics. Or in linear algebra, we can find dot product between vectors or matrix inversion, matrix eigenvalue decomposition, etc. Right? So this lean out here stands for linear algebra. You get a lot of interesting linear algebra routines that you can use. And just to showcase you some of these, right now we don't want to go too much into these different topics, but let's say we create this one-dimensional array, which contains 2, 3, 8. You can use np.power, and then you pass the array that you have in 2. So this means that you want to raise each element to the power of 2, right? So we get 4, 9, and 8 squared, which is 64. And now if I have a second array, which contains these 3 elements, 2, 5, 6, now you can use np.equal and pass these 2 arrays. The first array, my array, and my array 2, and see whether they are equal or not. So this is an element-wise operation. 2 is equal to 2, so that's true, but that's not the case for the other 2 elements. So we get 1 true and 2 falses. And you can also use like np.grader, right? So in this case, we can see that only for the third element, 8 is greater than 6, but for the other elements, actually, it is false, right? Meaning that the first element of the first array is not greater than the first element of the second array. So a lot of this we covered before, but now we just can do this element-wise in a very efficient manner. And other thing that is very important, for example, let's say we have this my array, which is a 2D array, right? So the first row contains 1 and 2, the second row contains 3 and 4. We can find the mean or average of all the elements, right? That's what we call here overall mean. So if you add everything here, it should be 10, 1 plus 2 plus 3 plus 4, divide by 4, you get 2.45. But also, the cool thing about NumPy arrays is that you can calculate mean along a specific axis, right? So remember, axis 0 refers to the vertical axis, and that's where the columns of the matrix are, right? So this means that you want to find the mean or average column-wise. And if you do this, right, use np.mean and set axis equals to 0, you can see that we get 2 and 3, right? Why? Because the first column contains 1 and 3 here. And so that's 4 divided by 2, which is 2. And then 2 plus 4, which is 6, divided by 2, which is 3. And similarly, we can find the mean across the axis 1, and that's the horizontal axis, which means that these are the rows of this matrix. And in this case, if we run this, you can see that we get 1.5 and 3.5. And the reason is that 1 plus 2 is 3, so that's the first row. And divide by 2, we get 1.5. And then similarly for the second row, we get 3 plus 4, which is 7, divide by 2, which is 3.5. So you can practice this and see how these different axes, you can find the average or mean, maximum values, different descriptive statistics. But it is very nice to have this option of working along different axes. Some other operations that are more useful in terms of linear algebra routines is, for example, dot product or inner product. In this case, you have 2 vectors of the same length, and then the dot product, which we use this notation here, is simply the multiplication of element-wise multiplication, and then adding all these results of these multiplications, right? So A has n elements, B has n elements. You multiply the first element of A by the first element of B, and similarly the second element of A by the second element of B, and then you do these multiplications and add all of them together, and the result is a single number. So here you can see that we can test this by creating 2 1D arrays. One is 1, 2, 3, and the other one 4, 5, 6. And the function that we have for this is np.dot, and then you pass the 2 arrays. So in this case, we get 32, which is it's like 4 plus 10 plus 18, right? And that gives us 32. Now, let's talk about matrix vector multiplication. That's something that we use a ton in machine learning and data science, right? That's something that, for example, when we talk about linear regression and its extensions, we always need matrix vector multiplication. And the good news is that we can do this very efficiently using NumPy. So recall that in this case, this matrix that we have here has m rows and n columns, which means that is m by n. And this vector in front of it has n elements, right? So in this case, if we perform the multiplication, we have different ways of doing this. One way is to take the first element that we have here and multiply this by the first column. And similarly, we multiply this last element here by the last column. And this would be the result of this matrix vector multiplication, right? So it would be an m-dimensional vector. And the other way to do this matrix vector multiplication is in the form of dot products, right? So in this case, we look at the rows of this matrix and we find the dot product that we just mentioned between these two one-dimensional arrays. And that's something that we can write in terms of this summation here, right? So you can see all of these elements, because during the first row, the first index is always 1. And then the second index shows you the column number. So here is I, and we multiply by xi. And I goes from 1 to n, right? So this is the mathematical definition of the dot product between these two 1D arrays. And we can repeat this until when we get to the last row, which is row index m. So you can see that these indices are all m. And we have, again, a summation from 1 to n of mixi's. So we can perform matrix vector multiplication using either of these two formulas. But the nice thing is that this is already implemented in NumPy. And the way that we can do this is using np.matmul, which stands for matrix multiplication. Okay, so now what we're going to do is going to create a matrix A. So this is a two-dimensional array. And we know this because we have a list of leads. And then we have this X, which is a one-dimensional array because it's just one list with 3 elements in it. And if we do this matrix multiplication, you can see that we get 25 and 58, right? Just to show the shapes of these arrays, A is 2 by 3, and X is a one-dimensional array with 3 elements. So when you do matrix vector multiplication, this number and this number should be equal. Otherwise, we cannot do the multiplication. And the result is always this number by the number that we have after this trailing comma here. But in this case, you don't have anything. So that's why we just get a 1D array with 2 elements in it, right? And here we can also visualize what's inside A. So this is our A, which is 1, 2, 3, 4, 5, 6. And this is what we have in X. So one way to confirm what we have for matrix multiplication is to find the dot product between the first row and X and the second row and again X, right? And the way we can do this, again, using this indexing notation, right? So what this says is that we want to have the first row of A and all the elements that are in those columns. So we are not really indexing across columns. It's just we want to pick the first row and find the dot product or inner product between the first row and X. And similar here between the second row and X. And if you run this, you see that we get 25 and 58, which is the same as what we have here. So that's always something useful really to do to double check your analysis to make sure that you have not done anything wrong in your in the process. So now that we talk about selecting the first row of A, let's talk about, in the second row of A, let's talk about more in-depth about array indexing when we are working with these multi-dimensional arrays, right? So for one-dimensional arrays, we can access elements more or less like a Python list, right? Because it's basically a list, just, more efficient because we have all these built-in functions and methods, element-wise operations in NumPy, right? So in this case, we create a 1D array and we want to access the element at index 2. And remember that indexing starts from 0. So 0, 1, 2, right? So in this case, we get 3. And you can also use the slicing notation as before. This is the starting index and the stopping, which we don't specify, meaning that we want to go to the end of this NumPy array, which gives us 3, 4, and 5, basically these 3 elements. For two-dimensional arrays, where we have a matrix, you saw before too that each element that we have here needs 2 indices, right? Because we need to know where we are in the rows and in the columns, or where we are in axis 0, where we are in axis 1. So we need 2 indices, right? And in this case, let's create a two-dimensional array of size 2 by 3. And what this means here in this case is that we want to pick element at row 1. Remember, the first one is row 0. This is row 1. And then column 0, column 1, column 2. So this is the element that we want to pick, right? And you can see that we get 6. And in the next cell, what we are doing, we're saying that we want all the rows. So we don't want to do any indexing across the rows. But for the columns, we want 1 through 3. And remember, this is always exclusive. So this means that column 1 and column 2 and all the rows. So you can see that we get this portion of the matrix 2 and 3, 5, and 6. So basically very much like what we had before, except that now we have to do indexing across both axes. When you're working with more than two-dimensional arrays, something that is very useful is using ellipses, which is these 3 dots that you see here. And this is a convenient shorthand for representing multiple columns in an array slicing. And it's often used when you have, as I said, when you have arrays of more than 2 dimensions and you want to just specify a slice along a particular dimension, right? So let's create a 3-dimensional array. So you can see that we have 3 elements across axis 0, and then 4 elements axis 1, and 5 elements for axis 2. And in this case, let's say I just want to pick whatever I have in index 2 for axis 0, right? So again, now you need like 3 sets of indices, and the first one corresponds to axis 0, and I set that to be 2, right? So that should give me what we have here, right? Because this is what I have in the first element of axis 0, the second, and this is the third one, which is index 2. And if I run this, you can see that that is correct, right? So I get exactly what I have here. But then the problem was that I have to use columns, and you may have more dimensions or axes here. So one way to make this more professional is to just use these 3 dots, which is known as ellipses. And in this case, you can see that we get exactly the same result as before, and we don't have to specify that we want to select everything from all other axes that we have. The other important thing that we want to cover here is that for indexing NumPy arrays, you can also use Boolean indexing, right? So remember, Boolean values are true and false, and you can have Boolean arrays, meaning that arrays of true and false values. And you can use these to index or filter elements from an array. And this works as kind of like a mask, right? Where if you have true, means that I want to pick something. If it's false, means that I don't want to pick that element, right? So let's create a 1-dimensional array with 5 elements in it. And then I create this mask for indexing where I have true, false, true, false, true. So this means that I want to pick the first, third, and the fifth element here. And we can do the indexing like before. We just pass this Boolean array, and you can see that we have the first, third, and fifth element here, right? So why is this useful? Because in many cases, you want to actually do some sort of conditioning, meaning that let's say I have an array of elements like what I have here, right? So we are doing some data analysis and we got a bunch of numbers, and you want to only keep elements that are above some threshold, and this threshold is 8 here. So what you do first, you create this mask, which is a Boolean array, and you say that array greater than threshold. So what this does is creates a one-by-one sort of or element-wise operation to figure out whether each element is greater than 8 or not. So it will be a Boolean array of trues and falses. And now if you pass this to the array that you have originally, you will keep the ones that are actually greater than 8. Right? So you can see that in this case, we get 10 and 12. And you can easily see this by just looking at this mask, right? So you get true because yes, this is greater than 8, false, false, true, and false. And you use this for indexing, right? So when you're working with large arrays, you don't want to go and individually inspect them. You want to be able to pick the ones that, for example, are greater than some threshold, and you can really do this literally in one line of code, because what you can do, you can write this as the array, an array greater than threshold, right? So this can be written in only one line of code, and in this case, you get the result that you want. So it's a very compact way of doing indexing. The other thing I want to talk about here is concatenating NumPy arrays. And in order to do this, you can use np.concatenate, and the syntax or the grammar is that you provide this tuple of arrays, and then also you need to specify the axis along which you want to concatenate, right? So in this case, you can see that we have array 1, which is a two-dimensional array, and array 2, which is another two-dimensional array which has 5 and 6 in it, right? So you can see these arrays here. That's array 1 of size 2 by 2, and array 2 is 1 by 2. And now you want to concatenate these along axis 0. So what this means is that if you run this, you can see that we have the 1, 2, 3, 4, right? So that's the 2 by 2 array. And then the other 1 by 2 array now is concatenated. So the result is actually now 3 by 2, right? And we can confirm this too by looking at the shape attribute, which is 3 by 2. So this is very also handy if you want to have like concatenate or merge different data sets. You just need to make sure that you do it along the right or correct axis. And the last thing that we cover in this lecture is how to save and load arrays. Let's say you have done some data analysis, you have some NumPy arrays, and now you want to be able to store this information and load this information again. And one way to do this is using these two methods, np.savetext and np.loadtext, right? And the way you can use it with the savetext is that you need to provide the file name, right? What is the name of the file you want to store, and the array that you have, right? So let's say here we do something very simple. We create a 2D array using Python list. And in this case, you can say that, well, I want to use np.savetext, and that's the name of the text file that we have, and you provide the array. And now use the np.loadtext and just give the name of the file. And if you look at this loaded array, we can see that we were able to correctly and successfully load this array after saving it, right? So this is very helpful to make sure that the analysis you have done, you are able to store the result and be able to load the result later on, so you don't have to spend all the time again to redo your experiments. As before, we have 10 problems for homework 3, where we're going to extend on what we learned already in this lecture and do some practice and be able to really make sure that we truly understand the material covered here. In some of the cases here, you can see that I provided the documentation page for some of these NumPy methods. And this is just to make sure that you have the skills to be able to understand and read read the documentation for new NumPy methods whenever you need them. Thank you for watching this video, and I hope you found this video useful. Hello everyone. In this video, we talk about functions in Python. In both mathematics and programming, a function is a fundamental concept, but its specific definition can vary slightly between the two contexts. In mathematics, a function is a relation between a set of inputs called the domain and a set of possible outputs called the codomain, such that each input is related to exactly one output. It's like a machine that takes an input, performs a specific operation, and produces an output. Functions are often represented using notation like f of x, where f is the name of the function and x is the input. In programming, a function is technically a reusable block of code that performs a specific task or a set of tasks. It's a way to organize code into modular units, making it more readable, maintainable, and efficient. Functions in programming take inputs, arguments, perform operations, and return outputs. They help break down complex problems into smaller, manageable pieces. Therefore, it is critical to know how to use and define functions in Python. Okay, so now that we are done with the definition of function in Python, let us focus on two important pieces when you want to work with functions: input arguments and output parameters. Recall that functions can receive input arguments provided by the user or calling entity, and functions produce output parameters representing the results after completing their task. So this is very similar to the idea of domain and codomain when we talk about functions in mathematics. We have different types of functions in Python. We have built-in functions that we have seen a few examples of these so far. And the reason that these things are called built-in because you don't have to define them, and there are predefined functions in Python's standard library, and we do not need to import anything. For example, anytime you're working in Python, you can use the built-in function print, which prints a string, or you can use len, L-E-N, which gives you the length of a list or a sequence in general. Or you can use type, which gives you the type of any object in Python. On the other hand, we can define custom functions in Python. These are very helpful when you want to perform a specific set of instructions or tasks that are specific to your goals. And in this case, you can define your own function. And the way we can do this is using the def or def keyword. We can also have nested functions, which means that we have functions defined within another functions. This is kind of like a composite function in mathematics where you have functions where there are inside another functions. And also we have something which is very important for machine learning and data science applications known as lambda functions. Lambda functions, you can think of them as anonymous functions. So it's kind of interesting, but you can think of these as functions that they don't really have names, but you can use the lambda keyword to define them. And these are typically very helpful when you want to perform short and simple operations. And we're going to talk about these lambda functions that are very helpful for data cleaning, for pre-processing data, and therefore we need to learn about them. But let's get started first with built-in functions, right? Like, for example, the len function. And this is part of the Python standard library and is available for user without the need for explicit import statements. For example, here we have a list which contains three elements. And if I use type here, it tells me that the type of this object is a list. And this is consistent with what we learned in the data structures lecture. Or if you have another list, which I call it 1, 2, 3, 4, with the square brackets, you can use len on this or len, and you can see that we get 4 because there are 4 elements inside this list. But let's talk about custom functions, something that we need to learn to see how we can define functions on our own. You can define a function, as we mentioned earlier, using the def or def keyword. And here is the general syntax that you can use. So you use def, the name of the function, and then the input parameters or input arguments. So this is very similar to the idea of f of x, where f is the name of function and x is the set of inputs. Something which is very important, but optional when you define a function is to explain what that function is supposed to do. Now, this is what is known as docstring or documentation string. So this is some text that explains the purpose of the function, and you use these triple double quotes. And the nice thing is that anything here inside these triple double quotes is like Python comment, meaning that the compiler does not look at these in terms of Python codes, and this is just for readability and conveying some information about what this function is supposed to do. And then after docstring, usually you have the function body, and this is where you put your code that you need to provide to perform some task. And at the very end, if you want to return some parameters, meaning that you want to have output parameters and your function is supposed to return some values, then you must use this return statement. So you say return, and then whatever the result is. So this is something that is very important because I see this very often that you perform some operations here and we don't use return, and you get to see that when you're using your function is not producing any outputs, and that's just because there's no return at the end. And it's a very simple kind of mistake, but something that happens very often. So let's start with the very first function that we want to define here. We use the def keyword, the name of the function. It should be something meaningful, like add numbers. In this case, we have a function that accepts 2 input arguments and add them together. And do not forget to use this colon here, right? That's important. So you use the def, name of function, input arguments, colon. And once you do this, I can show you this even here. When I press enter, I get this automatic indentation, right? So this is very important because in Python, we don't have any like end keyword. So we need to say, well, which block of code is inside this function or relates to this function that we want to define. And the way that Python understands this is using this indentation, right? So that's something very important to consider here, that everything that is supposed to be inside this function needs to be indented, as you can see here. And in this case, we start with a docstring, just some general information about this function. We perform some operation, add x and y, and assign the value to result. And at the end, we return result, right? So if I define this, and remember, right now, we are not really doing any sort of anything or any operations. We just define the way that this function is supposed to behave. And later on, when in the next cell, I'm saying that call this function, pass these input arguments, and save the result in any name you want. Here, I call it my result. And now we print, you can see that we get 5. So that's how we define it. And then we can use that functions. Remember that usually we have to follow some naming conventions. And similar to naming conventions for variables, it is recommended to use lowercase letters for function names. And also, you can use underscore when you need to use multiple words. That's something completely legal or something that you can do. The other thing which is very important is about the type of docstring, right? So choosing the suitable type of docstring really depends on your personal preference and the level of information that you want to provide. So you can either use like a one-line docstring, right, which is only one line, or something which is definitely better and I recommend you to use is multi-line docstring. So the nice thing is that when you're using these triple double codes, you can use multiple lines and they're all considered as just text or comments, so they're not going to cause any issues with your Python code. And in this case, you will have one line or one paragraph where you explain a detailed or provide a detailed description of the function. Then you have another section where you have args or input arguments. Here you explain what input arguments this function accepts and then returns, so what this function is supposed to produce. And even you can provide an example, right? Like, how can I use this function that I just defined? So these are very helpful, especially if you want to uh, ensure that other people can use your code conveniently, so they can read your documentation here and also know exactly how they can run your code. So this is a really good practice for programming. Something to keep in mind is that in Python, a function can return more than one value. And the way that it works is that the function returns a tuple, right? So remember when we talk about packing and unpacking using tuples in the data structure lecture? So if you assign multiple values to an object, Python will create a tuple. And this is, you can see that something that happens here. For example, we have this function and I call this calculate rectangle properties. So this function accepts length and width of a rectangle. And here you can see that we use the multi-line docstring. So we have these two arguments. And then in the case of what this function produces, we create a tuple containing the area and perimeter, right? So the area of a rectangle is easy, is length times width, and then the perimeter is 2 times length plus width, right? So you calculate these two values, and then you just say, I want to return area and perimeter. So remember that now because you're assigning two values to one object at the end, this will be converted to a tuple, right? So to show you how this works, let's run this cell to just define the function. Right now, we are not really performing these operations. This is just the blueprint or design of this function. Now, next, we are going to give the length and width values and provide these input arguments to this function. And we call the output result, right? And remember, result is a tuple. So if you want, you can unpack that, right? We know that the first element should be area, the other one perimeter. And then we can use these print arguments to print them. And as we expect, the area is 5 times 3, and perimeter is 2 times 5 plus 3, which is 2 times 8, 16. And just to show you, if I look at this result, you can see that the type of this result is a tuple, right? Because we return two values. So in this case, we actually get a tuple. And obviously with tuples, we can unpack them whenever we want. The other feature when working with Python functions is that you can provide default values for some of the function parameters or input arguments and making those optional when calling the function. You have already seen this. For example, when we want to do a slicing in Python, for example, for Python list, we know that we have the structure of a start, colon, and colon, a step. And we said that if we don't provide the step parameter, the default value is 1, right? So this means that when that operation was defined, somebody said that, well, the default value for a step is 1. But how can we define these default values? The way that we can do this is that inside these parentheses where you provide your input arguments, you can provide the default value. So this means that the default value for width is 1. If you provide another value, that will override this value. But if you do not provide width, it's going to be 1. And the same thing with height. So in this case, for this function, this means that length is the one that is mandatory, and width and height, they're both optional, right? And it's always a good idea to include this information in your Docker string to make sure that the other people that they want to use your code are aware of this. And in this case, we want to calculate the volume of a rectangular prism. And in this case, it's just length times width times height. And in this case, you can see that for the length parameter, we use the value of 4, right? And in the first case, we are not providing any values for width and height. So by default, they are 1s. And this means that the volume should be 4. But in the second case, right, we are using these non-default values of 2 and 3 for width and height respectively. And if I run this, so you can see that with default values, we get 4, and with custom values or dimensions, we get 24. Okay, so now that we learned about default values in Python, let's dive a little bit deeper into this idea of what variables functions have access to. And this is what is known as the scope of a variable. So what is the scope of a variable? It refers to the region of the code where the variable is accessible. And we have local variables and global variables. So as the name suggests, for local variables, they are defined within a function and are only accessible within that function. Okay, so it's just inside the function and not outside of it. But global variables, they are defined outside of any function, and it can be accessed throughout the entire script. To just explain this, here we start by assigning value 1 to this variable out. And because this is outside this function, this means that from now on, whenever we use out or call or print out, its value is 1, right? So this is a global variable. However, if you look at this function, right, so we want to add two numbers, a and b. So we add a and b together, and then we assign the result to this variable out, and then we want to return this. So this out that you can see here inside this function, this is a local variable. And Python is very smart. It is not going to use the same place in the memory for these two variables. So they do not interfere with each other. So this means that even if I have, like, let's say a and b, one to be 1 and the other one 2, so 1 plus 2 would be 3. That value 3, which will be assigned to the out inside this function, will not impact the value of out in the outer part of this function, right? Because they use separate memory blocks. To just prove that that's the case, what we are doing here, we are using this print statement inside the function, right? So this means that now when I call add numbers 1 and 2 here, first, we're going to this function, and we're going to print this statement, whatever the value of out is. And once we are done with this function, we are going to, again, print the value of out, right? But remember, this last print that we have here is going to print the global value of out, not the local one. So if I run this cell, you can see that the first print, which is the one inside the function, gives me the value of 3, and that's what we expect because you're adding 1 and 2, so it's 3, and the 3 was assigned to the variable out inside the function, so that's the local variable. However, for the second print statement that we have, you can see that this is the global value of out, and that's 1. And this is something, again, possible because Python is not going to share the same place in the memory for both of these variables, even though they have technically the same name in this case. So we have explained this here in text because this is something very important. And remember, this is mainly because the memory block is distinct from the memory block where variables outside the functions are stored, right? So when you define a function, it's going to use a distinct or separate memory block, so it does not interfere with global variables. And just again, to prove that this idea of local and global variables, right? So we call this function in this line where we said d equals add numbers 1 and 2. So we went through this function once. So you may expect that, well, then a should be defined, right? Because I assigned the value 1 to a. But remember, this a is local variable. So if I just, in general, like outside this function, put print a, I get this error message that a is not defined, right? And it is true because a is only defined within this function that I'm highlighting, right? So it's just a local variable, it's not a global variable, and you cannot use it as a global variable. So that's something very important about the scope of a variable. Okay, so now let's talk about nested functions. So nested functions in Python refer to the concept of defining one function inside another one. And in this case, you can think of having an outer function and an inner function. And the nice thing is that the inner function has access to the variables and the scope of the outer function, right? So you can notice the hierarchy here. And this is very helpful, especially for functionality and maintaining a modular structure. So let us, for example, here define a function which is called outer function so that we know it's actually an outer function. And now we have two inner functions. This function that finds the squared value and the other one that raises x to the power of 3. So in this case, I do not need to explicitly pass this x to these inner functions because x is the global variable inside this outer function. And you can see that in this case, I just call a square with parentheses, but nothing inside it. And I assign the result to result underscore a square. And the same thing with cube, result underscore cube. And then I'm returning these two, right? So in this case, it is just enough to give this value of 4 to the outer function. And because this x here, which is now 4, is global for these two inner functions, so you can see that we are able to calculate the square value of 4, which is 16, and also the cubic value of 4, which is 64. But what do really we mean by maintaining a modular structure? This is something very important, especially when you focus on more advanced programming topics. So let's say we have a set of three-dimensional data points. So it's a 3D space, you have X, Y, Z coordinates, all right? And let's say you want to write a function that calculates the square differences between each of every two coordinates, right? So X and Y, X and Z, Y and Z, right? So one way to do this is just saying that in order to find the square difference between X and Y, find X minus Y, raise it to the power of 2, right? And similarly for X and Z, subtract X and Z and raise it to the power of 2. And the same thing with Y and Z, find Y minus Z squared. But as you can see, this is really boring and really waste of resources, right? To repeat this again and again, right? So one thing you can do, you can define this inner function, which is called find a square difference. And this accepts two input arguments, subtract them, and raise it to the power of 2. Because this is an inner function, and x and y are local variables inside that function. So this means that I only need to define this operation once, and later on, I can call this function that we have here 3 times. One time I pass x and y, the other time x and z, and then the other time y and z. And again, this is something we can do because the x and y that we have inside this inner function will not interfere with global variables that we have in our outer function, right? So there's no overlap or interference here. And also this gives you a lot of functionality and modularity here, which is really helpful. So you can see that once we define this function, let's say you have a data point, 3 coordinates, 2, 4, 7, and you call your function. And in this case, you can see that we get this result. Recall that this is a tuple because of these parentheses that we have. And so the first element should be 2 minus 4, which is negative 2 raised to the power of 2, which is 4. And then 2 minus 7, which is 5 or negative 5, and raised to the power of 2, which is 25. And then 4 minus 7, which is negative 3, and raised to the power of 2, which is 9. So that's, you can see how this works. Now let's talk about lambda functions. So lambda functions, as we said, are anonymous functions, and they're very interesting, actually. So defining a function in the conventional way, sometimes it's not optimal because we may have like a relatively simple function, which is like 1 or 2 lines, typically just 1 line. And in such cases, you just want to perform that operation and you don't want to assign a unique name to that function. And you can do this using the lambda keyword instead of the def or def. So the way that this works is very simple. Use the lambda keyword, use all your input arguments, colon, and some expression. So this is what you're trying to do with those input arguments. To just explain this and how simple it is, so let's say you define a function add, it accepts 2 input arguments and returns the sum of the 2. So this is something obviously possible because we do not have to assign x plus y to another variable and then return the other variable. You can just write this in 1 line. So in this case, we can have this equivalent lambda function, which we use lambda keyword. X and y are the input arguments, colon, and this is what we're supposed to do with those 2 input arguments, which in this case means that we want to add them. And in this case, if we run the 2 functions or call the 2 functions and compare them, you see as expected, we get the same result. However, something to keep in mind is that these lambda functions can be extremely helpful for solving a lot of scientific computing and data science problems. One of them is, for example, the problem of root finding, right? Meaning that if, let's say, we have this quadratic function, f of x, ax squared plus bx plus c, right? So a and b and c are constants. So these are the constants you have in your polynomial function. And you want to find the root of this function, meaning that for what values of x, we get f of x equals 0. So one way to solve this problem is to use a library called scipy, which is like NumPy and other libraries in Python, but it's specifically designed for some of these like scientific computing problems. And inside this library, we have something called fsolve. And what this does, you can go through this documentation page and learn more about it, but it returns the roots of nonlinear equations defined by some function of x equals 0. And the way that this works, it needs a starting point or estimate. So you provide an initial guess, and this fsolve here is going to try to improve that initial guess and give you a solution in a sense that some x value such that f of x equals 0. So how this works with lambda function, so in this case, you can use lambda function to define this polynomial function rather than just calling it some name and use the def keyword. You can just use a lambda function. To show you this, let's say we import numpy as np, and we said that we need to use scipy. So one way to use this is saying that from scipy that optimize import this f-solve. So this is what we just talked about, finding the roots of nonlinear equations. So in this case, let's say the polynomial that you have is x squared minus 4, meaning that if I compare this with what we have here, a is here in this case is 1, b is 0 because there's no x, and c is -4, right? So in this case, we provide a, b, and c using this Python list, right? 1, 0, -4. And then in order to define the polynomial function, we just use the lambda keyword. So we say lambda of x, so x is your input, is the first element of this list, which is the a here, which is 1, times x squared, plus the next element in this list times x, plus the third element that we have, right? So these are the a, b, and c. So it's ax squared plus bx plus c. And also you need some initial guess. So let's say, in this case, we think 5 is a good initial estimate. And then what you do, use this f-solve. And the first thing is that you have to provide the function that defines, in this case, your polynomial. And we are using this lambda function that we have. And then the initial guess, and this will do the magic and will tell you the root of this polynomial, which is 2, and it is correct, right? Because if I substitute 2 in this polynomial, I get 2 squared minus 4, which is 4 minus 4, and that is actually equals 0. So you can see that we get the correct root of this polynomial. So something I think would be fun to do is to use different initial guesses and see whether you can find the other root of this polynomial, right? Because note that if x equals -2, then you get -2 squared, which is 4, and then 4 minus 4 is 0. So see if you can change this 5 here and find the other root of this polynomial. And now we have the homework problems for this lecture. Something to keep in mind is that for this homework problem that we have, make sure to use appropriate docstrings. I do prefer multi-line docstrings where you provide some details, what are the input arguments, what are the output parameters, and you explain all of those in the docstring. And then we have really interesting problems where you work with NumPy arrays and you also define functions that they operate on them, and also functions that operate on Python list, etc. And also you get to use a few more built-in Python functions such as sorted and filter. So the idea here is to build on what we have learned in the lectures and expand our knowledge. I hope you find this video helpful, and please let me know if you have any questions. Hello everyone, in today's video we will delve into the critical concept of branching statements, specifically if, elif, and else, which serve as the cornerstone of decision-making in computer programming. These constructs enable programmers to direct the flow of execution based on conditional evaluations, allowing for dynamic responses to varying inputs. This understanding is essential not only for developing efficient and responsive software, but also for fostering a deeper comprehension of algorithmic thinking. Okay, so now let's get started with this Jupyter notebook. So the most important thing that we cover in this video is if-else statement. A branching statement, also known as an if-else statement, is a code construct used for conditional execution. It allows you to execute blocks of code only if certain conditions are met. And for doing this, we need to use logical conditions. Remember that logical expressions evaluate to either true or false. And that's what we use for conditions in an if-else statement. So in the simplest case, when you want to use an if statement, you use this if for if, and you put the logical expression here. So this is the one that either is true or false. Do not forget the colon here. That's extremely important. And then here, if you're using Jupyter Notebook, after this colon, if you press enter, you're going to see that you get this indentation. So this is what is very important because we do not use any end and at the end of this if statement. So you can see this if does not have any end later on. And therefore, this indentation is what tells Python what is included inside this if statement, right? That is why we need to use indentation. And here is where you put your code block, right? So here I just put this comment, but this can be multiple lines. You put, everything that you want to be executed if this condition here is true. And if the condition is false, obviously this means that this block of code will not be executed. Okay, so now let's talk about something which is a little bit more complicated, and that's when we can use if-else statement. So similar to before, you're going to use this if and some logical expression. So if this logical expression is true, like what we did before, you're going to run everything that is inside this code block identified by this indentation here, right? You can see the space that we have here from the beginning of this if on the previous line. And then the nice thing about here is that you can use now this else. And remember, you need to, again, use your colon here. And now you have a second block of code. So this means that if that logical expression that we had originally is false, now we're going to run whatever is considered here under this else statement, right? So in this case, whether it's true or false, the logical expression that we have, we're going to run code block 1 or code block 2. But as you can imagine, in some cases, you might have even more complex rules, right? It may not be just as simple as one logical expression that we have to evaluate to be true or false. And in that case, we can use this if statement at the beginning, like we did before, and some logical expression and some block of code. But also you can use elif or elif, and now you can use another logical expression. And again, if this is true, you're going to run this block of code. Although I have to be very careful because once you start with multiple elifs, right, we can see here, the way that Python will interpret this is that the first, and again, I emphasize this, the first true condition that you encounter here determines the code block to be executed. And then the subsequent conditions are not going to be evaluated. So what does this mean? It means that if logical expression P is true, then you're going to execute code block 1. And let's say logical expression P is false, right? And then you move to the next statement here, and then you check this logical expression Q. And if this is true, you're going to run code block 2, but you're not even going to check whether the other expressions that we have later on are true or false. So meaning that you are going to exit this if statement that you have. So that's like the key thing here. And I'm going to emphasize it again, that the first true condition encountered determines the code block to be executed, right? So that's something that you really need to remember here. So from now on, we're going to just look at a few examples to kind of like get some practice, experiment with code. And I encourage you to do the same thing when you're working with these Jupyter notebooks. So let's say we want to create a function called device status, right? Let's say this is for an HVAC system. You have a desired temperature and you have the current temperature, right? So this is the current temperature that we have. This is the desired temperature. And you want to have a function, and we learned about function in the previous lecture, to return a string. If the temperature is less than 5 degrees below the desired temperature, then we should print heat because we have to, that's what we need to do. And then if the temperature is more than 5 degrees above the desired temperature, then we should return cool. right? So these are the two main functionalities that we need. And also, if we are within plus minus 5 degrees, then it should return off because we don't need to turn on the HVAC system. Okay, so let's run this and see how that works, right? So we have this function def device status temperature. So this is the current temperature, desired temperature with the default value of 65. You can override this if you want, but this means that we don't have to provide this desired temperature later on. Do not forget the doc string or documentation string. That's important to know what this function is for. So this is the first, thing that we want to write here for if statement, right? So we're saying that if the temperature is below the desired -5, then return heat. And something I want to show you, I'm just going to press enter here, and you can see that I already get this indentation, right? So this is what we are talking about, this space that we have here, right? And you don't have to be too worried about it, because if, as I said, put enter here, you can see that we go exactly where we are supposed to be. Okay, so we are saying that if this logical expression is true, then return, or in this case, we have a variable result, and this result, we're going to assign heat to that, right? And then we have this elif, right, that if temperature is above desired temperature +5, then the variable result should be equal to cool. So that's what we use for assignment. And else, meaning that if we are somewhere between plus minus 5 degrees, the result should be off, right? I remember when you have a function, right, you always want to return something, especially in this case, since you want to print the result, right, later on. So you're going to see now we can return the result, right? But the value of this result really depends on this if statement that we have here, right? So if the temperature is below something, then it's heat. If other condition is true, then it's cool. And if none of these two conditions are true, then we return or produce off. And you can see that here. Now, if I put temperature to be 40, this is obviously way below 65, right? So when I run this, you get heat, right? And if I put out there like extreme value, let's say it's a summer day, 80 degrees, you see it's now cool. Also, we can try, for example, to put 67 degrees, right? This is very close to 65. As you expect, this condition is not true. This one is not true. So we end up with the else, what we have in the else part of this branching statement, and we get off, right? So please feel free to experiment with this code, and I'm going to put this back to 40. To get the same result as we had originally. So in that case, it's heat. So in the next cell, what we want to really talk about was this very important information that we had, that if you have this if, elif, the first true condition encountered is the one that really determines which code block needs to be run, right? So let's say we have this function, which I call a check condition. We're going to see whether the value is less than 0. Then we're going to assign negative to result. And this operator here is the remainder after division. So if this value that we provided divided by 2, the remainder is equal to 0. That's why we use equal, then it's an even number. If the remainder by after division by 3 is 0, then it's multiple of 3. And else, we just say other because it's none of these 3 things that we have originally. Okay. So let's start, right? So I can give something negative here, like -3, right? And you can see that we get negative. What this means is that because this is true here, we're gonna assign negative to result, and that's it. We don't have to go and check other logical expressions that we have here, right? And now let's say I use 4, right? So then this one is not true. This one is true because the remainder of the division by 2 is obviously 0, right? But here it becomes tricky. I want you to think about that, right? So what happens if you use 6, right? So let's run this and see what we get, and then we can explain it. So you can see that you again get even, Why is that? So again, we go through all these conditions. So this is false. This is true because if I divide 6 by 2, the remainder is 0, right? So definitely, that's why we get even. But you can see even here that because this condition is true, this one, we are not gonna run this next or evaluate this next logical expression. And because of that, we are not gonna get multiple of 3, right? Because we never get to this point. Once we get to this elif and the expression is true, we run this block of code, which is result equals even. And after that, we're gonna exit this function. So we never get really to the rest of these statements that we have here. So we can do many cool things with this type of like if-else statements. So let's say, you want to write this like, function for a data science project. And one of the first things you want to know is that once you are given a variable, whether it's the right type or not, right? And then Python actually has a built-in function to do this thing, similar to the type function that we had before. There is this function which is called isInstance, and the syntax for that is very simple. So you provide an object, you provide the type, and this will tell you whether this object is this type or not. So that's exactly the logical expression that we talk about it, right? So it's either true or false, whether this object is of that type or not. So let's say we have this function process variable, and we have this Docker string here, right? So you have a variable which can be any type, and you want to see whether this what returns is that whether this variable is of one of these types that we have here, right? So we're saying if isInstance variable, so this is the input to this function, is int, then the result is variable is an integer. If this isInstance variable and a string is true, then the variable is a string. And we want to also see whether this variable is a list or not, right? So we want to check these 3 types, integer, string, list. And if it's not one of these, then we want to return that this variable has an unknown type, right? So if I run this cell to define this function, so now you can see that you can use this, right? So I'm giving multiple values or inputs to this function, 42, hello, a list, and also something that is, we can run this cell here, but you can see that this is actually a float, right? So it's not an integer, it's not a string. So let's see what happens here, right? So you can see that, yeah, for the first one, we get variable is an integer. So that's for 42. Then we get a string for hello. Then obviously this one is a list and you get a list. And this one, 3.14 is a float, which means that it's not a integer, it's not a string, it's not a list, right? So that's why we get this. Obviously, if you want, here you can have another elif and say isInstance variable and float, and print the type of that variable. But this is what we have here. We didn't want to make this too complicated. Okay, so now we can do even a lot more like cool things for, especially like in the context of like data science, right? So let's say you have an array, a 2D NumPy array. I have to be rigorous about it. And so here you want to find the sums of rows or columns depending on the given input. So meaning that you give the array, and also you can provide the access, whether it's access, rows or columns, right? So that's how you want to write this function, that this access can be rows or columns to show you that you want to find the sums across rows or columns. And also you want to make sure that your function is, in some ways bulletproof. So in the sense that if the input array doesn't have a rank of 2, meaning that it's 1D or 3D or something that is not ranked 2, you want to return none, right? So we had this none before, right? If you remember, which represents the absence of the value, meaning that we really don't want to return any value. So here we import NumPy as NP. We define our function. I'll call it sum rows columns. So you can give it any name you want. And as we said, we have 2 inputs, right? Array and access. That's the really nice thing about Docker string. You can really explain what these things are. So as you can see, the array should be a NumPy ND array, which is a 2D array ideally. And if not, we're going to return none. And then this access here, before you saw that in the NumPy lecture, we use 0, 1, but here we want to use a string, whether rows or columns, to calculate the sum along the corresponding axis, which is rows or columns. And then you return either NumPy array if it's a 2D array originally given to you, or none if the original array is not 2D. So the way that you do this, right, is that you're going to start with the most important thing. Is this array 2D or not, right? So you can use the ndim method to count the number of axes. And if that's not equal to 2, you want to return none. And that's important with knowing how functions work. So when you return something inside a function, means that everything is done. You're leaving that function, right? So meaning that we are not even going to check the rest of whatever is after that, return a statement that we have here. So that's, you can see, if for whatever reason this array is not does not have ndim equals 2, then we return none, and there's nothing really to do after that. However, if ndim is equal to 2, right? So that's the only way you can get after this if statement. If axis equals rows, remember, based on the definition of axis for NumPy arrays, so now you can use np.sum and set axis equals to 1. So this means that now you're going to have these horizontal axis that you use, which means that it's sum across rows, right? And if the axis is columns, then you're going to sum this array across axis 0, which are the vertical axis, which corresponds to columns. And if, like, let's say somebody gives you access where, it's not rows or columns, it's something else, we want to also be like, provide another else statement here to say that access is invalid. So if I run this, we're creating this 2D array, right? Very simple, 1, 2, 3 through 9. The first time I'm gonna use axis equals rows, axis equals columns, and axis equals something else. I call it invalid. So let's print the results of all of these. You can see for the first one, which is the sum across rows, right? So you get 1, 2, 3, which is 6. 4, 5, 9, 4, 5, 6, which is 9 plus 6, 15, and so on. So that the result makes sense, right? The same thing with some columns, right? So the first column is 1, 4, 7, and if we add all of them, we get 12. And in the last case, we get this axis is invalid. So you can see that this if a statement that we have here, it's working as expected. And in this case, if we, let's say, provide a 1D array, right? This is a 1D array, and give it to this function, even though access is valid, is rows, you can see that if I run this, I get here printed none, right? Because that's what the function is supposed to return if you get, like, let's say, a 1D array, right? So definitely the ndim for this is not equal to 2, and we can't even check it, right? So if I just use ndim, you can see this is a 1D array, right? It's not 2D. So therefore, once we go through here, we see that we get here 1, and 1 is not equal to 2. So this is true. And since this is true, we return none, right? And that's exactly what happens here. We return none. Okay, the other thing that is very important to know, especially again in the context of being able to write efficient code in data science and scientific computing, is this idea of ternary operator. So what is the idea? So sometimes you have this if-else statement, and you want to write this in one line rather than having these multiple lines of code. So in this case, one thing you can do, I like to read it like in this form, that if some condition is true, right? So this is the one in the middle, then execute whatever it's here, this expression. And if it's not true, means else, then run this part, right? So just to kind of again repeat this, you have a condition in the middle. If this condition is true, then you're going to run whatever is on this left side, right? And then you put the else here. And if this condition is false, then you're gonna run it's on the right side, right? So it's a very helpful thing. So let's say you have like a variable x, which assigned the value of 10. You want to say that, well, if the remainder after division by 2 is 0, right? So this is our condition, then the result is even, else is odd, right? And you can see that it works as expected. So this is really nice, right? And writing if this condition, colon, then true even, and else, colon, then other line odd, right? So that's like really the nice thing about this. And here I show you also one example of this. There's this like module called sys. Especially this sys has a like this sys.version, which gives you a string containing the Python version that you use. So why is this important? Let's say because we do have like Python version 2 and 3. I think these days most people are using Python version 3, but you want to make sure that like, nobody's using Python version 2 in your sort of like code, right? So you import sys, and then you look at this sys.version. I'm going to print it to see what's inside it. So this is what's inside sys.version, this thing. So you can see the first like element here, or if I use index 0, it's this 3, right? So we don't really right now care about these other values here. I just want to see whether this is 2 point something or 3 point something, right? And for doing that, you can look at the first element at index 0, and you can see that it's 3. Right. And based on this, you want to see whether the code that you have is machine learning compatible or not, because if it's version 2, it's not, right? So you're saying that if this sys.version, right, the first element, and you can also convert this to integer because what you get before is a string. If this, when we convert it to integer, is greater than 2, then this ML compatible variable is true, and else it's false, right? So this ML compatible can take on 2 values, true or false. And this value depends on whether this like system version that you have here is 2 or 3, right? So if it's 3, which means that it's greater than 2. So if this condition is true, then we return true, else we return false. And this is very helpful because then you can add this nice like print a statement somewhere in your code and say that, well, machine learning compatibility, right? So this part is always fixed, but you want to say whether it's true or false. And in order to do that, you can just use this ternary thing that we have here. So you can see that if this ML compatible, the one that we found before, is true, you're going to print compatible. And if it's else, which means that it's false, you're gonna print not compatible. So in this way, you really don't need to, use multiple lines of code to do this. In just one line, you just check whether this variable is, true or not, which really depends on the first element of this sys.version, right? Whether that's 2 or 3, right? As we can see here. Hello, everyone. In this video, we talk about iteration in Python programming. Iteration is a fundamental concept in programming that allows you to repeatedly execute a block of code. And there are several ways to implement iteration. The most popular one is using a for loop, but there are other options too, such as while loops and comprehensions. Let's get started with for loops. So the syntax for loops is very simple. You have to use this for, and then the name of the variable that you want. So that's why I like to use here variable, but obviously this is optional. You can say for item, for I, or any other name that you want. So you can just choose the name of the variable that you want. In, and then after this in, you need to have an iterable. So what is an iterable? Iterable is a Python object which is capable of returning its elements or members one at a time. So this means that now you can iterate over these elements using a for loop. Examples of these iterables include Python lists, tuples, strings, We are familiar with these when we talk about Python data structures. It can also be a NumPy array. So there are many different forms of iterables. And so the way it works, you say for some variable in this iterable, or let's say for now a Python list, I want to run this piece of code, right? And very similar to if statements, the way this works is that you use colon, and after that, you will need this indentation or these spaces to show that this block of code falls within this for loop, right? So that's how we know what is included inside this for loop using this indentation. And I'm going to talk about this when we go through the code cells in a few moments. But one thing that we can also talk about here is that you may wonder how this works, this idea of iterating over elements, right? Because we need to somehow keep track of what elements we have already observed and what is the next element to retrieve from that iterable. And in order to do this, the way that Python works, we need to have an iterator. And you shouldn't confuse iterator with iterable. They're two different things. What iterator is like an object which keeps track of the current state of the iteration, meaning that what elements have been retrieved and what is the next element to be retrieved. And for that, we can use the next function or method. We don't really need to use iterators very much in this course, but just to show you how this works, let's look at this Python list, which is obviously an iterable because we can iterate over its elements, as we just discussed. And you can use the iter method or function to create an iterator out of this object, right? And now we use this next method that we just discussed about, right? So far we have not retrieved anything from this Python list here. So if I run this cell, as you expect, you should get 1, right? Because that's the first element that we have there. But now this iterator knows that you have retrieved the first element. So now when you use next, you're going to have the next element, right? And we can see that that's what we get here if we run this cell. And similarly here, if I run this one more time, we get 3. If we do this one more time, and if we do this one more time, right? So that's why this iterator is very important to keep track of what we have retrieved and what is the next element to be retrieved. And if for whatever reason, you want to retrieve another element from this list, you can see that you get an error message which says stop iteration. And the reason for this is very clear because this list has only 5 elements. So once you get to this element, there is no next element, right? You expect that you should get an error message to tell you that, well, there's nothing else to be retrieved at this time, right? And that's what exactly this thing is. And as I said, we don't really need to use iterators in this course. What we really want to learn to use is for loop, right? So we say for some name here, call it variable. In this iterable object, remember, iterable object is this list that we have here, this line. So you don't need at all to use iter or next. So you just have the list, and then you're going to print each variable. Ideally, you want to do something more sophisticated with these variables, but right now we want to keep this as simple as possible to understand how for loops work. And for that reason, we just print this variable that we'll retrieve from this list. And as I said, we need to make sure that we always use this colon, otherwise we will get an error message. And once you do this, if you press enter, you can see that we come to this sort of like indented line, right? So there are 4 spaces here, which is the standard indentation. And you can see that anything that is this indentation is part of this for loop, right? So right now, this is not part of for loop because it doesn't have that indentation, but you can, again, just use enter And you can see that now we have these 4 spaces. And if I run this, we get 1, 2, 3, 4, 5. As we said, this is arbitrary. I can just call this item instead of variable. And you can see that we get exactly the same result. So this is just a name that we assign to each element that we retrieve. And you can decide any name that you want. Obviously, we discussed this before. You cannot start a variable name by a digit or something like that, by a number. So these are things that we have to follow. But other than that, you can choose any name that you want. There are also other types of iterables. One of the, useful ones is NumPy arrays. And here we are using np.arrange 1, 6, which means that we want to iterate from 1 up to 6. So 6 is not included and is actually excluded. So you can see that if I run this, I get 1 through 5. If for whatever reason you want to include 6 here, then you need to increase this to be 7, then you get 6, right? So that's why to just remember always the stopping point is excluded. Okay, so now let's exercise a bit more. Let's say we want to find the factorial of a positive integer. So what is a factorial? Factorial is the product of all integers up to n. So meaning that if you want to find factorial of 3, then you have to multiply 1 by 2, and then the result of that by 3, which means that you get 6. If you want to find factorial of 4, then you have to multiply 1 by 2, and then by 3, and then by 4, right? And in this case, it's up to n and including n, right? And therefore, factorial of 4 is 2 times 3, which is 6. 6 times 4 is 24. But how can we implement this using a for loop in Python, right? So let's say you want to write a Python function that can calculate factorial for any positive integer n. So you can use the def keyword here. Again, similar to for loops, if statements, you need to use colon. We need to use the indentation to show that this is part of this def block or def block. You need to use docstring. It's always a good practice to explain what this function is, what input arguments we have, what it returns. In this case, it's simple, but it's still a good idea to include that. It's always a good idea to have safety checks. If for whatever reason you're given a negative integer, then you shouldn't even try to find the factorial, right? So in that case, you can use this if statement and return none, which means that there's no result, right? None means the absence of a value. And remember, once you get to return, if this statement is true, then you are exiting this function, right? So you're returning none, and you're not going to go through the rest of this code. But if n is greater than 0, then you have to start finding these factorial. So remember, if you have, let's say, factorial of 3, 4, 5, 10, you have to always start from 1, right? And 1 times 1 is basically 1. So that's why we initialize this variable result to be 1. And then we include this for loop to go through sequence of numbers starting from 1 up to n, and n should be included. So that's why here we are using this range. So range in Python is very similar to np.arrange, right? The starting point is always included. The stopping point is excluded. So when we put n plus 1, means that we are going to go from 1 through n, which that's what we want to do. And what you do is that you're going to multiply the result that you already have by this I that you retrieve from this list, and you're going to update the result, right? So this is basically, I can show you what it means. So this means that you want to update result by multiplying result by I, right? So in this case, right, so first I result is 1, right? And so once you get to 2 here, right, like let's say 1, 2, then you multiply 1 and 2, and now the new result is 2, right? And then when you retrieve the next I, which is 3, then you multiply 3 by 2, which is 6. And similarly, now when you go to I equals 4, now you multiply 4 by 6, which is 24, right? That's exactly how factorial works. So in this case, we retrieve these elements one by one, multiply by the current result. So that's what you have on the right side. And then remember, equality here means assignment, right? That's what it means in programming. So this means that you're going to update this new value to the result and update it. And once you're done with this for loop, right? So this is what is done inside the for loop, you're going to return the result. Okay, so let's see how this works if you provide n equals 4, right? So in this case, you have to go through 1, 2, 3, 4. And we are, as you can see here, using this print statement, the factorial for n equals 4, because that's what we have assigned here, is 24. But I like the more compact form. So what I'm gonna do, I'm gonna remove this line. And I'm gonna remove the comment here. And I'm gonna use this simplified notation. And what this means is that you're gonna multiply result by I and update it. And I run this cell again to just show you we get the same result. And you can see that still the result is 24 as expected. So this is one real world example of using for loop for solving this mathematical problem. But you can also use for loops to iterate over elements of dictionaries. Remember, in Python dictionaries, we have key value pairs, right? And like, for example, like here, right? So the keys are these A, B, C, and the values are 1, 2, and 3. So what if we want to iterate over these key value pairs to do some computation? Now, here we are printing just these key value pairs, but in general, we may want to do more sophisticated operations. And as you can see, we have a method for dictionaries which is called items.items, and I forgot to run the previous cell. So before this, my dictionary was not even defined. So once we define it, actually, you can see that if you use .items, we know that what this does, it returns a list. And remember, a list is iterable, meaning that you can iterate over its elements. And each element is actually a tuple, where you have one key and the corresponding value. So this means that if you want to iterate over these key value pairs, what you can do, you can say for, and remember, because now we have these tuples, we actually have two items here, right? So that's why we here also need to use two items. Obviously, these names are arbitrary or optional, but I like to use key and value to remember, okay, the first one is key, the second one is value. In this dictionary.items, we want to print keys and print values. And this is, as you can see how it works. So remember, Python is smart enough to know that when you use this key value in dictionary.items, that the first one, which is key, corresponds to A, and the second one corresponds to the second element, right? So if for whatever reason you have a tuple with 3 elements, then you need to have 1 item, 2 item, and then the third item, right? So here we don't have it, and I'm gonna erase that, but that's something to always important to know, that if you get multiple elements, also you need multiple names so that way this for loop is going to work the way expected. The other thing which is very important when you're using any kind of iteration in Python or other programming languages is that sometimes you may need to stop the iteration sooner than expected, right? So you may have a for loop, you want to go through all the elements of a list, like what you have here. But let's say your goal is just to find the item with value 5 and then stop, because that's what you really care about, finding this item with value 5. So in that case, you can use the break keyword. So the break keyword is used to immediately exit or break out of the most immediate for loop that it contains, right? And I'm going to explain what we say here, the most immediate for loop, because you may have multiple for loops, but let's start with a simple case where you only have one for loop. So in this case, as we said, you can write this for loop and say for num in numbers, and numbers you can see is this list. If this num equals to 5, right now we are using this equal sign. So this means that we want to check to see whether the value of num is actually 5 or not. And if this condition is true, right, now we want to print that, oh, we found 5, and we want to leave this for loop. And after that, we don't want to go through the rest of the elements, right? So we're using break. So what this does, this break looks at this for loop and says that, well, because now I got to break, I have to stop this iteration that is defined through this for loop right now, right? And you can see that here. Otherwise, if we continue, we print the number that we have. So I want to add these to show you actually when we are stopping this for loop that we have here. And if I run this, so you can see that we start with the first value, which is 1. And obviously 1 is not equal to 5, right? So we are not going to go through any of these things here, right? Because this statement is not true. And we print num, which is 1. And then we go through 2, and it's still this if statement. We don't go inside it because this condition is not true, and we print that until we have num equals 5, right? Then we print this item, which is found 5, but we do not anymore print that num 5 in the next line because we have seen this break keyword here. And what this means is that we have to leave this for loop right now. So we don't get to actually print 5. You see there's like 1, 2, 3, 4. There is no 5. We just have this statement, and that's what is coming from this print statement that we have here. And I wanted to show that if you want to use something which is outside of this for loop that we have here, then it's very easy. You just have to remove the indentation and go back to the beginning of the line, right? So then regardless of whatever happens in this for loop, we always print this because this doesn't have anything to do with the for loop because it's not inside the for loop in a way that it doesn't have that indentation. But let's look at what happens if we use break keyword. If you have a nested loop, right? Meaning that if you have like 2 for loops, like what we have here. So here the goal is this. We have 2 numbers. Think of them as x and y. And we know that x is from 1 to 5 because 6 is not included. And y is also from 1 to 5, which is, because again, 6 is not included. And we want to find the combinations such that the sum of these two, these x and y, or here we call them I and j, is equal to 8, right? So we start with the outer for loop, right? That's what I call outer for loop, and I call this the inner for loop, right? So first we're gonna set I equals 1 using this outer for loop, and we're gonna now inside this outer for loop increase j from 1 through 5, right? So we know that if we add 1 and 1, we get 2, so that's not 8. Even if we add 1 and 5, we get 6, which is not 8. So there is no way we can have I equals 1, and then we have another value of j in this range where we get 8, right? What if I equals 2? In order for I equals 2 to get 8, the sum of the two, we need j equals 6, and that's not the case because this is excluded. So the first time is when I equals 3, right? So if I equals 3, then for j equals 5, which is inside this range, we get the sum of 2 is equal to 8, which means that we're going to go through this if statement. We're going to print the fact that we found a pair with this sum equals 8. And we're going to use this break. But remember, this break goes back and finds this for loop. And this is the iteration that we are going to stop. We are not going to stop the iteration for the outer for loop, right? So this means that now we can actually go from I equals 3 to I equals 4 and repeat the same process again, right? So we just have to stop this inner for loop. And if I run this, you will see that this is actually the case, right? Because we're going to find the first pair, which is 3 and 5. Obviously, the sum is 8. But then we're going to increase I to 4. There is another actually pair, which is I equals 4, j equals 4. And then there is also another pair where I equals 5 and j equals 3. And after that, we don't have any other pairs. So that's something important to know, that this break is not stopping both of these for loops. It's just stopping the closest or the innermost for loop, which is this one, which comes very handy in this case because you're able now to find all these pairs where the sum is 8. Okay, so this is for loops. Similarly, we can use while loops. The main difference between the two is that for while loops, we just have to put a condition, like very similar to when you use an if statement. And you're gonna run this block of code as long as the condition is true. So this is very helpful where the number of iterations is not known beforehand, right? If you know the number of iterations beforehand, you can just use a for loop and say np.arrange or range if you're using Python and provide the number of iterations that you need. But sometimes we want to continue something until something else happens, right? So that's when this while loop becomes very important with this syntax, right? So while some condition, again, indentation, and that's how we show what's included inside this while loop. So let's look at a real world example of this. Like, why should we use while loops? Let's say you want to solve this problem where you are looking to solve this problem where the goal is to find the smallest power of 2 that is greater than a given threshold, right? So let's say the threshold is 100, as you can see here, right? So if you remember the powers of 2, right? 2 to the power of 6 is 64, right? So it's smaller than the threshold. But 2 to the power of 7, right, is 2 times 64 is 128, which is just above 100. And then obviously you have 2 to the power of 8, which is 256, etc., right? But in this case, the solution should be 7, right? Because 7 is the smallest power of 2 that is greater than this threshold 100. So how can we solve this problem for any threshold that is provided? So you can always start with power of 2 to be 1. That's how we initialize this variable. And obviously, we need to keep track of the power of the 2 raised to this power, which is 1. So 2 to the 1 is equal to 2. So that's the current value. So now the condition that we have here for this while loop is that if this current value is less than or equal to threshold, let's do these 2 lines of code, right? Why? Because if the current value, meaning that 2 raised to the power of that number that we have there, is past the threshold, then we have to stop, right? Because we found the solution that we want. But if this current value is less than the threshold, then let's increase this power of 2 by 1, right? So remember, this is very similar to what we had before. So this line is equivalent to saying that we have power of 2 plus 1, right? So adding 1 to the power of 2 and then updating it, right? Because this equality sign is assignment operator in Python programming, right? So that's what this line is doing. But I like the more compact notation. So in this case, if current value is less than threshold, we're going to increase the power of 2 by 1. And then we're going to update the value of the current value, which is 2 raised to the power of this number that we have here. And now we're going to again check whether current value is less than threshold or not, right? So when power of 2 is equal to 6, right, then we get 2 raised to the power of 6, which is 64, right? And 64 is less than 100. And in that case, we're going to increase that power of 2 by 1, which means that now we get 7, and 2 to the power of 7 is 128. And this time, when we check, 128 is actually greater than 100. So this means that we have to stop, right? That's how while loop works. We're going to go iterate until some condition is met. And that's exactly the solution that we are looking for, right? So if I run this cell, you can see that now we stop at 7, and you can see that the smallest power of 2 that is greater than 100 is 2 to the 7, which is 128. If we want, we can change this threshold to be 60, right? In this case, let's run this cell again. So the smallest power of 2 greater than 60 is 2 to the power of 6, which is 64, right? And that really makes sense. So therefore, you can see that this code is actually working, right? You can obviously choose different thresholds, but it is working as expected. The other thing which is very important is the continue keyword, right? So we know already the break keyword, which means that a stop iteration, especially when you have a for loop or even a while loop. But the continue keyword is a little bit different in a sense that what it means is that you want to skip the rest of the code inside the loop for the current iteration and jump to the next iteration, right? So we don't want to fully stop the for loop or while loop that we have, but we want to go to the next iteration. So let's say that, we want to start from 0 and increase these values up to 10 and skip printing even numbers, just print odd numbers, right? So you're gonna increase I by 1. This means that you're gonna add 1 to the I and update it. And you're saying that if the remainder of dividing I by 2 is equal to 0, that means that it's an even number, then continue, which means that skip the rest of what's included inside this while loop, right? So you're not gonna print this. But if it's an odd number, right, then this statement here is not true, which means that you're not going to see this continue, right? So from this line, you go through that line, and so that way you can print that current number. And you can see that this is actually the case, right? So for odd numbers, 1, 3, 5, 7, 9, you're going to get to this print statement and actually print the current number. However, if you get an even number, this condition is true. You see the continue keyword, which means that we are going to ignore whatever the rest of this while loop is, right? So both of these keywords are very important, break and continue, and they have different implications. And just to show you the difference, what would happen if instead of this continue, we use break, right? So the way it works, we go back and find this for while loop, which is this while loop. In this case, this means that the first time you get this break, you have to stop iterating, and therefore there is no more next iterations, right? So in this case, you can see that we only get one print, right? Because we're going to increase I by 1 when we start from 0. So you get 1. And for the first case, obviously the remainder of dividing by 2 is not equal to 0. So we are not going to go through this if statement. So we can print this. But once I equals 2, then the remainder is 0. And we see the break here, which means that we have to stop iterating. We don't have any more future iterations. And as you can see, that's what this means. Finally, let's talk about list comprehensions, which is a very important topic. So sometimes, very similar to when we defined the lambda functions before, you do not want to write the whole for some item or variable in an iterable colon and then use the indentation and then define new variables and perform some operations. And you want to do this in a very simplified form because in some cases you want to, let's say, retrieve some items from a list, multiply them by 2 or square them and just store the result, right? So you want to perform something simple. And in order to do this, you can use list comprehension with this syntax that we have here, right? So you use for some item or any name that you want in this iterable. This is the expression that you have, meaning that, let's say, if you want to do some operations or perform something else on this item. And the cool thing is that you can also add an if statement too. So all in single line. And just to show you how you can use this to use this as a concise way of creating lists based on existing iterables or list. Let's say that you have this list of numbers 1 through 5. And what you're saying is that for each x in this list, raise them to the power of 2 and save the result in another list called squares, right? If we run this, you can see that we get 1, 4, 9, 16, and 25, right? Even we can add some conditions, right? So this is exactly what we had before. However, you can use an if statement and saying that if x, the remainder of dividing x by 2 is equal to 0, then perform these operations, right? So this means that we want to only square these elements if they are even numbers, right? Because that's what this if statement here is. So in this case, you only have 2 and 4, and these are the two numbers that are eligible. So now let's practice a little bit more. So let's look at the prime numbers, right? So what is a prime number? A prime number is a positive integer greater than 1 that has no positive divisors other than 1 and itself, right? For example, 5 is a prime number because you can divide 5 by 1 and 5, right? Or like, for example, 7 is a prime number because you can divide it by 1 and itself, which is 7, but 9 is not a prime number because you can divide 9 by 3, right? And then the remainder is 0, right? So that's how we define prime numbers. And let's say if we can use what we have learned about list comprehensions to find prime numbers up to some number, right? So first you need to define a function to check whether a number is prime or not, right? As you can see, we've put first an if statement and saying that if num is less than 2, then we return false, right? Because we know that the first prime number that we have is 2, right? And the way that we can check whether a number is prime or not is very simple, right? You have to consider all the integers up to that number, let's say n or num here, and see whether we get the remainder of the division to be 0 or not. If it's 0, then it's false because that's not a prime number. But if you check all the numbers up to n and you don't find any remainder to be 0, then it's a prime number. And in order to do this, you can write a for loop and go from 2 to exactly up to that number that we want to check. But actually, we can show that iterate from elements from 2 to the square root of that number, right? That's why I'm using num raised to the power of 0.5. We don't go through details of this because it's beyond the scope of this course. But if you want, you can also iterate through all the elements from 2 to exactly that number, but you can actually save a lot of computation by looking at the elements up to a square root of that number. And after that, it's very simple, right? So you're gonna just use this if statement and see whether the remainder of the division by I is 0 or not. If it is equal to 0, you have to return false because that number is not a prime number. And if you go through all these numbers and you don't return anything, meaning that there is no remainder which is exactly 0, then you're going to return true, meaning that yes, that's a prime number because I check everything and we don't have that remainder which is 0. And after that, in order to find the list of all prime numbers, you can use list comprehension, right? So you have this for loop, which is saying that for number in range of 2 to limit plus 1, because remember, if you want to include the limit, which is 20 here, we have to use this plus 1 to make sure that it's included. If this is prime num is true, meaning that it's a prime number, then return that. Otherwise, if it's false, we are not going to select that number. And if I run this cell, you can see that now we get all the prime numbers up to 20. We have 2, 3, 5, 7, 11, 13, 17, and 19. So this code works as expected. So that's something I would say is important to kind of practice and write it on your own. Try to replicate these ideas. It's a very nice exercise to show you how you can use for loops, if statements, and also list comprehensions. And just like list comprehensions, we can have dictionary comprehensions too. It's something that is less commonly used, but it's something important to know. So in this case, again, we have this dictionary with these keys and values, and you can use this for loop here, where you have key values in this dictionary dot items, right? So that's what you get the list of keys and values, and then you keep the key, but for the value, you define a lambda function. So this means that for whatever this input is, right, you want to multiply by 2 and then add 3, right? So if I run this, so you can see that now I get this new dictionary, although I don't really square elements of this, I just wanted to still call it a square dictionary. But you can see that the first value is 5, which is 2 times 1 plus 3, and then 2 times 2 plus 3, which is 7, and 2 times 3 plus 3, which we get 9. Okay, so now let's look at quickly at the homework for this lecture on iteration. The first one, we want to have a Python function. So in this case, you actually have to write a Python function using the def statement or keyword that adds elements of a given NumPy array with even indices using a for loop, right? So here, for example, we have a test case. Your code should work with any given 1D NumPy array. But in this case, we have this test case that you can use to make sure that your code is running. So remember, the first index is 0, the next one is 1, 2, and here you want to add all the elements with even indices, 0, 2, 4, 6, and so on. So very similar to what ideas that you have seen, you can use if statement and use the remainder or modulo operation to see whether you have an even or odd index. The next question, you want to define another function, which is called custom numpy max, to find the maximum or largest value in a 1D numpy array. And the goal here is obviously not to use the built-in numpy function. You have to define and write your own way of finding the maximum or largest value. And you can use this test case in this case that we have. And just to give you an idea, one way to look at this problem is that you can iterate through these elements, right? Because this lecture is about for loops, while loops, etc. So you can iterate through these elements and always store the value of the largest element that you have seen, right? So meaning that for the first case, you see -2, that's the largest value that you have seen, right? And then when you go to the next one, 17, you ask yourself, is 17 greater than -2? And if it's true, then update the variable which keeps track of the maximum value, right? So that's one way of thinking about finding the maximum value in a given list that you can implement in this case using a for. We have a similar problem for in the third problem. And in this case, we take a positive integer as input, and we want to return the sum of the squares of even numbers from 1 to n, right? So if n is 19, for example, then you want to find even numbers like 2, 4, 6, up to 19 that we have, and also square them and add them together, right? So you can use a for loop and possibly some if statements and store this value, which should be the sum of the squares of even numbers. Problem 4 is definitely an interesting problem where you have two 2D NumPy arrays, also known as matrices. One is m by p, and the other one is p by n. So obviously you can multiply these two matrices because the neighboring dimensions do match, meaning that p is equal to p. And if you do the multiplication, you get a matrix or 2D array of size m by n. So if you remember from the lecture on NumPy arrays, you can use np.matmul to solve this problem. This is already built in. But in this case, we want to write our own function. And this function, which we call myMatrixMultiplication A and B, is supposed to find the answer using a for loop. And also, it's better to say that using for loops, because you will see that you actually need 3 for loops to write this. So this is a really good practice. So what is happening here, I'll show you in the next slide. So in this case, we have 2D array or matrix A, which is m by p, and then we have B, which is p by n. And in order to do this matrix multiplication, we know that if we show the result by C, and if we want to find the value of the element at location with index I and j, so this is like one element that you have here. In order to do these, you actually have to go through the ith row of A. So you can see that we have actually p elements here, right? Because we have p columns. And then the jth column of B, the second array that we have. And we also have p elements here because we have p rows, right? So you can see that that's why these two numbers should match. And what you do is that you multiply the corresponding elements and sum all of them together. So we end up with a single number. So that's exactly this for loop or summation that you can see in this problem, where we have this AI case where I is the number, the index for the row, and k shows that we want to iterate over all these different elements that we have. And we multiply this by b, k, j, right? So these are the fixed I and j that we have, and this for loop or summation is over k. But this is not enough because remember, this only gives you one element that we have here, but you want to find all these elements across the rows of C and all the elements across the columns of C's. So you need 2 more for loops to iterate through all possible values of i's and j's. And therefore, you should be able to implement these using 3 for loops. So we have also here a test case that you can use to make sure that your code is running as expected. You can, as explained here, compare these or verify the correctness of your code using np.metrics multiplication, which is the built-in method. And then we also have another problem where the goal is that you are given a Python list, like what's given here in this test case, and you have some minimum for valid numbers and maximum. And the idea is that you may have some faulty readings or some extreme or invalid values. And you want to do data cleaning here, meaning that you want to exclude the elements that are not between this mean and max value. And therefore here the goal is to write a function which is called clean temperature data, where you provide this list and these two mean and max values, and you're supposed to iterate through these elements and figure out whether they satisfy this condition. And if they satisfy this condition, you're going to keep them. And finally, we have an interesting problem where you have to write another function where given a Python list, which is like a 1D array, as you can see here, you want to find the maximum number of consecutive elements that are above the given threshold, right? So meaning that here, for example, the threshold 5, you can see that 5, 7, there are two elements that are greater than 5. Although here, I think the way that we have defined this is be above the threshold. So this means that, okay. So for the last problem, we want to write a Python function, count consecutive above threshold, where given a 1D array or a Python list, as you can see here, find the maximum number of consecutive elements that are above the given threshold, right? So for example, you can see here 6, 8, and 10, right? They're all above the threshold of 5, and they're consecutive elements. So that's basically 3 numbers where we have consecutive elements above the threshold. So we want to count this number if we have given any sort of like Python list, right? How can we find the maximum number of consecutive elements in the list that are above the given threshold? And in this case, the goal is to use a while loop, as the problem says. So you can have a while loop to iterate through the elements of this list that we have, and then you have to keep track of the number of times that these consecutive elements that are above the threshold, right? And once you go below the threshold, then you have to start again from 0, right? Because in this case, let's say we start from the beginning of this list, we have 1, 3, 5, so they're all below the threshold because we want to have absolutely greater than the threshold. And we have 7, so that's 1. And then we go to 4. So this means that now, we have to stop counting from now. So that means that we have 1 element above the threshold. And then we have 3 consecutive elements above the threshold. So in this case, the answer should be 3. But we want to make sure that this code works for any Python list. In this video, we talk about object-oriented programming, or OOP. In Python, we have 2 programming approaches. The one that we have used so far is known as procedure-oriented programming, or POP. In this case, we emphasize a step-by-step execution of procedures. And this means that we usually have a set of functions that perform a specific tasks. But what is very important here to mention in procedural programming is that data and functions are treated as separate entities. This means that data structures are defined separately from the functions that operate on them. Functions are written to perform operations, and they can be called with specific pieces of data as input. To understand this, think of this as a library where you have books or data stored separately on shelves, and there are various actions or functions you can perform, like borrowing a book, returning a book, or searching for a book. In this case, actions themselves do not belong to any specific book, but can be performed on any book.
So that's the main advantage of procedure-oriented programming, or POP. On the other hand, for object-oriented programming, which is extremely important in machine learning and data science, we emphasize the organization of code into reusable and self-contained units called objects. And therefore, your program is a collection of interacting objects. And the main advantage here is that data and functions are encapsulated within objects. And in this context, we usually call data as attributes, and we call functions as methods. So this is something very important to remember, that when we talk about object-oriented programming, when we say methods, we actually mean functions. And for attributes, we mean data. Okay, so now with this very brief introduction, let's go and talk a little bit more about components of object-oriented programming. We have two main components. One is class and one is object. So what is a class? A class is a blueprint or template for creating objects. And in this case, you define attributes or data and methods or functions that objects of this class will have. So, right, this is the part that is very important because you encapsulate data and functions inside these objects that you're going to create in the future. And in fact, class acts as a user-defined data type. You have seen even this before when we check the type of integers in Python, you get also something called class integer. So that's exactly what this is about, right? So anything that we work with in Python has a class, which means that somebody has written this class that you can encapsulate attributes and methods. So now that we know what a class is, what is an object? An object is simply an instance of a class, right? So remember, class is the template. Like, think about that. You have a template for a Word document file, and now you can actually customize that or instantiate that, right, to send a letter to a very specific person, right? So that, very specific letter now becomes an object. And it possesses unique attributes and behaviors defined by the class, right? So let's start by defining a very simple class to understand better the concept of, attributes and methods and, these topics that we just discussed. One thing that is important is that for class names, it is better that each word to begin with a capital letter. This is what is known as the camel case, right? So for example, we said for functions, it's better to all be lowercase letters, but for class names, it is better to capitalize the first letter in each word. For example, you can have something called my class or car model if you want to write a class that applies to cars. But in this case, let's look at something even more interesting, right? So let's say you want to define a class named student, and this class is supposed to have some important attributes or data, such as a student ID and name, right? So these are two important pieces of information we need to record for each student. And also we want to have one method to just print this information, right? Remember, print is actually a function, right? Because you want to act on something and print. So that's why here we have two attributes and one method which will be printing this information. The most important thing when you write your own class is to know how to use constructor. So what does this mean? So the nice thing about constructor is that once you want to create an object using the class that you have, Python will execute or run this function you have here. It's obviously a function because it starts with def. That's how we define functions, without needing to explicitly call this function, right? So the way that this works, if you look at it, this function
has this underscore underscore init underscore underscore. And this tells us that this is a special function. So this is not just any function. This has a very special meaning in Python. And this means that once you have this in a class and you call that class to create an object, then this will be called in the background. And the way that it works is that the first argument should be something called self. I have to say that you don't have to necessarily use the name self, but this is a very good programming practice to use self. And what this does, because remember that right now you're creating a template, right? So you do not have instances of this class. So you have to have a mechanism to refer to this class later on, or this object of this class that you're creating. And in order to do this, you use this term self. And after that, you have your input arguments or attributes, which, as we said, there are two of them here, a student ID and name. So this means that once you use this constructor, you initialize this class with these two attributes. And as we said, self here refers to the instance of the class being created, right? Because we need to do this to make sure that we can refer to this, object that we're going to have in the future. So just to explain how this works, so you start with the class keyword, right? So that means that we want to define a class. You choose the name that you want. Here I use a student, or you can choose any other name. You can follow the camel case rule that we said. Very similar to when we use like if a statement, or even we define functions, you need to use the colon. And remember that here, if I press enter, you see that I have these 4 spaces, what is known as indentation in Python, right? So this means that anything that now has this indentation will be part of this class, right? So if you want to later on have something that is not part of this class, please do remember to remove this space, right? Meaning that you have to, for example, then, start from here and say print something, right? So that's how you know that you are exiting this class definition here. But let's back to where we were. So we defined the class, we used the colon, we used the indentation. And as we said, the first thing is that you need to have your constructor, right, for initialization of your, or instantiation of your class, it's better to say. And in this case, use the def for defining a function. And use this special function, is underscore underscore init underscore underscore. We use self as we said. And then from this point, you have your input arguments. Now we have to assign these arguments to this self. So we create these attributes self.studentID self.name. This equal here is the assignment operator, meaning that we want to assign a student ID to self.student ID and name to self.name, right? So this self, which is the object being created, now has these two attributes, a student ID and name. And remember, here you should not use parentheses, because parentheses are used to call methods or functions, and attributes, as we said, are essentially data or variables that store data within an object, and they don't require parentheses. So now that we have this constructor here, let's just add one method or function, something very simple to make sure that our definition of class here works. And we call this display info. And remember, now you have to pass this self, right? Because again, this self now should be passed as input to this function. And we just have two print statements, right? We use the f string that we said before. We say that a student ID is whatever is in this self.student ID, and name is what's included in self.name, right? So we retrieve the information from these two attributes. So we define the class, right? So this means that now we have the template for creating objects, but let's create objects, right? So I create an object called it's called a student1. That's the name of this object. That's the name of the class. And remember, because here in the constructor, we need these two pieces of information, we have to provide a student ID and also name. And once I create this, right, remember that now this object has these two attributes. And I can access these attributes using this dot notation, right? A student one dot a student ID, a student one dot name. And as you expect, you can see that we can retrieve this information, right? This is what we provided for this student. So we can always use this dot notation to access attributes, but sometimes it is nicer to have this in a little bit more readable format. So that's why we included that method called display info, right? And I can just now call this. Remember, this is a function. So that's why here you need parentheses, right? This is a method or function. And if I run this, you get exactly what we defined before, right? We said that you need to print a student ID and whatever the student ID is, name, and the name of that object, right? That's consistent with these two print statements that we have here. So this is very interesting, right? So you can access attributes using this dot notation. You can also add methods to be able to also display or print these attributes if you want to. So right now we created one object. Let's create another object, right? So this is the idea of reusability that we mentioned, right? You have this student class and you can create as many objects as you want, right? So you're at the university, there are 20,000 students. You can have 20,000 objects created using this class that we have defined, this blueprint or template. So here we have another student ID. These are just some random numbers, another name. This case, I want to just use the display info, and you can see that now we have the student ID and name for this new student or new object that we have here. But the fact that matters is that you can now add a lot more functionality, right? So that's what we talk about, right? The fact that you can actually encapsulate data and functions within these objects, right? So let's say that this class that you have, you want to add a method called add courses to this class to store the list of courses that a student has taken. This is very important, right? You want to know, whether a student can graduate or not. And for that, you need to make sure that you keep track of all the courses that each student has taken. So how this works is that very similar to before, we use the class keyword, the name of the class, we use the constructor. Remember here, at the beginning, we can assume that the courses that each student has taken is an empty list, right? That's what this is. This is an empty Python list. And we don't even have to provide any input for this, right? Like before, we have a student ID and name, which we assign to each student, but we assume that each student starts with no prior courses. So that's why it's an empty list. We modify the display info to also add the information about the courses that they have been taken. But what's really important here, we need to add a new method or function where we can add courses, right? So again, self should be always included because that's what refers to the object being created. Then we need to add a list of courses that the student has taken. And then self.courses underscore taken is a Python list, right? Remember that that's how we define this. And for a Python list, we can use this dot extend method that you can provide a list of courses, and this will be added to this empty Python list that we have, right? So that's like the main difference here, that we added a new attribute called courses underscore taken. And now we can also update that attribute using this new method, right? So that's the main difference from what we have here and what we had in the previous cell. So like before, we can create a new object or a student with some student ID, some name. You can even right now use the display info. And you can see that since we have not used add courses before, there's no courses available for these students, an empty Python list. But let's say now we use this .add courses method, and you provide a list of courses that this student has taken, right? So mathematics, history, programming, 3 courses. So once you run this, first line, you will add this information to that courses underscore taken. And if I use this dot display info, this method that displays information for this student, you can see that now this courses underscore taken is not really empty anymore, right? It has the information that we provided, and we were able to successfully update that attribute, right? But what is even more interesting here, I would say, is that from now on, at any point when this student takes a new course, you can always use this add courses method and keep track of all the courses, right? Because you have a like an attribute, which is a list with these 3 courses here. And now you use this add courses again, and you're going to add the statistics to whatever this student has already taken. And you can see that if I run this again, we have statistics as the 4th course included here. So you can see this idea of encapsulating data and functions, right? Because now we have a very special function, this add courses, which works on this attribute or data, which is called courses taken. And also we can reuse these as many times as we want. If we have 20,000 students, we can use these for all 20,000 students. So to just recap what we had, here's the summary of the main syntax for defining a class in Python. Obviously, use the class keyword, the class name. You always want to have this constructor. This is very important. And the way it works is using this underscore, underscore, init, underscore, underscore. Do not forget to use self. And then use your arguments that are parameters passed during instance creation. And then usually you can update these arguments or these attributes that we have here that we passed using these methods that we define, right? So these are some methods to define behavior of this class. And remember that self refers to the instance calling the method. And that's something that we can always keep in mind in terms of like the main structure for defining classes. Something that is important to remember is that when we talk about attributes, we have instance attributes and class attributes. Instance attributes belong to specific instances of the class, right? Or the objects. And so they're unique to each instance. For example, a student ID that we have, right? Each student has a unique student ID. That's something that belongs to the instances of the student class, not necessarily the entire class. And for those, usually we define them within the constructor method, that init method that we just said, right? But class attributes belong to the entire class and shared by all instances of the class. Let's say that you want to have like a class called like circle. To explain this, we import the math module. And in this case, because we want to use the number pi, right, to like, for example, find the area or circumference, we define this math.pi, which is included inside this math module as pi. And remember, this is now class attribute, right? Because this belongs to all instances of this class. And we specifically put this outside the constructor, right? So this is our constructor, and we put this pi outside. So this pi now on is something that is shared across all these instances. But obviously something like radius is specific to that object or that circle that we have, right? So we don't want to share the same radius across all of them. That's why it's inside this constructor. And so you can now use, let's say, one method, which is called calculate area, right? So pi r squared, that's exactly what we have here. But the way that we now access this pi, remember, this is a class attribute. The class name is circle. So you say circle, the name of the class, dot pi, right? So that has now a very special meaning, means that that's the pi that we have in math, right? And then obviously you have the self.radius, because this is something that belongs to the very specific instance of this class, right? So that's why here we have self.radius and then the class name.pi, right? One is class attribute and the other one is instance attribute. You can also calculate, circumference is 2 pi r, right? So, but just to show you the fact that you can use this class attribute using this name of this class dot pi. And, now we can create different instances or objects. So you just have to call the name of the class and then the radius, because that's the only thing that we really need here, right? That's just the radius. And now you can see that we can access these class attributes or use this calculate area or calculate circumference, and you can print this information, right? So you can see that this circle.pi is 3.14.1415, right? So that's the pi that we have. And then we have the area of circle 1 and the circumference of circle 2, right? So you can always double check to make sure that these are correct, but I'm sure we have done everything here correctly. Okay, so now let's go to the next topic. In Python, if you use the name of object and then use the dot notation and then underscore underscore dict and then underscore underscore, this is a dictionary that holds the attributes and object, right? So let's say we have this class example. I want to make it really simple, where we have two information or two attributes, I would say, name and age. So now we have to just assign these to these attributes. Usually you want to add also some methods to do something with these attributes, but right now we want to keep this simple. And you can see that if I use this, name of this object, which is, obj dot this, keyword that we said, this dict here that we have, you can see that you can now get a dictionary, right? To just show that this is actually a dictionary. You can use the type function in Python that works everywhere. So this is indeed a dictionary. And you can see that the name is John and age is 25, right? So these are the key value pairs that we have. Okay, so now let's move on to the last example that we have in this notebook. And this is something that very much related to when we do what we want to do in data science and machine learning. So let's say you want to have a basic implementation of a custom array. So, for example, Python lists, NumPy arrays. But let's say now you want to have a custom array that mimics some of the functionalities of a NumPy array, but focusing on Python list with attribute n, right, where n represents the length, along with some basic operations such as dot product or vector norm that we want to implement, right? So obviously you can use like NumPy arrays to perform this, but right now we want to have our own class that has a very special like functionality, right? Without really going through a NumPy array, right? So the goal here is that, create a custom array that kind of looks like NumPy array, but not necessarily using built-in functions in NumPy. And in order to do this, we're going to start with math module. Remember, math module is something that, is included in Python. So it's very helpful for any kind of mathematical operations. We have been using this even before introducing NumPy arrays. So in this case, we define a class called custom array. Remember that we, use uppercase letters for the first letter of each word. Obviously, in this case, you want to have, again, your constructor. And it starts with this init. Self is always there. Again, it refers to the object of the class being created. And then some data, right? So something that is very nice here, you can actually use this isInstance method or function in Python. And we have used this before. Just to recall this, you have two arguments. First, you provide your object, and then the type that object you want to see whether it belongs to or not. So we want to make sure that here, this custom array that we have, we provide a Python list. So we say that if not isInstance data of type list, then raise some error, right? So we have not discussed this in much details before, but what this does is that we check this if statement. And if the input is not a Python list, then we raise this error, which says that input data must be a list. And now, if actually the input is a Python list, now we use this self.data, which is the data that we provided. So that's the attribute that we call it data. And then the other attribute that we want to have here is this n, which is simply the length or the number of elements in this Python list, right? So we want to have these two attributes defined. And then we want to perform some operations on these Python lists. And one of them is, for example, like dot product, right? So if you have two Python lists and you want to find the dot product between them, you're going to multiply the corresponding elements and then add the result of these, products, right? So the first thing you want to do is that if we have two Python lists, so one is self, which is what we have here, and then also we need the other Python list. Obviously, you don't have to call this other, but that these are good programming practices. That self refers to the current object that you have or you want to create, and the other corresponds to the other object, which is another Python list. And if these two, because now we have this attribute which is called n, which is the length of this, if the lengths of these two arrays are not equal, we cannot find dot product. So we have to provide some error message that we have done here, right? So you provide this value error to say that, input arrays must have the same length. So the user knows that, what happened and, why, an error message is encountered. But if, they have the same length, then what you can do is to use this zip, which is something, again, we discussed before. And what this does is that if we have two lists here, right, we have self.data and other.data. So these are the two Python lists. You're going to create a list of tuples where each tuple contains one element from the first list and one element in the corresponding location from the second list, right? And so now you can use this for loop to iterate over all these pairs of values, and then you're going to multiply them together, and later you're going to sum all of them, right? So these are the ideas that we had behind, list comprehension, right? So obviously you can write this in multiple lines, but it's a much more compact way of doing this. So you use this zip to create a list of tuples. You use this for loop to iterate over the elements of these tuples. You multiply them together, right? And then finally, you're going to sum them together. So one thing you can do if you're not 100% sure how this works, create two Python lists and call one call one self.data and the other one other.data. So these are the two Python lists that you have. And just perform this, right? Use the zip and then the for loop and then multiplication and then the summation. And in that case, that should really make sense. And then also we can here create another method, which is this vector norm. And then you have this self again here. So for vector norm, remember, you just want to find the norm of a vector. So we only have one vector. We do not have the other one that we used before. And this one is also simple, right? So for each element in that list that you have, you want to raise that to the power of 2, add all those values, and then take the square root, right? So that's the definition of the vector norm, right? So which is the square of each element. You add all of them together, and then you take the square root. So in this case, let's say that we have a custom array where you pass your list, which is this 1, 2, 3, and then you have another object, which is this array 2. You pass in 4, 5, 6. They obviously have the same length. They're both Python lists, so we don't expect to get any error messages. And now the way that you can use this is that you can say for dot product, finding the dot product, you have array 1 dot product. That's the name of this method. And now you provide the other list or object that we have, which is this array 2, right? And then for using this vector norm, you can see that we can just use array1.vector norm, and this doesn't really need any input right now, right? Because the only input is self, which is already provided, and it will automatically find what we need here, which is this sum of the square of elements, and then taking the square root, right? So if we do this, you can see that we get the dot product, which is 32, and then the vector norm. So something that we can actually do here to just show you how this zip works here in this case, that's something important. So let's look at this very simple example. Here I'm going to work with two Python lists. So I call list 1, and I'm going to copy this 1, 2, 3, and I'm going to have list 2, which is going to be 4, 5, and 6, right? So just to show you what this zip does here, I can just copy that. And remember, right now, list 1 is what we have here, and we have list 2. So I'm copying pasting so you see like exactly how that works. And in order to see what's actually included inside this zip, we can use list. And if I run this, so this is exactly the idea behind using this zip, right? So you get a list of tuples where each tuple has 2 elements, one from the first list, one from the second list, and you can do this for all other elements that you have or other positions that you have, 2 and 5, 3 and 6, right? So in order to find the dot product, you want to multiply these 1 and 4, 2 and 5, 3 and 6, and then add the result, right? So that's exactly what we have here. So I can show you this part of this. Let's show you this one. So we can remove that here. So now we have that for X and Y, right? So X corresponds to the first one, Y corresponds to the second one. In zip of list 1 and list 2, we want to find this sum of these elements. So this should give me that 32 that we have seen before. So let's run this and see what we get here. And that's exactly what we see, right? So what's happening, you multiply 1 and 4, which you get 4. 2 and 5, which is 10. So far we are at 14, and then plus 3 times 6, which is 18. So 14 plus 18 is 32, right? So that's just something that we're going to need also for the homework problems too, using this zip to be able to perform these element-wise operations. Okay, so let's see if we get an error message. And going back to this class that we defined, right? So if you remember, we said that we need to provide a list. But what if we provide a tuple to this custom array? Do we get an error message? Of course we do. So if you see that we get this type error, input data must be a list. And this comes from actually this if statement that we have, right? Because now if we choose the is instance, right, that tuple is not a list, so that's false. And then there is a not here, which makes it true. And so this means that you're going to raise an error and you're going to exit this sort of like, object creation here. So, and you will explain what the problem is. And let's look at the other error message that we included. What if we have 2 objects with different lengths? If I use the dot product, you again see that it says value error, input arrays must have the same length. So this is the error message that we included. And obviously you can check the instance attributes here that we have. So you can see that array 1, if you use this .n, and remember, we do not need to use parentheses because these are attributes. We get 3. And so this wraps up this lecture on classes, objects. As you see, they're very simple topics once you get to create your own classes and objects and start working with them. So that's something important to start experimenting with the code that we have here. Okay, so in terms of homework for this problem, we want to use this custom array that we have here for the problem 1. So we have already this custom array, right, where you have a Python list, and then you define the dot product, vector norm. But what we want to do here to make this even more interesting and add some more tools from statistics. For example, one of them is this correlation coefficient between two vectors or two Python lists, to better say here, where the formula is, basically a summation of xi minus x bar, and x bar is just the mean of the first vector x, y bar is the mean of the second vector. So it's very much like an element-wise operation as we just did for dot product, except that now you have to subtract these means from both vectors. And then for the denominator, if you look at it, it's very similar to that, the sum of the squares that we had before, except that now, again, you have to subtract these mean vectors from both of these summations. So that's one method or function we want to add, this Pearson correlation. The other one is the vector norm. And so what you can do here is that we have something known as LP norm, which is very helpful in machine learning and data science. So this is a general norm where the way you calculate this for a vector, you raise each element to the power of p, and then you add them together and raise it to the power of 1 over p. So if p equals 2, this is exactly the norm that we already implemented, the vector norm, also known as the Euclidean norm. But it really here is interesting that this p can be any number greater than 1. So, it can be 1, it can be 3, 4, 5. So it can be anything greater than or equal to 1. And we want to give the user, when we define this function, the flexibility to use any p that the user wants, right? So you can see that here for solving this problem, we copied paste part of the class definition that we had, but here you have this Pearson correlation. And remember, here you want to find this between two lists or vectors. So you need to have self and other, very similar to when you find dot product. I've included a statement here to raise an error if we do not have the same length right before. And here is where you have to add your code, right? So this is where you include your solution. Similarly with LP norm, right? So here you also have this P. And the only thing that here we want to make sure is that P is not less than 0 or exactly 0. But, in terms of, we're going to talk about this later on, to be a valid norm in the sense that we define in mathematics, it has to be actually greater than 1, not necessarily greater than 0. But computationally right now, you can actually find this value for any p greater than 0. So that's why we have just that statement. And for any p greater than 0, you can, raise these xi's to the power of p, and then the whole thing raised to the power of 1 over p. And you should be able to use everything from the math module. So remember here, the goal is not to use NumPy's built-in functions or methods. We want to have our own custom array. And I included one test case that you should run here to make sure that your code actually working properly. So once you define your class, you can run this cell. The other problem that we have here is very interesting. It's actually a gateway to data science and machine learning. So what we know right now, it actually you can implement your own linear regression class or model. We are going to talk about machine learning libraries and data science libraries later on. But right now, you can actually create your own small libraries in some sense. So in linear regression, the equation that we have is that, the dependent variable or output is beta 0 plus beta 1 times x, and x is your independent variable or input, right? So we know that beta 0 is technically the intercept or the y-intercept, and beta 1 is the slope or the coefficient, right? That's what we learned in calculus 1. And so if I give you a bunch of data points, meaning that multiple instances of x and y, like x1, y1, x2, y2, right? So different data points that belong to this equation, you can actually, calculate or estimate these coefficients using these formulas, right? It looks kind of like that Pearson correlation coefficient that we have with some, minor modifications, right? And these bars here means that these are the means of the vector x and means of vector y. So we're going to go later through why we have these two equations here. But right now, because we are mainly focusing on programming and object-oriented programming in particular, we want to be able to just implement this. So you want to define a class and then create these methods to calculate these coefficients. And once you have this beta 0 and beta 1, now for a new input like this new x, you can actually calculate this output, which is this y, right? So beta 0 plus beta 1 times this new input. So that's when you want to make predictions. So here we have, the basics of this class linear regression. For simplicity, here I included some information, and now we have these two: calculate coefficients and predict. And you can see that here we have one example where I already know this beta 0 and beta 1. That's how I created my data. But I want to make sure that you run this class and create these objects and find beta 0 and beta 1 to make sure that this works. And then later on, you want to define a new class called NumPy dataset analyzer. In this case, you're actually working with 2D NumPy arrays, right? So that in that case, actually your input is a NumPy array. But what you want to do is to add these methods or functions to really simplify the process, such as like calculating the mean for one column, median, finding the minimum, and finding the maximum value. So we already know how to do this in NumPy. The only thing we really want to do is to put this in a class definition where it's specialized to be able to find these different values for each column. Hello everyone. In this video, we continue our discussion about object-oriented programming. One of the most important topics in object-oriented programming is inheritance. Inheritance allows a new class to inherit properties and behaviors from an existing class. There are different ways to name these two classes, but something that is always important to remember is that in this case, we assume that we have an existing class, and then we want to define a new class based on this existing class. And usually the existing class is called superclass or parent class. And then the new class is known as the subclass or child class or derived class, right? But it's always important to remember this relationship that one is already defined and the other one is supposed to be created based off of the existing class. And inheritance is a very important topic because it promotes code reusability and establishes a relationship between classes. And therefore, this means that you can reuse, extend, or override the functionality of the superclass. So let's look at the syntax of how we can create this subclass. So remember, in this case, we can use the keyword class, and the name of the base class or superclass to define that. And in this case here, I put comment so that this means that we have some code here. You have usually a constructor, some methods. So this is what we use to define this parent class or base class. And then after that, now once you want to inherit from this class and define the subclass, we are going to use again the keyword class and the name of this subclass. And one thing that is important to remember is that we have to use these parentheses and put the name of the base class or parent class, right? So it's very much like when you define a class that we discussed before, except that in this case, we have to use these parentheses and provide the name of the base or parent class. And after that, now we have to have, again, constructor and methods that we want to use for this class. So let's go through the details of this and how we can do this through a very simple example. So in this case, we are going to first define a class called employee, right? So this refers to employees of a company. And this class has just a method which is called display info to display information about that employee. So let's look at how we can write that, right? So in this case, first we have our base class. And we use the class keyword, the name of the class, which is employee. Then we have to provide the constructor to instantiate this class to create objects. In this case, we use def and these double underscores. Remember, these are special methods, which means that in this case, once you create objects, you have to provide these two attributes, name and employee ID. And self is what refers to the object being created. So in this case, we're saying that we have two attributes, the name of the object dot name and the name of object dot employee ID. And these are the values that we assigned. And then after that, for simplicity here, we are only using one method. And in this case, the method is display info, in which we want to just provide this information using formatted string or f string, where we have employee ID, and then the name of the employee, right? So that's kind of like our base class that we have here. But now we want to talk about our subclass. So the way that subclass works, as we said earlier, we choose the name, and then inside parentheses, we provide the base class, which is employee, right? And then use colon, and now we have to have our constructor and method and things of that nature. But let's focus right now on this constructor that we have. How does this work? Because something to keep in mind is that we do have a constructor for the original or the base class. And now we may also want to add more attributes for the subclass. So how can we do these at the same time? So as you can see here, the way that this works is that, let's say we want to add one extra attribute here, which is department, and this tells us that, which department this manager works for. And then the other first two attributes are identical to what we had before. So in order to define the constructor, it's easier to use the constructor from the original or the base class to assign those values to the corresponding attributes. And in order to do this, you can use the super function. So what this does, you use super.init, and you provide name and employee ID. So why does this work? What this basically does is that this super is going to look at the constructor for the super class or the base class, and it's going to initialize that using the information that we have, right? Because remember, name and employee ID do belong to the base class. And that's something that we can use using the super function. However, in this case, we have a new attribute that we didn't have before, and that's department. And in order to instantiate that one, we can just add that inside our constructor for the subclass. So let's see how this works. So when we define our subclass and especially the constructor, we have this init method, again with self as the first argument that refers to the object being created. And now we have three positional arguments. Then we are going to use this super.init with name and employee ID. So what this really says here is that we want to use the constructor for the original or the base class and provide this name and employee ID. So we don't have to repeat all these steps that we have done before. We can just put this one line and say that super.init. And in this way, we're going to use the constructor of the base class. However, we have to add one extra attribute here, which is this department. And in this case, we can use this self.department. So this really simplifies the process because we do not have to repeat these two lines that we had for the base class. So this is how we can use the constructor. But in this case, we also want to have a method called display info, but we want to override the display info of the base class, because for the base class, we only have two pieces of information to print, the employee ID and name. But here we have actually three pieces of information, right? Name, employee ID, and department. So in this case, we defined a new method called display info. And even though it has the same name as the method for the base class, it is totally fine because Python understands that display info is a method that can be applied to the subclass and the base class. And the usage of these two methods is actually different, right? So if it applies to the manager class, which is the subclass, we want to print the employee ID for the manager, the name, and the department, right? So we have three things that we want to print. Whereas if it's for the base class, we actually have two things to print. And here there's no conflict or any issues. So just to show that how this works, let's just run this cell to define this base class and subclass. And now I want to create an instance of this manager class, right, which is the subclass. So we provide the name as expected, and then employee ID. So we assume that employee ID is 101. And then the department, and let's say the employee, this manager here works for the IT department, right? And so if I create this object and put display.info method, you can see that we print these three pieces of information, and that's something that we expect, right? That's what exactly is supposed to happen if we use display info for an object of the manager class. But let's see if there's any issues if now we use the base class, which was the employee class. So in this case, remember, we only need two pieces of information, only name and employee ID. And in this case, if I use display info, we see that we only get information about employee ID and the name. And this is exactly what we expect, because if we use the base class, which is employee, we only have these two attributes, name and employee ID. So you can see through this example that this .display info works differently if we apply it to the base class or the subclass. And this is something that is very preferable because in many cases, we want to make sure that we have different functionalities when working with different classes that might have been inherited from some base classes. And you can see that now in this case, let's say for some reason we forget about the fact that employee class only has two attributes and provide this additional attribute, which is the department name. And if I run this, you can see that you get an error message, right? So the error message clearly says that we should have provided 3 positional arguments, but 4 were given, right? So this is because in this case, when we have this employee class, we have 1, 2, 3 positional arguments, but we provided 4, right? Because we also provided a department name, which was IT. And that's something that it doesn't work for the employee class because we shouldn't provide that information. And that information should only be given when defining the manager class. Okay, so now let's make this a little bit more interesting, right? So let's say for the manager class, we want to add a new method, which is called assign task. In this case, this means that a manager can assign tasks to employees. And the way that we can do this is by adding a new method here, which is called assign task. And remember, self is something that we always have to include to know what object we are referring to. And the way that this works is that we provide two additional input arguments. One is employee and the other one is task. So this means that the manager assigns this task to this employee that we provide as inputs. And in this case, we just want to print that manager with this employee ID assigns this task to employee with this employee ID. So if you look at here, we are using this employee ID 2 times. But one is the employee ID of the manager, and the other one is the employee ID of the employee who is supposed to perform that task. So if we run this cell right now, and in order to make sure that we can do this task assignment, we need to have an instance of the manager class and also an instance of the employee class. So very similar to before, we do these object creations or instantiations. And then we say that manager instance dot assign task, right? That's something that we define here. And if you look at it, we need two input arguments. We need the employee information, and that's where we get the employee instance, and also the task. So the task here is just a string here, which says code a new feature, right? So let's say the manager wants to ask the employee to code a new feature. And if we run this, now it says that manager with this ID, and this makes sense because the ID of the manager is 101, assigns this task, which is provided here, to employee with this ID, right? And that's the exactly employee, the ID of this employee, right? So you can see that this is very powerful because now we have this original or the base class, and now we can subclass and add very useful attributes and methods that we need them. And we do this without writing everything from scratch, right? Because we are still relying on some parts of the base class. So just to recap this, right, just in terms of especially the way that we define constructors for the base class and the subclass. So we have this class and then again the name. For the base class, we don't use parentheses because this doesn't inherit from anything else. This is just its own class. And then we have some base attributes, right? So this can be more than one, but in general, these are the attributes provided for the base class. And the way you can do this is just by saying that self dot, the names of these attributes equal to these provided base attributes, right? So that's always what we can do for the base class. In our previous example, base attributes are name and employee ID. And then we create the subclass, right? And the subclass inherits from the base class. And in this case, for the constructor, we actually do have two types of attributes. The attributes that belong to the base class and new attributes that only belong to the subclass. For the first set, which is the attributes that belong to the base class, we can just use this super function, and .init, you provide the base attributes. And if you're wondering here inside these super parentheses why we have this information, this is actually the right way, or I would say the formal way of using super, where you use the name of the subclass and then the self input argument .init. But as you saw before, you can just leave these parentheses empty and it works. So that's one nice thing about Python, that it's really smart in terms of understanding what we are referring to, because since we are inside this subclass, it understands like what we're trying to do. But if you want to be very kind of formal and rigorous, you can always add the name of the subclass and the self input argument here to use the constructor of the base class. And then in the next line, that's when you use self dot sub attribute. And these are the attributes just for the subclass, where we do not have these for the original base class. Okay, so now let's do one more example to practice a little bit more. And let's say we want to have a class for calculating distances. So in this case, we have a two-dimensional space, meaning that for each data point, we have XY coordinates, right? That's something that we always work with, when we have like calculus one and in that area. And what we want to do is to calculate the distance of each point to the origin and also the distance between two objects, right? So in this case, we can import the math module and we define our coordinate class. So that's class coordinate. So we do need a constructor. And in this case, to define or instantiate, I should say, an object, we need to know the XY coordinates, right? So that's why we have to provide these XY values. And we have self.x equals x, self.y equals y. And then we want to add a method to find the distance to the origin. So in this case, the formula is very simple, is a square root of x squared plus y squared, right? And therefore to implement this, we need to return the square root of the sum of x squared plus y squared. We can also define this other method that we have here, which is distance between two data points. So we have self here, which is the current coordinate that we are looking at. And then we need to have another object, which is the other coordinate. That's what we call it. And we have to find the difference between x coordinates, the difference between y coordinates. And after that, it's very much the formula that we had before, is the square root of this dx squared plus dy squared. That's how we find Euclidean norms. So let's see how this works. So in this case, in order to use this coordinate class to create objects, you need to provide the xy coordinates. So let's say one data point has this xy coordinate 3 and 4. So 3 is the x value, 4 is the y value, and then the other point is 1 and 2. So we created the 2 points here. And now you can use point 1 dot this method that we have here, distance to origin, and print the result, again, using the formatted string or f string. And you can see that something that we use here is this notation. And what this means is that we want to have 2 decimal places, right? Because when you find this distance to origin, you may have, many decimal points, and usually it's good to round these numbers. So this means that we want to have up to 2 decimal places in our result. And the same thing if we want to use the other method, which is called distance between, right? So you have to provide one object which has these 2 xy coordinates dot distance between, and then we have to provide the other coordinate. Like that's what it refers to here. And then this class tells us that the way we can do this is by subtracting the x and y values and finding the square root of the sum of these, the square of these differences. So in this case, if I run this, you see that we get the result. The first one makes sense because we have this data point with coordinates 3 and 4, and therefore the distance to origin is a square root of 9 plus 16, which is a square root of 25, which equals 5 as we get here. And then for the other one, we want to find the distance between these 2 points. And as we just discussed, you have to subtract the x coordinates, which we get 2, and then subtract the y coordinates, which again we get 2, and then the result would be a square root of 4 plus 4, which is a square root of 8, and that's what we get here. Just to make sure, we can do the math here, but this should work. And that's exactly what I was talking here about rounding these numbers, right? So if you find a square root of 8, you get 2.8284, right? So you get all these decimal places. And that's sometimes like really unnecessary. So what you can do is to say that you only want to see 2 decimal places. And you can see that in this case, we get 2.83. Okay, so now that we defined this coordinate class, and this is actually right now our base class, right? Because if you look at it, this has not inherited from something else, right? If it did inherit from some other class, we should have like another base class here, right? But we do not have this right now, right? So this means that this is our base class. And let's say we want to do subclassing and create this new subclass, which is called enhanced coordinate. An enhanced coordinate just because it probably provides more functionality when working with these 2D data points. And you can see that this indeed inherits from the coordinate class that we defined before. So in this case, we want to slightly change the way that we instantiate this class. So we have the xy values for the 2 coordinates that we have, but we also want to add another attribute which is called label, right? So you want to, let's say, name these data points as A, B, C. So we provide that label. So you can see that for the attributes that they belong to the base class, we can just use super. We don't need to use anything inside these parentheses if we don't want to, and then use .init. And in the line after that, we can now say that, well, this self has another attribute, which is new, and that's this label, and do this assignment. And here the goal is to just add one more functionality, and that's finding the counterclockwise angle that we have, right, between that data point and the x-axis. So in order to do this, we can use one of the functions in math module, which is called this arctangent, and you have to provide the y and x coordinate. So you can search online for measuring the counterclockwise angle in radians, and you can see more information about this, arctangent. But because this is not a, trigonometry course, we, leave this here. But the goal is to kind of use this built-in method or function from math module to find this angle. And something else that also we want to do, because we want to find this angle in degrees. So we use this math.degrees to convert the result, which is in radians, to be provided in degrees. Okay, so now that we have this new method that we defined for our subclass, you can see that we can define an object using this enhanced coordinate. These are the xy coordinates, and this is the label that we just talked about. And even though for this enhanced coordinate that we have here, we never defined any method called distance to origin, but we can still use it because this inherits that method from the coordinate class. So this is what we are doing here. So here we're going to use this method called distance to origin. And even though, again, we didn't include this inside the definition of enhanced coordinate, it is already available because it's part of this coordinate class. That's the whole idea behind subclassing. And also we can apply this new method, which is angle with x-axis. In this case, the result is kind of obvious because if you have this, point at location 2 and 2, that's the 45-degree line, right? Is on the 45-degree line, which means that the angle is 45 degrees. But we want to, make sure that we get the correct result. So if we run this, you can see that for the first result, which is distance to origin, we get a square root of 4 plus 4, which is a square root of 8. And we just check this, that should be 2.83. Again, we get this result because we have also 2 decimal points. And you can see that now this arctangent works too. And we get the degree, which is 45 degrees as expected. So the idea behind this example was to show you that even though we don't have distance to origin method for this enhanced coordinate, we can still use it because it is part of the coordinate class, which is the base class. So that now that we know about inheritance, we can also write more powerful classes in Python. That's something that we really need them when we want to work with objects in different contexts. So we had this idea before about these 2 underscores and using def init for instantiating objects from blueprints or designs provided in classes. And in fact, these are special methods because of these 2 underscores that we have. But one thing that is important to know is that this is not the only special method that we have, and actually we have a bunch of these. For example, one of them is this underscore underscore str, right? Which, as you know, stands for a string. So what this does is that it provides a human-readable string representation of the object and returns a string. So what does this mean? So let's create a class. And in this case, we define a very simple class to just show the idea behind using this str. So in this case, we just assign one value to this attribute, which is called value. And now we define this special method str. And what this does, right, this is a function. It returns this string, which is a formatted string or f string, which says my class instance with value, and then you provide the value here. So this means that now that we create this object and we use print object, you actually get this information, meaning that once you call print function on this object, it's gonna look for this str, and if it finds it, it's gonna return this string that we have here. So it's kind of like the similar idea to class constructors, which means that when we call the class, automatically we are going to run the init method that we have. So that's the same idea here. When you use print, we're going to see if there is this str available, and we're going to print that. And also the other nice thing is that if you just use str, which is a function in Python, and then the name of that object, you again get that a string that we have printed out. The other useful thing that we can do with these special methods is to define what equality means. Because remember, right, as you can see here, we define a class and we have this attribute with the name value. So if I just create one class with value 2 and another class with value 2, these are indeed 2 different objects, right? Because one time we created one of them and the other time we created a new object. And although they have the same value for this attribute, but they're not the same. They're 2 different objects. So you can see that if I use this equality sign here, which, to make sure that whether the 2 objects are equal or not, you can see that we get false, which is not really useful because they do really have the same values, even though there are 2 different objects. So how can we get around this problem? And that's using this special method, which is underscore underscore EQ, right? And in this case, we have 2 inputs. the self, which refers to the object being created, and then other, which refers to another object. You do want to make sure that the other object belongs to the same class, because that's something obviously we want to have when we check equality. But then we're going to see whether the value attribute for the self is the same as the value for this other that we have here. And we're going to return the result of this comparison, right? So if these two are equal, then we get true. Otherwise, we are going to get false. So you can see that here, if I run this, because we did add this special method, now if we compare whether to see object 1 is equal to object 2, we get true. And that's something that, is possibly desirable in this scenario because they do have the same value. The last thing that we're going to talk about here, which is another important topic, especially in the context of data science, is what if we want to have methods with variable length input arguments, right? So in some cases, you want to give the option to the user to maybe provide multiple inputs, and the number of inputs really depends on how the user wants to customize the method or the level of information that the user wants to provide. In order to do this, you can use these star args and star kw args. So I'm going to tell or talk about very briefly about what these things stand for. But these are very useful tools to provide these variable length input arguments. So args stands for arguments, and it allows a method, as we said, to accept an arbitrary number of positional arguments. So this is something very important to remember because that's what differentiates args with kw args. So in args, we want to provide an arbitrary number of positional arguments. And the way it works is that these arguments that are passed as args are collected into a tuple within that method. So let's create a very, very simple class. In this case, we do not even include the constructor because the idea is to show you how these args work. So we are going to define this method called print args. This is just a method. We use self, like always we do, and then we add these args. So what this means is that now the user can provide different, positional arguments, and the number of arguments is arbitrary. But since these are provided in a tuple, now you can use a for loop to iterate over the elements that are provided. And in this case, we just want to print them to show you yes, they are actually passed along this method. So you can see that we create this object, which is instantiated from the example class. And then we use this method called print args. And in this case, we provide 1 and 2 and 3. So as you expect, now this means that we have a tuple here, which contains 1, 2, and 3. And now we go through each element and print that. But what is really nice here, that we can actually have an arbitrary number of inputs. So I can have only 1. So you can see that we print that. We can have 2. We can have 5. And so in this case, we can provide an arbitrary number of inputs. So let's put that back to 3, and you can see that that's how these args work. But how about that KW args? So that stands for keyword arguments. And this allows to accept an arbitrary number of keyword arguments. So this is the difference. The previous case, we set an arbitrary number of positional arguments. In this case, we have keyword arguments. And what does this mean? This means that actually we have key value pairs, like exactly when we talk about dictionaries in Python, which is a very important data structure, we have these key value pairs. So in this case, we create, again, a class called example. and we define a new method called print keyword arguments. And you can see that here you have to use 2 stars and then key. This name is basically like arbitrary, but again, it's a good practice to use KW args to know what we are doing. And because this is a dictionary, remember from the lecture on Python data structures, dictionaries, they have this method called .items. And this will give you a list of key value pairs that we have, which means that now we can write a for loop to iterate over them. And you can see that in this case, we are giving these names, or I would say keys and values, right? So name is the key, John is the value, similar here, age is the key, and 25 is the value. And if we add all this information here, you can see that we're gonna print each key value pair. But again, the nice thing here is that we can, for example, remove the city information. And if I run this, so now we have only name and age. But I can also put that information back, and you can see that now we have these 3 key value pairs. So that's something that you need to decide whether you want to provide positional arguments, meaning that you need to remember later on what is, this one, what does this one refer to? What does this 2 refer to, right? So this might refer to different attributes. But if you have multiple attributes, it's just much better to actually name them and provide these key value pairs. So let's go through quickly the homework assignments that we have. So in the first case, you want to modify that enhanced coordinate class that we have. So that's something that we define in the lecture. And add a new method called inQuadrant that determines whether a point that is represented by its XY coordinates is located in a specific quadrant or not, right? So we know that in a Cartesian plane, we have 4 quadrants, 1, 2, 3, 4. And in this case, we want to add this inQuadrant method and provide the quadrant number. So in this case, for example, 1 or 2, and we should get true or false, meaning that does this data point that we have belong to quadrant 1 or not? So, in this case, if you use all these quadrants 1, 2, 3, 4, so 1 should be true and the rest of them should be false. So this should be just a minor modification of the enhanced coordinate by just adding this method. The other thing that we want to do here for problem 2 is that to define this class called math operations, you want to define a method called perform operations. And in this case, we want to use these star args that we just talked about to be able to provide variable length input arguments. And what you need to do is to print 3 things. Print the sum of all the numbers that are passed as arguments, because remember, these arguments may not be numbers, they can be also strings, right? So we want to sum all the numbers, product of all the numbers, and concatenation of all the strings, right? So you can see here we have an example. Like if I provide an arbitrary, set of, numbers and strings, I want to be able to get the sum of these numbers, 2 pi 5, 4, 2, their multiplication, and also the concatenation of these 2 strings that we have. So this is another example to practice defining classes and using these star args. The next case next problem, we want to define a class called rectangle. And in this case, you want to have 2 attributes. So in this case, you need to define a constructor and initialize these 2 attributes given the provided values. Add 2 methods, one to find the area, one to find the perimeter. But it's also here important to define a method, which is actually a special method called EQ, to compare 2 rectangle instances, right? So in this case, we want to see whether 2 rectangles are equal or not, and this means that their widths and heights should be the same, right? So you can see that here we have defined these objects, and we want to see, whether this rectangle 1 is equal to rectangle 2 or not. And remember, in order to do this, you actually need to define this special method so that Python knows how to compare the two objects. In this video, we talk about modules and packages. In Python, modules and packages help make coding easier, especially for big projects. To put this into context, functions are like small tasks that you can use over and over, so you don't have to write the same thing many times. Modules are files that hold a bunch of related functions together, making your code neat and easy to find stuff. On the other hand, packages are bigger collections of modules, organizing everything into a system that's simple to use and understand. All these parts work together to make Python coding smoother, letting you build complex programs without getting lost in the details. To get started, let's revisit functions. Functions in Python are blocks of reusable code that perform a specific task. And we use the def or def keyword followed by the function name, parameters, and a block of code that usually returns some values. Let's revisit one of the examples that we had before. In this case, we want to define a function which is called isPrime. And this function accepts a number, a positive integer. And the goal is to figure out whether this number is prime or not. Just to remember the definition of a prime number is a number that exactly has two distinct positive divisors, one and itself. And the goal here is to return a Boolean value, true or false, which indicates whether the number is prime or not. This is kind of a simple problem because what we really need to do, find or list all numbers from 2 up to this number that we want to check whether it's prime or not, and then divide this number by the numbers that we have in this list and look at the remainder after the division, right? So if the remainder after division is 0, this means that we violate the definition of a prime number, and therefore we have to return false. And if we go through all these numbers in this list, which is called found primes, and we don't get any factor with the remainder being 0, this means that this is indeed a prime number. And in order to kind of go a little bit more into details here, you can see that we start from 2 up to a square root of the given number that we have here. So if you want, you can iterate or go through all the numbers up to this number that is given here. But in general, we can show that it's enough or sufficient to put the maximum to be a square root of this number that we have here. That's why we have this raised to the power of 0.5. But this shouldn't change the result, and it's more efficient to use the smaller range or list here. And after that, we use a for loop to iterate over all these elements in these found primes. And if the remainder of the division of num by factor is equal to 0, then we have to immediately return false, because then we know that this is not a prime number. And otherwise, if we go through all these elements in found primes and we do not return anything, meaning that this statement is false, then we return true at the end of this function. So just to see how this works, so let me run this cell. We can try a few options here. So you can see that if we provide 3 is indeed a prime number, so we do get true. Then for 4 is not a prime number, because if we divide this by 2, we get 0, the remainder after division. So that's why you can see that we correctly see that the result is false. The same thing with 9, because 9 is actually 3 raised to the power of 2, so we get false. And for 11, this is really a prime number, so you can see that we get true, right? So for 11, we can only divide these by 1 and itself, which is 11, and we do not have anything in between that we can divide this number with, and we get 0 for the remainder of the division. So the nice thing about this function right now here, this df is prime, is that now if we have a bunch of numbers that we want to see whether each one is prime or not, we do not have to repeat this process every single time, right? So that's the part that we say the code is modular, because we have written one function that is modular in a sense that we can provide a given number and it will return the result. So this means that now we can take this to the next step, right? So what if I want to give a list of prime numbers up to some maximum number, right? So let's say you're interested in finding the list of all prime numbers up to 20, right? So we know that 2 is a prime number, 3, 5, and then 7, etc. But the question here is, how can we find all of these up to some maximum? And this is kind of like, given the function that we have before is prime is very easy to implement, because we can start an empty list and then we can iterate over all numbers in the range 2 to this num max. And the way that we define here is that we do not necessarily want to include num max, so it's exclusive. If we want to make it inclusive, we can just add 1 here. But this is the way that we define this function. That's why the docstring is very important, because you can really state all the assumptions and requirements that you have. And the way that we have written this, this nummax is exclusive. So we do not need to be worried about adding 1 here. And so now for each number in this list, we're going to call that function is prime. And if it is true, meaning that if that number is actually a prime number, then we're going to use the append method to add that number to this empty list that we have. And at the end, we're going to return the result. So let's run this cell. And now if, let's say, I use list primes 20, so this means that we're going to see whether 2 is a prime number, 3, 4, 5, all the numbers up to 19 inclusive. And you can see here, we correctly get the result, like 2, 3, 5, 7, 11, 13, 17, 19. But the cool thing here is that you can increase this basically, like, let's say 200 or any number you want, right? So now you have the list of all the prime numbers up to 100. So this is something very helpful. So let's put this back to 20. So here is what we want to do next. So right now we have 2 functions. One is prime, which checks whether a number is prime or not. And the other one is list primes, which lists all the prime numbers up to some num max. So what I want to do, I want to start by restarting the kernel. So you can see that here we can go kernel, restart, and clear output. And the reason we do this is because we want to make sure that we have a fresh notebook. So we do not, right now after restarting this kernel, we do not have these functions defined, right? So I can, for example, insert a cell, or let's just run this, right? So if I just run this, you can see that now it says that this list primes is not defined. And that's something we expect because I just restarted the kernel. So if you want to have this like function defined, you need to run these previous cells that we have here. But here what we want to do instead, I'm going to copy this function that we have here. So I use Command C or Control C. And then I'm going to create a new Jupyter notebook. And I'm going to paste that function, the definition of that function here, right? And also the other thing I want to do here is going back to this previous notebook and copy this other function that we have. So one is prime, the other one is list prime. So the other thing also we want to do, I want to change the the name of this notebook from untitled to primes. So this means that we have now a notebook or file that is called primes, which includes some functions related to prime numbers. And what you can do right now is actually you can download this as a Python file. So if you look at it, here there's this option python.py. So this means that if you use this option, you're gonna save something called primes.py, right? So what we really want to do right now is to create this Python file, which is primes.py, which includes these functions. And so why is this important? This is very important because now if we have multiple notebooks, I can just import this primes.py and I have access to all the functions that I have here. In this case, this may not be a big problem because we only have two functions and you can always copy paste them. But this is not a good idea because if you change one of these functions in one notebook, then you need to make sure that you apply those changes to all other notebooks. Whereas in this case, you have one primes.py that contains these functions. And if you want to make any changes, you can do it here. And once you import these to other notebooks, you're going to be able to use the most recent version. And so that's the idea that we have here about modules, right? So a module is a file like primes.py that contains Python code. It can contain variables, functions, classes, everything that we have seen so far in this class. And this allows us to organize code into separate files for better maintainability. And the nice thing is that modules can be reused across different parts of a project or even multiple projects. And in this case, we created this module, which is named primes.py. And when the interpreter executes this line, right? So again, let me one more time restart and clear output here. What it does, it searches for that Python file that we created. So once you created that primes.py or downloaded that file, make sure that it's in the same folder or directory that you have your notebook. And in that case, if you run this, you can see that now we can import these primes. But something that is very important, like say I make a mistake and I put double two S's here. And you can see that in this case, if I run this, I get this problem or message that it says that no module name primes with two S's. So remember, if you get this error message, this means that the interpreter cannot find primes.py. So you need to make sure that you have that Python file in the same folder or directory. And if you do, you should be able to run this cell. The other thing that is important is that this primes file contains those two functions we have, isPrime and listPrime. But if you want to just use them as is, like for example here, say print isPrime4, you can see that again, you get an error message that says isPrime is not defined. And this is because the module contents are only accessible when prefixed with the name of the module via dot notation. So this means that if you think about this as a hierarchy, you have this module, which is called primes, then use the dot notation dot, and then the name of the function. And if I run this, you can see that now we get the correct answer, right? 4 is not a prime number. So that's obviously one way of importing modules, just say import the name of the module. But as you can see, this can be somewhat inefficient because you have to always also use the name of the module and then the dot notation. So if you want to avoid this extra step, you can use this syntax, which is from the module name, here is primes, import names that you want. So in this case, let's say you just want to work with isPrime, and so you can say that from primes, import isPrime. And if I run this, you can see that now I do not need to use the dot notation anymore, right? Because we specifically say that from this module, import these names, or for example, here, these functions. In some cases, you may have multiple names and you don't want to list all these names here. So Python actually has a nice way to get around this problem, and that's using this notation. So if you say from the module name import star, this means that you want to import all these functions or names that we have in this module. So in this case, you can see that we are checking whether 4 is a prime number or not, and list all prime numbers up to 10, right? And so we get 2, 3, 5, and 7. So these are very, important things to know about, like how to import modules and how to use what's included inside these modules. So once you understand this syntax and this structure, then you can see that some of these modules that we have seen even before in this course are now, they really make much more sense, right? So for example, we have something called time module in Python, which provides time-related functions. So allow you to work with time values, perform operations such as measuring time intervals, pausing the execution of a program. So anything that really relates to, to time when you want to run Python programs. So the very first thing, if you want to use the time module, is to import this, right? So this means that somebody has written this, time.py, which includes a lot of functions, classes, etc., right? And remember, you can always use this type function in Python at any point to figure out what the type of this object is. And you can see that here it says it's a module, right? So now we know exactly what a module is because we created one. So inside this module, somebody has written this function, which is called process_time or process time, which is used for measuring the CPU time consumed by a specified process, right? So something that is very important is efficiency of your code, meaning that how long does it take for your code to run and get you the result that you expect. And the way that you can use this process time is that before the execution of the block of code or piece of code that you want to see how long it takes, you're going to call this function and assign the value to a variable, let's say, called T0. This is obviously optional. You can use any name you want. And after the execution, you again call this function and you save the result in another variable, which I call it T1, right? So these are the kind of like a start, a stop that you use for timing, right? So in this case, you subtract T1, T0 from T1. So now you have T1 minus T0. And this represents the elapsed time or the execution time and serves as a metric to gauge the efficiency of your program. So in this case, you can see that, I have this start process time and end process time. So this is right before and after this for loop. So inside this for loop, I'm going to have this range of numbers up to 10 raised to the power of 7, right? So that's like 10 million, and I'm scoring each element in this range. Obviously, this is not really doing anything helpful right now, but that's the goal here, to just have something that we know is going to take some time because we have to go through 10 million elements. And before then, we use this time.process time to have the start point or start time. And right after, we use that to have the end time. And obviously, then we have to subtract these two times to find the elapsed time. And I'm using the formatted string or f string to print the result. So as you can see, this takes, some time, and you can see that it's about 1.5 seconds, right? Because you have to go through these 10 million times. So depending on, on the CPU that you're using, you may get different results. It may take longer or it might be faster, but that's something that I get right now running here. And possibly if I run this multiple times, I should be able to see different results. So you can see that now, I see some differences in the second decimal points. And just to recap, what we're using here, this 0.3f, that tells us that you want to have 3 decimal points, right? So if you want to really like just look at the first decimal point, you just use that as, 1 here. So you can see that now we have 1 decimal point. But if you want, you can use, for example, like 5, right? So now we will have 5 decimal points. So that really depends on the precision that you're looking for. So I'm going to put that back to 3. Okay, so now let's go to the very familiar example, the math module. We've been using this from lecture 1 in this class, which provides a set of mathematical functions, right? And these functions cover a wide range of operations, basic arithmetic, trig, logarithmics, exponentiation, and more, right? So similar to the time module, you have to first import this. And this means that there is something called math.py. And you can look at the type of this to make sure that this is indeed a module. And now, because in this case, we just imported this math module, you can see that we have to use the dot notation, the name of the module, dot, and then the function that you want to use, right? So that's why we have to use this dot here, because this tells us that this sqrt is part of this math module, and we have to show this hierarchy here. And here we're looking at the square root of 25, sine of 30 degrees, which we first, convert this to radians, because that's how the math.sine expects to get inputs as radians. We look at the factorial, which we, at some point we wrote this function, but obviously this is implemented there. So you get the result that we have. But just to kind of clarify this, let's say for the sqrt function, if you don't want to use this notation, we can say from math import sqrt, and now you can just say sqrt25, and we find these results. So in this case, we do not need to use this dot notation anymore, because we directly imported sqrt from math. So this really depends on you, which like syntax or notation is more convenient depending on the complexity of your projects. The other module that we want to cover here, which is kind of like very important, is this OS module. So this allows you to interact with your operating system, for example, figuring out the current directory you are in, and environment variables, and more. So, for example, one of the functions that we have here inside this operating system module is get CWD, which stands for get current work directory. And so you can see that in this case, if I run this is basically the place that I have included this right now, this notebook. So this is very helpful, because sometimes you may have multiple, directories or folders that you have your files and notebooks. And so you want to make sure that you are in the right place, and you do not really need to use traditional ways of checking these to go through different folders. You can just use this os.get current work directory and get this information. So let's revisit something else that we have used before, like the NumPy random module, right? We are familiar with this when we talk about NumPy data structures. So remember, within NumPy, we have a module called random. So that's how, again, we show the hierarchy, that random is part of NumPy. And this has a lot of functions and classes for generating random numbers, right? For example, using different distributions, uniform, normal, or Gaussian, and also like, random seeding, permutation, etc. So in this case, if you want to use this random module, you have to first import that. And remember, in this case, we have to, again, use the dot notation to explain that random is part of the NumPy. So then we know where to find this module. And we use the type to show that, yeah, this is actually a module. And once we import this, now you can see that we can access to the functionalities that included inside this random module. Like one of them, for example, is this rand_n, right? So again, this is the random module, and you have to use .rand_n to show that rand_n is part of the random module. And in this case, we will generate 5 random numbers according to the standard normal distribution. And this really takes us to the next topic, which is a package. So what is a package? A package is a way of organizing related modules into a single directory hierarchy, right? So think about, for example, NumPy. In this case, you have a random module, you have a module for performing linear algebra operations. And obviously, you can use this as separate modules, but it is really nice if we can put these all together. So now we have another level or another like way of organizing these together. And we call this a package. And also, this is something that sometimes is known as a library. So that's why we called before a NumPy library. But indeed, it's a package, right, which contains these modules inside it. And in order to import modules within packages, you can either use the dot notation that we did before, or if you don't want to use the dot notation, you can use this from package name import module name. So you can see here from NumPy import random, and so this means that now random is defined, and you can say random.randn. But just to clarify, if you don't want to use this from NumPy import random, you can just say numpy.random.randn. So it really depends on, the way that you feel more comfortable with defining these sort of like, methods or functions that we have here. Something else that you have seen before too is that we can use an alias, right? So for example, you can say from NumPy import random, but for the other reason, you don't want to use the name random. You want to use something like, let's say, shorter. And you say that now import this as actually RDM. So this means that you give a new name to random, which is RDM. So from now on, Python understands that RDM refers to random, and random is part of NumPy. And if you run this, you can see that we get the correct result, or what we expected. And the other thing also you can do is that, you can say that like from numpy.random, because this shows the hierarchy, right? It shows that random is part of NumPy. We want to import randn. So in this case, it gets much easier later on because you don't need all the dot notation, right? So you use that once here, you imported this randn, and from now on, Python understands what randn is. So in this case, again, we get 5 randomly generated numbers from the standard normal distribution. But now this gives us also really good opportunity to talk about scikit-learn, right? Because this course, the goal is to talk about machine learning and data science. And the most widely used library or package is scikit-learn, which the actual name in Python when you want to import it is actually sklearn. So that's something to remember, even though it's officially called scikit-learn. The name is sklearn when you want to like import it, right? That's the name that we use. So scikit-learn, again, is a machine learning library that provides tools for data analysis and modeling. It's built on other libraries and packages such as NumPy, SciPy, Matplotlib, which is for visualization. That's the topic of our next video. And so therefore, it provides a very user-friendly and efficient platform. And scikit-learn offers a wide range of machine learning algorithms for classification, regression, clustering. So we're gonna actually go through, these algorithms and the way that we can use scikit-learn for the rest of this class. So that's something that we're gonna go through these things that we're gonna talk about them. But in this video, we want to just kind of like talk about it from the module and package perspective to be able to understand how this hierarchy here works. So as we said, this library or package include modules, right? And these modules are for different purposes, such as data pre-processing, model evaluation, model selection, etc. And so one of the things that, for example, very popular and you need to use when you're working with machine learning and data science problems is this linear module. So inside linear module, you have multiple classes and algorithms that you can use to perform or use linear models for both regression and classification problems. And so the way that this works, in this case, we import NumPy as NP. So that's, importing the NumPy library, and we use alias to just call it NP. And so remember, scikit-learn or scikit-learn is the library or package that we have. So that's like the kind of like the big umbrella that we have. And then inside that, we have a module called linear model, right? So which includes functions and classes that can be used for running linear models. And one of them is this linear regression. And this is something that, you already defined a class to replicate some of the functionalities of linear regression. But if you go to the documentation page here, you can see that in this case, linear regression is a class, like very similar to the class that you defined in one of the previous homeworks, that can be used for performing ordinary least squares, right? So in this case, you can see what are the input parameters that you can have here, some of the attributes, etc. So you can see now the way that this relates to actually object-oriented programming we had in previous lectures. But in this case, you want to very briefly just talk about more like from the functionality perspective. So let's say you have a very simple problem where you have this independent variable x, which contains 1, 2, and 3. And then you have the dependent variable y, which is 2, 4, 6. So in this case, it is obvious that the dependent variable y is simply 2 times the independent variable, right? Because when we provide 1, we get 2. When we provide 2, we get 4, 3, 6, right? So we obviously have y equals 2 times x. And this is called linear regression because this is basically, the way that we look at this is we want to find the equation of a line that connects these two variables, y equals mx plus b or ax plus b, right? Where a or m is the slope, and then the b at the end is like the intercept or y-intercept. So in this case, since we are importing linear regression, the only thing we really need to do is to instantiate this class and create an object. And obviously, we have multiple options when we want to do this. And one of the options is that we can set the fit intercept to be false, because remember, in this case, we know that we don't have an intercept. Y is simply 2 times x. And we just want to find that coefficient or a slope 2 and see if that works. So once you instantiate this class and create this object, now you can use .fit. And what this does, very similar to the class that you defined before, in this case, you're going to find or estimate the slope that we have here that connects y and x, right? So that's kind of like what we call the training in machine learning. And once you find the slope, now if you have a new independent variable, which is 4 here, now we can multiply this slope by this independent variable and find the value of the dependent variable, which is here our prediction. But the nice thing is that this model object that we have here, once we do the training, also has some attributes that we can use to find more information about this model. So in this case, what we are really doing, we want to find what this coefficient here is, right? So as we expected, the coefficient is 2. And since this is a very simple problem, we don't have any noise or any errors here in the data. We can simply find that, well, yeah, the coefficient is 2. And as we said, now if you want to predict the dependent variable for 4, we are going to just multiply 4 by this value that we found here, the slope or coefficient, which is 2, and we multiply them and we get 8. Okay, so in this video, we talk about functions, classes, modules, and packages. So it's kind of important to remember the hierarchy here, right? So we have these smaller pieces that we can combine together and create modules like that primes.py or like numpy.random. And then you can put all of these modules together to find packages or develop packages like NumPy or scikit-learn, or we're going to talk about Matplotlib for visualization. So that's like the hierarchy there. In this notebook, we have 3 homework problems. Just to make sure that I didn't miss that. Yes, we do have 3 homework problems. In the first problem, you want to create a Python file, which is actually a module called math operations. And this is supposed to have 3 functions inside it. So these are the functions that you can add numbers, multiply, take a number and return its square. So these are simple functions, but I just want to make sure that we understand how to create these modules. And once you create this module, you're going to import it, right? And then you're going to be able to, for different numbers, you can perform these 3 operations. So that's what this homework problem 1 is, to create this Python file, put it in the same directory and importing it and making sure that your code works as expected. The second problem is you want to use one of the features in scikit-learn. So scikit-learn has actually a module called pre-processing. So this is for pre-processing your data. And we have seen an example of this, which was actually, this min-max scaler, where you provided a 1D array of numbers, and you want to scale these numbers to make sure that they're always between 0 and 1. So meaning that regardless of what the input values are or the given values are, you want to make sure that the pre-processed values are between 0 and 1. And so we did this from scratch previously, but now you want to use this pre-processing module. So remember, scikit-learn is the package or library. Inside that, you can access to pre-processing. So it's sklearn.preprocessing. And inside that, we have this min-max scaler class where you can create objects. And in this case, you want to provide this 1D NumPy array to this min-max scaler and be able to transform the data and print the result that we have. For sort of like reference here, I have included the link for this min-max scaler. So similar to what we saw with linear regression. So for each class that we have here, we have very well documented web pages that you can go through all the functionalities, what expected in terms of inputs, what you're expected to get from these classes or objects. So that's something that I want you to kind of practice and learn the way that you can read these documentation pages and be able to use them. This is very important because as you start your journey in machine learning and data science, you need to be able to understand these documentations to be able to use them. And the last problem is more or less just writing a function. So in this case, you don't really need to develop a module or package, but it's a good practice because we're going to need this later on. And that's about finding outliers in your data. So one way to finding outliers is known as the interquartile range or IQR method. So in this case, we are using NumPy, and it's and it's provided functionality to find outliers. The idea is very simple. So once you have a set of numbers, you're gonna find the first quartile or Q1 and the third quartile. So this is, obviously something that you can use NumPy's built-in functions and classes to find these. But just to give you an idea, like the first quartile is the 25th percentile. So this means that a number where 25% of the data lies below that number, right? So that tells you kind of like about the distribution of your data. And the third quartile, or Q3, is the 75th percentile, which means that 75% of your data falls below that number. And in order to find these numbers, you can use NumPy's, functions and classes. And once you find this Q1 and Q3, then you subtract them. So this shows you the middle 50% of your data, right? Because the first one is the 25%, the other one, Q3, is 75%. So what you have in the middle is the 50% of your data. And this really tells you the data set's spread. And in order to find outliers, you're looking for those points that fall below Q1 minus 1.5 times IQR, and that's that interquartile range, or above Q3 plus 1.5 IQR. So this allows you to find extreme values and label them as outliers. So in this case, you're going to work with these cell that is provided here to be able to find these outliers in this array of 100 numbers that are generated using a normal distribution. Hello everyone, in this video we talk about using Matplotlib for data visualization and plotting. Matplotlib is perhaps the most widely used library for creating static and interactive plots in Python because it provides a versatile and comprehensive set of tools for various types of plots. This includes line plots, scatter plots, bar plots, histograms, and so on. And therefore, in this video, our goal is to show you the basics of using Matplotlib. And so once you learn this basic, you will be able to apply them to different types of plots that you may need based on your application. And the nice thing about Matplotlib is that you have complete control over the appearance of plots. For example, customization of colors, styles, labels, and annotations, as we're gonna see in this video. In order to use Matplotlib, the first thing is to import this library. Since we talked about modules and packages in the previous video, we have here this Matplotlib package or library. And inside this, we have a module, which is called PyPlot. And therefore, the goal here is to import this module from this package or library. But it is very common to also use an alias. And here we import this as PLT. So therefore, we really shorten this name that we have here to make it much easier later on. So PLT refers to this module. And then we say PLT. And one of the things that you will definitely need is plt.plot. And this is what is known as the line plot. And here we give a list of 5 numbers. And we also specify the marker type. We're going to talk more about marker type, but for now, it kind of makes sense that these are the markers that we're going to use to plot these data points. So let's run this cell and see what we get. And something before I forget is that you also have to use plt.show to make sure that you actually show the plot that you have. So this is something kind of like, important, kind of like, when you're using print and then some string to make sure that you print that string. That's kind of like a similar thing when you're using Matplotlib. And so you can see that here, now we have these 5 data points that we have, 10, 20, 30, 40, and 50 on the y-axis or the y-coordinates of these 5 data points. But the strange thing is that the x values are 0, 1, 2, 3, and 4. So you may ask how we got these numbers here. So remember that when you're using plt.plot and provide, let's say like here, a Python list, what really happens in the background is that your x values are the indices of the elements in this list, right? So we have these 10 through 50, but we know that the indexing in Python starts from 0. So the first element is at index 0, then index 1, 2, 3, and 4. And plt.plot assumes that the x values are these indices. However, if you want to provide a different set of x values, you completely have this option to provide two lists. And so this really, I would say, makes much more sense because now you have one list where you get the x coordinates, and then you have another list where you get your y coordinates. So this is very intuitive, the way that we actually, plot 2D data points on a piece of paper, right? So we see that for the first point, the x value should be 1, the y value should be 10, and that's exactly what we see here, 1 and 10. And then for the second element, we have 2 and 20, right? So we get 2 and 20. And in this case, we obviously can change these lists however we want to get different set of x values. So we have the option to change both x coordinates and y coordinates. Okay, so now we learned the basics of plt.plot for line plots. Now, let's talk a little bit more about customization. So one of the things that we can use is plt.axis function in Matplotlib, which is used to set the axis limits for the x and y axis of a plot. And so the general syntax is that we say plt.axis, and then we provide a list where we have xmin, xmax, ymin, and ymax. Right, so these are the min and max values for each axis. So we're going to have the same plot that we had before. And let's say in this case, for some reason, we want to make sure that the x values that we show on the plot are from 0 to 6, and the y values on the y-axis are between 0 and 60. So if I run this right now, you can see that on the x-axis, we have 0 to 6, and on the y-axis, we have 0 to 60. In this case, obviously, it makes more sense to set this the minimum value to be 1, because we don't have any plot for anything less than 1, and the same thing for the max value to be 5, and for y-axis to be 10 through 50. And if you run this now, you can see that we get a really nice plot where we do not have any empty spaces, right? So that's why one of the reasons you want to use this plt.axis. If you have some empty spaces around your figure and that's something you don't want to have, then you can make sure that you can manually adjust the min and max values for each axis. And this is the syntax to perform this. Okay, so now let's go to the next step. Let's say we want to plot a quadratic function. And in this case, a quadratic function is y equals x squared, right? X raised to the power of 2. The first thing that you need to do is to define a grid for the x-axis, right? So in this case, x is technically your independent variable, and we are using np.linspace to have 500 data points equally spaced from -2 to 2. So obviously these are the x min and x max. You can adjust them as you want, but in this case, we want to have a plot from -2 to 2. And we have 500 of these data points. And then in the next line, we're going to raise each x to the power of 2 and store the results in this NumPy array called y. And therefore, when you want to plot this, remember the x values are given through this np.linspace. So this is the independent variable. And then the y is x squared, which is the dependent variable. And you use the plt.plot. There are also some other options you can use for customization, such as giving labels to axes. So plt.xlabel. This shows this string as the label for the x-axis, similarly for the y-axis. And also we can even use plt.title to put a title above your figure. For example, here saying that this is we're plotting a square function, which is y equals x squared. As we said before, we can use plt.axis. We know here that the x values are from -2 to 2. And since we know that we use, the x squared function, so the y values are also from 0 to 4, right? So we don't get any negative numbers because we are using this quadratic function, but the max would be 4. And if we plot this right now, so you can see that on the x-axis, we have values that are from -2 to 2. And then we have on the y-axis from 0 to 4. You can see the labels here. You can see the title here. And this is definitely the quadratic function that we know. If you want here, you can also use marker to better see the data points that we have. Obviously here, it's hard to see them because we have 500 of them, so they're very, very close. But if I use that, you can see that now this looks much thicker, this curve, than before. And that's because we have all these markers that are so close to each other. So for example, I can decrease the number of data points to 10. And if I do that, so you can see that now how this works. But this doesn't look very smooth because we only have a few data points, right? So you can always increase these, let's say 20. So this should be better, and so on. So now you can see that we have all these XY coordinates that this line plot connects them together to get the shape of this x squared function. We can also add more customization. One of them is using this option called line style, and the other one is color. So here we have the documentation for both of these customization options that we have. So you're more than welcome to look at them and figure out different options that you have. But as you can see here, one of the things is to set the line style. And I set that to be dashed. So this is going to be a dashed line. And also the other one is color, right? So there are multiple options for color, like red, blue, green, etc. And also like before, we have the labels for axes and the title. And you can see that when I plot this right now, so you get this dashed line. And the color is red, right? So if you want to change this, let's say color to green, you can do that, or blue. So this gives you a lot of different ways to customize this. And as you can see, just to make sure that you see this, since here for this plot, we didn't use plt.access, you can see that we get some empty space below this sort of curve, and also for values more than 4, right? So if you want to get rid of that space, we can use what we had before by providing those limits, right? So we say that for x, we have -2 to 2. For y values, we have 0 to 4. And if we run these, now you can see that we got rid of those empty spaces. So this is sometimes preferable because you want to make sure you have very nice figures. And then the other thing is about the marker type, right? So this is something that you have seen. This is the way that we represent these 2D coordinates or data points, but you can choose different types of markers. So far we have been using what is called O, that represents a circle, but also we have other options too. So if you use S, that stands for a square. If you use uppercase D, that stands for diamond. You can also use this notation for upward triangle. So you can customize this as you desire. So here we use S. So you can see that we have these S squares. But I can use, for example, this upper triangle if I want to. But I'm going to move this back to a square. And something also to keep in mind here, I can take this to the next line that you can see. You also have an option for marker size, right? So if I use 50 instead of 5, you can see that now these markers are huge. Let's put something more reasonable. So I put like 10, right? So now you can really see these markers very well. But depending on application, you might want to choose them a little bit smaller. but you have a full control over all these options. The other nice thing about Matplotlib is that you can have multiple plots in one figure. And in this case, you can visualize all of them inside one figure, which can be very helpful when you want to save a space. So let's look at this example that we have here, that we have these x values that, like before, we have from -2 to 2. And in this case, we define three functions. One is a linear function, 2x plus 3. Then is a quadratic function, x squared plus 2x plus 1. And then we have a cubic function. And so the way that you can have multiple plots in one figure is that use this plt.plot as many times as you want with different set of xy coordinates, as you can see here. But in this case, something which is very important and recommended is to use this label argument where you provide a label for this plot. So the first one is linear, the second one is quadratic, the third one is cubic. And now, like before, we can add X label, Y label, title, but something which is very important in this case is to include this plt.legend. And if I run this cell, we can see that now we have these three plots, and we have this box here. So this is what is called the legend, which has the information about those labels that you provided, like linear function, quadratic, cubic, right? Linear function, quadratic, and cubic. Therefore, in this case, it's always important to provide these labels. It's not mandatory, but otherwise it's impossible to figure out which plot corresponds to which function here, right? So you need to provide these labels. The next thing that we're going to talk about is how to save a figure in Matplotlib. And in order to do that, you can use plt.savefig function. And there are two things that you need to provide when you're using plt.savefig. You need to provide the name for this figure that you are saving, right? That's very intuitive. And then the other one is this DPI, which stands for dots per inch. And this really determines the resolution or quality of the saved figure by how many dots or pixels should be used per inch. So the higher the DPI, the higher quality is the saved image. So like before, we create these x values from here, -5 to 5. We're going to find the corresponding y values using this quadratic function. We're going to, even in the case of one plot, you can add the label and plt.legend, right? So that you don't necessarily have to have multiple plots. You can do this only with one. Something you can always use when you're saving your figures is use this plt.height layout. So it is very hard to exactly characterize what this does, but it improves the overall layout or quality of the plot. So you make sure that all the empty spaces and everything else looks nice. And so that's something that also recommended to use. But the point that we want to make here is this plt.savefig, where you provide the name of the file that you want to use to save this figure, and then use the DPI. So usually you want to have DPI more than 300. In this case, I'm using 600 to have even a better quality image. So you can see that in this case, we have our quadratic function as expected. And now if you look at the current directory or folder that you have, you should be able to see this PNG file. So please make sure that you look at the current folder directory to see whether you have this file or not. So it should be something called, in this case, this name.png, and you can also try to use different DPIs to see the difference between their resolutions. Okay, let's talk about more customization. So the other thing you may want to do is to adjust the font size. So one of the things that you can do is to globally change the font size. That's done using plt.rc-params. And here you set your font size to anything you want. You also have the option to do this like, for each individual like customization. For example, for the title, you can change the font size. For X label, Y label, legend, so you can manually change the fonts if you want, or just change the font for everything in your figure using this global font size approach. You can also adjust the figure size that you have using this plt.figure, and you provide this fixed size where you have the width and height of your figure. Just to show these points, so you can see that here we have this plt.figure to set this figure size to be width 5 and height 4. And then the other thing also that we have here, we are using these font sizes here, right? To give them different font sizes for the title, X and Y label, etc. So if you run this, so you can see that now we have a figure that looks overall in terms of its width and height is smaller than what we had before. And that's just because of this line. So you can see that if I, let's say, change this to 3 by 3, and run these, now we get something even smaller, which is probably too small for these font sizes that we have here. So let's put this back to 5 by 4. So now you see that the overall dimensions get a little bit bigger. And you can also change these font sizes. So if the title is too large here, we can set this to be something very small, like 10, right? So you can see that now the title, which is this one, is a small. So let's put this back to some other number. You may see that, oh, the legend is too large. So we can adjust that, right? So now the legend is small. So you have the option to change all these font sizes depending on the overall size of your figure and also other requirements. Now let's look at subplots. So for subplots, it's very important because sometimes you may want to have multiple plots in one figure. And sometimes you want to have multiple plots next to each other. Like you can create a grid where you have, let's say, a 2 by 2 grid where you have 4 figures and each one in one of those locations. And in order to do this, the most common way of doing this is using this plt.subplots, right? So this is the first time that we are moving away from plt.plot, right? So now we can use plt.subplots. And the syntax is easy. So you need to have the number of rows, number of columns, and optionally, you can provide the figure size or fixed size. Obviously, you can change it later, but you can also adjust it right away. And in this case, what we really want to work with is this axis. So as we say here, this is kind of like a NumPy array, which has this indexing system that starts from 0. So let's see how this works in practice. Let's say you want to create a grid of size 1 by 2, so 1 row, 2 columns, to have these plots individually next to each other. So in this case, we can change the font size that we discussed. But what's really important is that once you create this axis, now you can have axis 0. So this shows you the first place that you have in the grid. So right, we have one on the right, one on the left. So this is the one on the left. And you can use now axis 0.plot and provide the XY coordinates. You can also give the label. It's a little bit different in terms of the way that we provide X and Y labels, right? So before we said like plt.x label, now here you said set_x label. That's like a minor difference, but this is just something that you can always just remember, like the difference between subplot and a regular plot. Some of the things are similar, like that legend to show you this label that we have here. And then for the second plot that we have here, the one on the right, now we can use this axis 1. And so now we plot the linear function, etc. And if I run this cell, you can see that now we have 2 plots. So it's a 1 by 2 grid, 1 row, 2 columns. The one on the left is the quadratic function. So this shows you what, how we get this quadratic function. And then for the one on the right side, or the second position, which has index 1, now we have our linear function. So this depends on the application, whether you want to create a grid and have multiple plots individually, or you want to have all these plots in one figure, right? So it really depends on your application. And the nice thing here is that you can really choose any number of rows and columns. Okay, so in Matplotlib, you can also draw text on your plots to add more information. This is something very important when you want to convey some important message. And one of these options is using plt.text, which is very simple to use. You provide the XY coordinates of where the text you want to be placed. S is the string that you want to show. This is the text string. And you also have options like font size, color, the horizontal adjustment, vertical adjustment, etc. So those are, optional arguments. But just to show you how this works, so let's say we have this line plot where we have these X values, we have these Y values. Obviously, the maximum value happens at this point where we get 20 for the Y value and 3 for the X value. And so if I run this cell, you can see that we have our normal plot, right? So we have our X-axis, we have our Y-axis, and this is where the maximum Y value happens. And you want to show this text, which says max value. So in order to do that, that's the code that we are going to use. So we're going to say plt.text. We want to choose the X value to be 2.6, right? Because we don't want to put this like a string right on this point. We want to be able to see this. So we put this at 2.6, and the Y value is obviously a little bit less than 20, so it's 19. And this is the message that we want to show. So if you want to change this, you can, for example, add max value 1. So you can see that this one now is added, but we can remove this. You can adjust the font size and everything else. So that's one way of adding annotation or text to your plot. But if you're looking for something a little bit more sophisticated, you can use plt.annotate. And plt.annotate is a function that you can add annotations. And the main difference is that you can also use some arrows to exactly point to the points that you want. So to a specific locations of the figure. And the syntax is a little bit different. In this case, first, you provide the text string to be displayed. Then you want to provide the XY coordinates of the point that you want the arrow to be pointing towards it. And then the XY coordinates for your text. And also you have some options for the arrow that you want to plot. So just to show the difference, here we have exactly the same setup, but we have this plt.annotate. And you can see that first you put your message, XY coordinates for the data point. So here we are trying to have an arrow that points towards 3 and 20, which was like the maximum we wanted to show. The XY for the text, and some information about the arrow, such as like the arrow should be blue and things like that. So you can see now in this case, right, so we get a little bit a better visualization. So we can show that, okay, this is the max value that we are talking about. And, before we just wrote max value next to it. So it wasn't necessarily super clear what point we are referring to. But in this case, it's much easier. Okay, so let's talk about now 3D plots. Creating 3D plots in Matplotlib is something we can use to visualize data points in three-dimensional spaces. This is obviously something that we are not going to use as much as 2D plots, but I wanted you to have at least the instructions for creating these 3D plots if needed. And so it's here we have the full instruction, but I can show you in the code the main differences. So one thing that you have to do for 3D plots, you have to add this line. So there is a package or library called MPL toolkits. So inside this, we're going to use this axis 3D. So this is what we need for creating 3D axis. We're going to create the data. So here you need to have three coordinates, right? Like X, Y, Z or X, Y, T. So that's how we create it. We use some sine and cosine function, and T is the independent variable. And then very similar to before, you can use plt.figure. And in this case, you want to, once you create this figure and assign it to the variable fig, you want to add this thing called add subplot. And you want to make sure that the projection is equal to 3D. This font is just for the font size, as we know. And then the main difference is that you take this object x and now say x.plot3D, and you provide the x, y, z coordinates. And after this, everything is very much the same as before. You can set the X labels, you can use tight layout, you can save the figure. And something else that is also important is to use this view init. And this shows you the viewing angle. So using the elevation and azimuthal angles of the view, right? So you can really change the perspective you're looking at this 3D plot. So in this case, you can see that we have this nice 3D plot, right? So we have this t variable, and then x and y are defined using sine and cosine. That's why we get this very nice 3D plot here. And if you want, for example, to look at this from a different perspective, you can choose this elevation, for example, to be 0. So now you can see that elevation is 0, and you can increase that to be 20, or even increase that to be 60, right? So now we are going to look at this from above, right? But I'm going to put this at 20. So the full instructions is here, that how you should do it, adding this add subplot, then using xplot3D, and also this view init. The next type of plot that we're going to cover is a scatter plot. So scatter plots and line plots are both used very frequently to visualize data, but they serve different purposes. And the main thing about the scatter plots is that they can be used to visualize the relationship between two variables. And instead of connecting them together, data points here are represented as individual markers. So in this case, you can see that like before, we have a set of x values and then y values, and then we use plt.scatter. We have the x, y values. So these are the x coordinates, y coordinates. And s here is the marker size. So before we use the argument marker size, now we use s. And still you can choose the marker type and the color, which is shown here by the c variable. And you can see that in this case, right, so we have one data point which has x value 1 and y value 10, right? So we have 1 and 10. That's the first one. Based on what we see here, the next one is 2 and 12. Let's see if that's correct. Yes, 2 and 12. And then next one, 3 and 8. And you can see that here we are not connecting these together. It's just visualizing the relationship between them. And to see, how this works, especially in the context of machine learning and data science, let's look at a real-world problem, which is known as iris flower dataset. And this dataset has 4 measurements of iris flowers and are categorized into 3 species based on those measurements. And you can see that in this case, in order to access this data, we can go into scikit-learn. Inside scikit-learn, there is a module called datasets. And from that, we're going to import load iris. So this is the way that we can load the iris dataset. And then inside that, we have the actual features for these iris flowers and the target values, and also the feature names. So if you look at this data, once we get this, so you can see that now each data point has 4 features because we have, 4 measurements of each. And then we have the targets for them. So this shows us all these 5 data points belong to class 0. And if you're wondering what those 4 features are, for example, 5.1, 3.4, 5, 1.4, and 0.2, these are the names: the sepal length, sepal width, petal length, and petal width. So we have 4 features or measurements per sample. And this is sample 1, sample 2, sample 3. So that's usually how we store and access data points when we have these types of data sets. But what we want to more focus on here is that if we only select 2 of the features, right? So the feature 1 and feature 2 across all the samples, right? Can we see interesting relationships in the data? So what we do is that we say that we want to look at the first 2 features, which are sepal length and sepal width, index 0, index 1. And then we are also going to distinguish between different classes, right? So we write a for loop so that we have now 3 different scatter plots inside one figure. And the way that we can do this is by putting this condition that each time we're going to plot only data points with the values of target values that are equal to this class label, which is 0, 1, and 2 here, because we have 3 classes. And then you have the X feature, which is 0, Y feature, which is 1. And also we're going to add this label where we say now this is a species 0, 1, and 2, depending on what this class label is when we have this for loop. So if I run this, so you can see that now on the x-axis, we have sepal length. That's why it's so important to add x label and y label. And then on the y-axis, we have sepal width. And these are the xy coordinates for data points from different species or classes. So here we have 3 species. You can see, for example, we see a clear distinction between species 0 in terms of their sepal width and the sepal width for the other 2 classes, right? The sepal width for the blue class is definitely higher than the sepal width for the other classes. So you can easily now draw a line here to separate this blue class from orange and green. So that's why scatter plots are very important in machine learning and data science. The last type of plot that we're going to cover here is histogram plot. And histogram plot is also very popular for statistical data analysis, which is used for graphical representation of the distribution of a data set. And the way that this works is that we use plt.hist, so that stands for histogram. Usually we provide a 1D array here, and this is the data to be histogram. You can provide a sequence of arrays too if you want to plot multiple data sets, but in most cases, make sure that X is just a one-dimensional NumPy array. And then you can have the number of bins, right? So you're gonna, divide these values that you have, all the values in X, into different bins, and you're gonna count the number of data points that you have in each bin. So you find kind of like a frequency plot. But something which is really cool about Matplotlib's histogram, you also have this density option where you can set that to true. So by default it's false. But if you set that true, it actually returns a probability density. And what does this mean? Is that in this case, each bin will display the bin's raw count, like how many values fall into that bin, divided by the total number of counts and the bin width, so that what you get at the end has area under the histogram, which is exactly 1. So this is something very important if you have had if you have seen probability density functions before, because probability density functions, they have this property that the area under them is 1. So that's kind of like a nice way of normalization. And so if you set this density to be true, then the y-axis wouldn't be just the raw count, would be this type of normalized raw count, such that the area under this histogram plot would be 1. So you can find more information here at matplotlib.pyplot.hist. But here we're going to see a few applications of these. So let's, in this case, generate a 1D array. using np.random.normal. We know that this is the normal distribution generator in NumPy's random module. Log or LOC is the mean, the scale is the standard deviation, and size is the number of samples that we select. So if you look at data right now, if I run this, you can see that data has 1,000 elements. You can use, for example, .shape. So you can see that this is a 1D array containing 1,000 elements. And so what we do here when you use plt.hist, you provide this data, you provide the number of bins, and I personally like to put the density equals true, because now the nice thing is that the y-axis is this sort of like, normalized version, where still you can see that based on what we see here on the x-axis, we have values. So because we created random numbers from a normal distribution with mean 0, this is definitely centered at 0. And then this is the standard deviation or spread of the data. And you can see that in this case, that if we find the area under this, histogram plot, it should be 1. Whereas if I set this density to be false, right, you just find the raw count. So, right, this means that out of those, 1,000 data points, 160 of them, almost more like 150 something, are from like 0 to whatever this number is here on the x-axis. So I personally like the to put the density equal to true. So in that case, we find a more normalized version. It doesn't matter if this is 1,000 or 500. You get more consistent results, right? Because we do not have a raw count. The other thing you can, for example, here do is to increase the number of bins. So if you see like I increase the number of bins, now we have 50 of these bins here, but it may look a little bit less smooth. So that's why you don't want to increase the number of bins too much. You can reduce it if you want. So you can see that now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 bins. But I think in this case, like 20 looks, relatively nice. If, for example, let's say I increase the scale or the standard deviation, we expect that the spread of the data should be also increased. And you can see that that's the case, because now when I use a standard deviation 10, these numbers can go from as low as -30 to almost 40, right? Whereas if we set to 1, like before, you can see that they're from -3 to almost 4. So that's something that you can use. Obviously, there are some other options here too, like the color, the edge color. You can see that here the edge colors are black, alpha, right? So this is something, as you make this closer to 0, you get more transparency. And as you get it closer to 1, it gets kind of like darker. So that's something you can adjust as you wish. So that's the histogram plot, but let's do something interesting here. So for example, for the normal distribution, we actually know the probability density function. And that's something that is already inside this library or package called scipy. So scipy is similar to NumPy, but it has some more functionality and statistical methods. And inside scipy.stats, right? So that's the module. We have something called norm. And inside this norm, you can use this method or function called PDF, which generates the PDF, right? For the normal distribution with a given mean and a standard deviation. So what we want to do in this case, we want to create our data from this normal distribution, and we sample 1,000 of them. We use plt.hist to provide a histogram, but now we also want to plot the PDF or probability density function of the normal distribution for comparison to see how consistent they are. In order to do this, we're going to use np.linspace from some mean and max values. And we get the mean and max values from plt.xlim. So this tells us the mean and max values that we have on this x-axis. And then we're going to pass these x values to this norm.pdf. And in this case, because we assume that we don't really know the mean and the standard deviation of the through normal distribution that we have, we're going to use the empirical mean and empirical standard deviation. So we just use the data that we have, these 1,000 samples, to find their mean and the standard deviation, and we pass here for this probability density function. And we're going to, at the end, plot this probability density function. So you can see here, now we have our histogram plot, and in the same figure, we have now this probability density function, this bell-shaped curve shown in red for the probability density function of a normal distribution with this mean and this standard deviation. So if you run this, you can see that the mean here is close to 0. So remember here, this is empirical mean, not the true mean of the data. Therefore, we may not exactly get 0, but we would say that this is close enough. And then for the standard deviation, we expect that to get something close to 1, which is 0.97. Obviously, if you want to get better and better estimates, you can always increase the sample size. So for example, here we can increase that to be 10,000. You can see that now we get something that really looks like the PDF for normal distribution. And if I look at the standard deviation of this new data with 10,000 samples in it, you can see that, yes, it is really close to 1. And for the mean, it should be very close to 0, which it is, right? So it's negative 0.002. And this shows very easily here that you can see that we get something very close to the ideal probability density function of the original normal distribution. So in this video, we covered multiple types of plots using Matplotlib, line plot, scatter plot, histogram plot, and so on. And I hope you found this video helpful. Hello, everyone. In this video, we talk about a very important data science library known as Pandas. A Pandas data frame is built on top of NumPy arrays, providing a more flexible and labeled interface for working with structured data. So to see the connection between Pandas data frame and NumPy arrays, you can think about it through this very simple example where, let's say we have a 2D array where we have in the first column information about age and in the second column information about city, right? So we have a data set where we have 3 rows and 2 columns. And in this case, let's say that the first row corresponds to Alice, the second row Bob, and third row corresponds to Charlie. So in NumPy array, we don't really have a good way of labeling, and we usually have to resort to the standard indexing in Python, which means that, well, the first row is index 0, the second row is index 1, and then the third row is index 2, and the same thing with the columns. But what is really helpful if we can actually label this data set or this 2D NumPy array. And in that case, we can create an object which is called a Pandas data frame. So as you can see here right now, this is very much like an Excel file or a spreadsheet where we have these labels for each column. So we know that the first, for example, the column here, we have this name label and then age and then city. And also for each row, we have these names. So this means that if you want to retrieve information about Alice in this, data set that we have or data frame, we know that we can just call the name, right? And remembering that Alice corresponds to the first row of this, NumPy array. So that's why we really want to use Pandas data frame in data science and machine learning problems, because it makes it much easier to be able to access information, filter information, and other things that we're gonna very briefly discuss. So as we just discussed, each column in a data frame can be considered as a one-dimensional NumPy array, right? So for example, here, the age column, you can see that this is actually a 1D NumPy array, which contains 3 values, 25, 30, and 35. And therefore, the entire data frame is a collection of these 1D arrays, right? So you have these collections of these 1D arrays for each column, where we put them all together. Now we get the Pandas data frame. And as mentioned earlier, each column in the data frame has a unique name. So that's like very important here, this labeling process, which allows for easy identification and access. But sometimes we want to also access information in the rows of this data frame. They also have labels, as you can see here, and we call these, in this context, mainly an index. So index is what we use for the labels or names that we use for the rows, and for the columns, we just call them column names. So let's just get started with the first data frame. And in this case, we are going to first create a NumPy array and then use this method, which is called .dataframe, to convert this NumPy array to a Pandas data frame. So in this case, the main thing that we have to do is to import Pandas. And it is common to use an alias. We use import Pandas as PD. We use import NumPy as NP, so you can see that we are building on the libraries that we know. So now we know very two important libraries, NumPy and Pandas. We also know about like Matplotlib, so we are getting to know more and more libraries that are helpful for data science. And in this case, as we said, we want to create first a 2D NumPy array. So you can see that now we're going to have 3 rows and 4 columns. And to emphasize this, if we have just this NumPy array, now we have to remember what each row and column corresponds to here, right? But the point that really is important to consider is that when we use Pandas data frame, and that's what we are doing here, we are trying to convert this 2D NumPy array to a Pandas data frame, we have to provide these column names and also these index labels that we have, right? So remember, index here is technically what refers to the rows. That's what the official terminology that we use. So this means that because we have 4 columns, we need 4 column names: math, English, science, and programming. So these are, let's say, 4 courses that each student can take. And then the index here is a list of 3 elements, because we have 3 rows: a student 1, a student 2, a student 3. We can, provide any strings here, but that's what we have used in this case. And at the end, I'm going to just print what's inside this data frame. And you can see that this is exactly what I showed you earlier, right? So you have this nice data frame with the column names and these index labels, right? That's what we call them, these index here, what shows what these rows are. Okay, so now let's say we are given this data frame and we want to access data that we have in this data frame. So let's say you want to find out the grades for all the students in the math class that we have here. So in this case, you can use df and then the name of the column, right? So here basically would be df, and the name of this column is math, and we can access this full information. There is another way of doing this too, which is this dot notation, df dot, and then the column name. I definitely recommend you to use the first approach, where you just use these square brackets and column name or column name. So you can here also provide a list of column names if you want to access more than one column. So as you can see here, if I use df math, you get 85, 92, and 78, right? So these are the scores that we have for this math class across all rows, or here students. And if you want to retrieve 2 columns, now we provide this list of the 2 column names, and you can see that we get this information for math and English. The other thing is that sometimes you want to access a row, and in this case, you have to use the index for those rows. with this method, which is called df.lock or LOC. So that's the difference between accessing rows and columns. For accessing columns, you just use the name of the data frame, a square bracket, the column name. But if you want to access a row, you have to first say whatever the name of the data frame is, .loc, and then you provide that label index. So as you can see here, if I want to retrieve grades for a student 2, then I can use df.log a student 2, and we get this information 92, 88, 95, and 75. Remember, what we have here is just a subset of this data frame. So when you say df.log, we actually have to look at the df data frame, which is this one. So you see that that's why we get this 92, 88, 95, and 75. So sometimes you want to also do a data manipulation, for example, add a new column to a data frame. And this is very easy. You just need to use df and the name of the new column that you want to create, right? So there's nothing called total before, but let's say we want to add that information. So you just say that, well, I want to have this new column. And in this case, you have to assign something to that new column, right? So we are saying that we want to use df.sum access 1. So what does this do? Remember that, when we are working with multidimensional arrays, we have something called an axis, which shows the direction that we have the information. And so very similar to what we have in NumPy. So axis 0 is this axis, and then so this is 0, and axis 1 is this one, right? So if you want to find the total sum for each student, so you want to perform this summation across the rows of this data frame. So that's why we have to use axis equals 1. So that's something that we inherit from NumPy. So we use the same indexing for axis. So based on that, now we can go back to the cell where we wanted to find this sum. And you can see that when I print this data frame, so you can see that we get the sum of these 4 numbers in this new column, which is called 345. And then similarly for the other rows here. So the nice thing is that you don't have to apply these individually. So you can just say that I want to add all the elements in each row and assign the corresponding value to this new column, which is called total. And so now that we created this, let's do something interesting. And let's say that we want to sort these values in this column, which is called total. And in this case, we can use this built-in method, which is called sort values. So when you say the name of the data frame dot sort values, you can use the syntax we have here. So the first one is by, which is the column that needs to be used when you want to sort these elements of this data frame. So here you want to say that I want to sort these students based on their total score. You can do this based on their math score or any other sort of like columns you want here, but it makes sense in this case to do this based on the total column. And then the axis by default is 0, which means that you have the vertical axis because we want to sort them based on this information that you have in this column. And then you can also decide if you want to do this ascending or descending. So by default, ascending is equal to true. We set this ascending to be false, right? So if you see when I run this cell, what's happening here is that now these grades are actually, because ascending is set to be false, now they are in descending form. So meaning that you have the highest number first, which is 351, and then you go to the lowest, which is like 345. So this is very helpful if you want to just visualize if you have a large data set and you want to see the distribution of data in a sense from maximum to minimum. You can sort this as students, right? So student 3, based on what we have done, has the highest score based on all the courses that we have here. But something else that is important here, you can see that once we do this sorting, if I again print the data frame, you can see that we lost the sorting that we have. And this is a very important concept when working with data frames, is that some operations are not going to be permanent. And the terminology we use for this is in place. So in place equals false here means that this sorting does not change the original data frame and it just creates a copy of that. But if you want to perform this in place, meaning that by setting in place equals to true, then this means that the original data frame will be modified. And therefore, from now on, whenever you have data frame here, you can see that, you will get this one that we have here that is sorted, not the original one. So this is kind of like your preference, whether you want to modify your original data frame. In many cases, it's better not to do that because you may need the same ordering as you received before. But in general, you have the option to decide whether in place should be false or true. So here you can see the information about all these parameters that we have in this syntax. The other important thing that we want to do with data frames, because in general, you may have a lot of information about different students, users, depending on what the data frame is about. And you want to just look at a subset of this data frame, right? So again, let's go back to our example. And let's say for whatever reason, you only want to include students in your analysis that they have received more than 90 in their math class. And so in this case, what we can do is to use this comparison operator, saying that I want to look at this column, which is the math column, and see whether it's greater than 90 or not. So in this case, you can see that we should get false, we should get true, and false, right? Because only the student 2 is the one that has a score greater than 90, and the other two ones are below 90. And so very similar to, again, what we did before with Python lists or NumPy arrays, you can use these Boolean values to do indexing. So this means that if I just use these Boolean values that I received before inside this data frame, so use the name of the data frame, a square bracket, and what you get here, these Boolean values, this will, in this case, understand that you want to only keep the ones that are equal to true, which is only the second row. And you get this information about a student 2. So again, this is a very simplified case, but you may have hundreds of thousands of rows in a data frame, and using these can easily filter this data frame without you going through them individually. So it's a very helpful strategy to use this type of indexing where you put some condition on one of the columns, or it can be more than one column too, and then you feed that again to the data frame to select the ones that are equal to true. There are also a lot of more functionality here. For example, one of them is this df.plot. So in general, we learned about Matplotlib in the previous lecture, and you can, select the data that you want, convert that to a NumPy array. We're going to talk about this very soon and use Matplotlib. But the point that really here is important is that data frames also come with some plotting options. And you can just say like the name of the data frame, dot plot, and then the kind of plot that you want. So you want a line plot, bar plot, a scatter plot, histogram plot. These are things that we talk about it in the, in the Matplotlib data visualization lecture. But if you don't want to directly use a Matplotlib, there are some functionalities here for visualization in data frames. And you can see that here we are saying that I want to plot the data frame and I want to use the bar plot. And I call this, you can provide a title to a student scores. So you can see that in this case, we get this very nice plot where for student 1, we have the grades for each individual course and then the total. So this can be very helpful because you do not have to do this manually. So it's kind of like a very low code approach. You can also create other plots too. For example, a scatter plot. Remember with the scatter plot, you need to have X and Y values because you have 2D coordinates. So in this case, we want to say that on the X-axis, I have math scores, and the Y-axis, I have science. And so you can see that in this case, we get 3 data points. Each data point, you have the math score and the corresponding science score, right? So that's something can be very helpful to visualize the relationship between grades in these two classes, right? Is there any relationship between your math score and science score? The other thing that is kind of important to understand when working with data frames is handling missing data. And in general, for missing data, we use nan or not a number or null values. So this shows that there are some missing values. So for example, let's say for some reason you do not have information about one of the students' grades. So in that case, you cannot just put 0 or some random numbers. You have to have a very specific way of saying that, well, this number is missing, and that's why it is not a number or null value. And in order to check whether you have these null values, you can use this dot is null or is an A. And also then you can, on top of that, you can use dot sum to find the count of missing values. So let's create this example where we have a data frame with 4 columns and 3 rows. So I intentionally use this example to show you that in order to create a data frame, you can actually use a dictionary. So this data right now is a Python dictionary where you have this key value pairs. And if we just convert this to a data frame, you can see that each key here now is a column, right? So A is now the first column, B and C. And these values here are basically the values that we have in the rows. And since we don't have any index labels, there are the default indexing, which is 0, 1, 2, 3. But you can change this if you want, right? And provide the index labels. But for now, let's just use these. And for nan, you're using np.nan. So if I use df.isNull, you can see that we get true wherever we have a missing value, right? Like similarly here. And we get false when we do actually have some values. And the same thing with is and a, right? So that's, you can see that it's the same thing. And so if you want to now find the total count of missing values per column, you can see that now you can use dot sum. And this tells us that we have 1 missing value, right, in column A, 1 missing value in column B, and no missing values in column C because they're all false, right? And this is because when you have summation applied to Boolean values, false is equivalent to 0 and true is equivalent to 1. So adding these numbers will tell you the total number of trues or missing values that you have. And in general, when we go to like machine learning and statistical methods, in many cases we cannot fit these missing values to, like, let's say a machine learning algorithm, and therefore we need to either drop them or fill them with some other values. And one of the approaches is to use this drop and A. You can see that in this case we have this data frame. If I use drop and A, we are going to remove the rows that they have missing values. So this row with index 1 has a missing value, so it's not here anymore. And the same thing with this one, right? That you have a missing value, and so it's gone. And so we only keep the first and the last row in this case. This is more common to do this row-wise because we want to get rid of samples that they have missing values. But if for some reason you want to remove columns that they have missing values, meaning that column A and column B, then you can change the axis. And remember, axis again is very much like we had in NumPy. Axis equals 0 is the vertical axis, and axis equals 1 is the horizontal. So in this case, you can drop the axis 1, and you can see that we only keep column C. But remember, all these operations by default do not modify the original data frame, which can be a good thing because you may want to know exactly where you had missing values, or if you want to use the other information that you have for each sample. And therefore, in this case, what we used did not modify the original data frame. The other option to handle missing values is to fill in these missing values with either a specific value, right? If you want to exactly, for example, here say that, well, anywhere is missing, just you fill that cell with value 4, right? So you can see that now we have 4 here and 4 here. These are the missing values that we had to just show you. Or you can use actually like some more advanced operations here. For example, you can say that I want to use the mean or average of samples in each column to fill these missing values, right? So you can see that in this case, this was our missing value, and now we have 1, 2, 4. So if we add all those numbers, we get 4 plus 3, which is 7, and then divide by 3, which should be this number, right? So that's how you fill this information using the average values of non-missing values. The other operation that we can use when working with Pandas data frame is something called group by. And I think this really tells you what this is. So this is used for grouping rows based on some criteria and then applying a function to each group independently. So the syntax is relatively simple. You use df.groupBy, and then you provide this by argument. So this is very similar to the case where we wanted to do like sort values, right? We had to provide the column for that. But in this case, this is a column that we want to use in terms of identifying criteria for grouping. And usually after that, you also want to apply some aggregation function, meaning that for all those columns or rows that are in the same sort of like, column, do you want to find the sum, mean, count them? You want to perform some aggregation function. So let's say, create an example to understand this better. So again, I create a dictionary, and then we provide a data frame using pd.dataFrame. So you can see that here we have information about the students, class, scores. Something that is unique here, there are some student names that you see that we have more than 2 times. Like Alice, for example, has this class A and B, obviously with 2 different scores. Similar with Bob, but Charlie, it seems that has only 1 class. So in this case, what you really want to do is, for example, saying that, well, even if a student has taken more than 1 class, I want to just look at the average score across all classes. So if the student has only taken 1 class, that's the score. If it's more than 1, I want to take the average. So here you just say that for this data frame, so we're going to look at the 2 columns, a student and a score. We are going to group by the student column. So now we group them based on their these names. So Alice will be grouped based on these 2 rows, Bob similarly, and then you're going to apply that mean, right? So in this case, Alice has one with a score 85, the other one 90, and so the average would be 87.5. And you can see that here, if I run this cell, that's exactly what we get here. So for Alice, we get 87.5. For Bob, has 2 scores, 92 and 88. If you take the average, it will be 90. And Charlie has 1 score only, right? So this is very helpful if you know that you have multiple rows per, let's say, user, customer, or a student, and you want to perform some aggregation function on those grouped rows. Something else that we want to cover here is combining data frames. So we had a very similar idea in NumPy. You can see all the connections now between NumPy and Pandas. In NumPy ND arrays, we had the option to concatenate arrays using np.concatenate. In this case, we have a similar thing too, where we can use the concat function to concatenate, combine two or more data frames. And you can do this along a particular axis. So you can see that the syntax has these like objects, which is a sequence, which means a list or dictionary of data frames that you want to concatenate. And the axis is either 0 or 1. So 0 means that you want to concatenate things vertically, and axis 1 means that you want to concatenate them horizontally. So usually the more sort of like common approach is to concatenate vertically using axis 0. That's why this is the default value, because you may have, like, let's say, different students, different users in different files, and now you want to combine them together. So here we create these two data frames, df1 and df2. So you can see that df1 is this data frame and df2, right? So they have the same columns and then obviously different values inside them. So here I just decided to assign them some strings, but again, this can be some numbers, etc. And if you use pd.concat, and then we provide a list of these arrays axis 0, you can see that now we are going to combine this vertically, right? So we have this part, and then this A3, B3, C3 right under the first part. But you can see that here, one issue that we have is that the index labels that we have for the rows, now they are kind of like conflicting because we had 0, 1, 2 for one of them and 0, 1, 2 for the other one. So there's no like direct way of knowing that, well, we have to change them. So there are multiple options to handle this. One of the options is use the reset index method. As you guess, this reset the index label. So now means that we're going to start from 0 to whatever number that we have here. And if you want to change this to something more helpful or useful, I would say, you can use set index, right? So you can see that we provide 6 values here. And if I run this cell, now we get these index labels N0 to N5. So you have a lot of options in terms of changing column names, changing index labels, and also concatenating different data frames. But I would say the most important part of this lecture is here, because in general, when you're doing data science, you don't want to create your own data set, and instead you're given a data set. And one of the most common formats to actually store data sets is this CSV format, comma separated values. So in this case, for example, you can open this life satisfaction file, which is a CSV file, and you will see these values that are separated by commas. So it's really hard to read that if you just open that CSV file as it is. Obviously, you can open it as an Excel file because it has, as you have seen today with the data frame, these data frames are very much similar to Excel files and the spreadsheets. But anyways, you are given a CSV file. This is very common. And in this case, you want to convert this to a data frame. So there is a special method to do that, and that's pd.read_CSV. So it's very easy to remember. And there's also this index call here, which, as we have the information here, this tells you that, the index the index of the column that has to be used as the index row or the row labels for your data frame, right? So in this case, when you're given a CSV file, you have the option to decide what actually is the row labels that we have for our data frame. And in this case, we are saying that that information is inside the column with index 0. So if you can run this cell, now you can see that we get this information that is included inside this CSV file. So we have these column names, country, GDP per capita, life satisfaction. So in this data set, the goal is to find out whether there is a relationship between GDP and life satisfaction in a country. So you can see that this is a data frame where you have 27 rows. It starts from 0 to 26. Very similar to NumPy arrays, you can use dot shape, and this tells you that you have 27 rows and 3 columns. And just to show you the difference here, because again, it's very important to experiment with the code. If you, for example, choose index column to be 1, so now you can see that that sort of like, row label or index label is actually like country, right? So this means that if you want to use that .loc method to recover information for each row, now you can provide these names. So that's why it is kind of like important to decide which, column here is actually your row labels. So in this case, it makes sense to use index column 0 to make sure that we get these, integers that we have here for the indices of the rows or the row labels, and then we have this information. But again, there are some degrees of freedom here, and what we really, look for here is to find a relationship between GDP, gross domestic product, and life satisfaction. So a very useful method in data frames is .describe, and this provides basic statistics for your data set. So here you can see that the two main columns, GDP and life satisfaction. So we only get these two because these are like, numerical values. If you look at country, we have strings. So therefore we cannot really find the minimum and maximum value, but for the numerical ones, you can count the total number of elements, the mean or average, a standard deviation, and then distribution information, minimum, maximum, percentiles. So for example, here you know that just by using df.describe, that the minimum value for life satisfaction is 5.4 and the maximum is 7.6. So from a data scientist perspective, that can be very helpful to figure out like what range of values you have for life satisfaction in your data set. And also you can use other methods too, for example, like df.info. The nice thing is that this one will tell you whether you have missing values. You can see here it says none null, meaning that you don't have any missing values. It tells you that the country, the data type is object. And then for GDP and life satisfaction, you have float, say 64. So these are like floating point numbers and the amount of storage you need. So in this case, this is a fairly small data set. But if you have a huge data set, you may want to know whether, you need like, 200 megabytes or 2 gigabytes, right? So you want to have that information. So now we can practice some of the things we discussed before. So let's say you want to filter this data set to find countries where their GDPs are greater than 40,000, right? So you use this Boolean sort of like, or a comparison operator to get Boolean values. And then you feed this to DataFrame to do the filtering. And you can see that in this case, we are now only, accessing or working with, the part of the data frame where the GDPs are greater than 40,000. And that's exactly something we can confirm here by looking at the GDP column. If you want to, we can convert this data frame to a NumPy array, because sometimes we do not want to keep this information anymore about the column names and row labels. We are ready to feed this data set to some machine learning algorithm. And in this case, you can use the two NumPy method. So if in this case, we are selecting 2 columns and then using 2 NumPy, and this will, give us, in this case, a 27 by 2 NumPy array. And we know that this is NumPy array because we can use the type. So you can see that NumPy.nd array. And just to see inside here, you can see that this is our 2D NumPy array. Also, in this case, if you want to plot or have a scatter plot, we can do this. So we can plot the first column of this array versus the second column, right? So these are the x coordinates, these are the y coordinates. the way we can do this using NumPy is that we select all the rows and then the first column, all the rows and the second column. And you can see that now whether we have any kind of obvious relationship between GDP and life satisfaction. We are going to work this from a machine learning perspective, but immediately you can see that based on a very simple data analysis that we have done here, that there is actually a positive correlation between GDP and life satisfaction. And in this homework, we're going to work with a CSV file, which is called iris.csv. This is provided to you, and make sure that this CSV file is in the current folder or directory. If not, you will get an error message that the interpreter cannot find this CSV file. So if you get any error message like that, you need to make sure that you put it in the same directory. And then the idea here is to start working with data frames, like loading this data, displaying the first 5 rows, printing the summary statistics that we just discussed. In this case, because it's a classification problem and we have 3 species of iris flowers, you can use value counts to count the number of samples per class. And then we want to create some scatter plots similar to what we have done here to figure out whether there is any relationship between these different columns. And also we want to perform some operations such as displaying samples or rows where, like, let's say petal length or one of the features is greater than some numbers. So this is the filtering part that we mentioned. Also, we want to create new columns such as like sepal area, petal area, etc., where we want to, for example, operate on 2 or more columns and assign the value here. So this should give you a good sort of like practice for working with Pandas data frames. And this is something that we're going to use a lot for the rest of this class when we use machine learning algorithms. Hello, everyone. So far, we have covered basics of Python programming, object-oriented programming in Python, and also important libraries and packages such as NumPy, Matplotlib, and Pandas. And now we are at a very exciting point where we can talk about machine learning in Python using scikit-learn. So we're going to start this lecture by briefly discussing the main concepts and ideas behind machine learning to motivate the use of machine learning in recent applications. And then after that, we're going to see how we can actually apply and develop machine learning methods using scikit-learn, which is a popular library in Python for machine learning algorithms. So the first question we want to answer is, why should we use machine learning? Let's say that you want to design a system for predicting bank loan default based on several features, such as income, debt, for different applicants, and you want to figure out the risk in terms of bank loan default to better make decisions for your financial company. So there are 2 main ways to solve this. So the typical, or classical programming approach is that you can start by writing down a step-by-step instructions or rules. And that's what we have in the figure on the left side. So this means that you have these features such as income and debt, and then you write down some rules. For example, if the debt to income ratio is greater than some number, so you have to do your research, figure out what those numbers are. Then we find some responses, meaning that, yes, if, for example, the ratio of debt to income is greater than 0.5, then it is very likely that the applicant won't be able to pay the loan on time. But on the other hand, this is very time consuming and labor intensive because you have to write down these rules. And then if there are changes in your problem, you also have to change these rules. The other way to solve this problem is using machine learning. So here what we really want to do is to provide these features, meaning that in this case, income and debt, and also some responses, meaning that based on the observations that we have or historical data, we have information about people who previously were able to get loans and their information, including income and debt. And we know that, whether they paid their loan on time or not. So we do have some responses for these, group of people that already have been granted some loans. And therefore, in this case, the goal is that to use machine learning to actually provide us with these rules, right? So how can we distinguish between applicants that are able to pay off their loan and applicants who fail to do so? And here on the very right side, I have an example of this, right? So you can see that in this case, each data point, right, has these XY coordinates. One is debt, the other one is income. And you can see in this, synthetic data set that we obviously have a clear separation between these two classes. And the goal of machine learning is to find the rule that separates these two classes. So this means that now, if we find this rule and we have some new applicants, we will be able to figure out how to identify whether they're going to, or predict whether they're going to have problems with paying off their loan or not. So therefore, to recap what we just mentioned, when we have a machine learning system, this means that it is trained rather than being explicitly programmed, right? So that's kind of like, one way of thinking about machine learning systems. And therefore, the benefits are that, machine learning systems are in general easier to develop and maintain as long as you have enough data. And also, they can be more accurate than explicitly programming machines. But we do have challenges too, right? So as I just mentioned, we do need, features and responses. So in this case, features are income and debt, and responses are whether they, fail to pay off their loan or not, right? So that's what we call as label data. So label data means that you have features and corresponding responses. Another example of this, if I want to maybe clarify a little bit more, this like, data labeling. So let's say you want to develop a machine learning system to predict whether a medical image is normal or abnormal. So in this case, we need to hire some, physicians or some experts to look at some medical images that already we have and provide responses or labels for those images by telling us whether there's any kind of abnormality within each image or not. And that will be our labeled data set. And also we have other challenges too, because as machine learning methods become prevalent in high stakes applications and in safety critical applications, we have challenges to make sure that human users understand and trust these rules. For example, in the medical imaging case, we need to trust a machine learning system that predicts whether a medical image is normal or abnormal. And if the machine learning system makes wrong predictions, that can be really catastrophic. So therefore, we always have to make sure that we understand and trust the rules that machine learning models they provide. And so just, to emphasize this, in machine learning, data labeling, because that's a term that, you hear a lot, involves assigning informative labels to raw data, like images, text files, or videos. And, machine learning in general, in terms of like differences between like a statistics, optimization, and machine learning, you can think about it in a way that machine learning really moves beyond the confines of these traditional domains. Because in machine learning, first of all, we want to be able to handle large and complex data sets. And what this means is that, we need a combination of both math and coding skills. right? Because in some cases, you need to be able to handle, millions of data points. So that's something usually we don't discuss or take into consideration when we talk about traditional statistical techniques. But in these cases, we need to make sure that we can import the data, read the data, manipulate the data, and then feed that to some machine learning pipeline to extract some knowledge and information. And obviously, this course mainly focuses on coding skills, but we do have other courses that are more focused on math skills. And at the end, you want to have a balance of these two very essential skills. Okay, so now let's talk a little bit more about learning rules that we just mentioned, right? So, as we said with the bank loan default problem, we have some data points represented by their coordinates, right, in a two-dimensional space or R2. As you can see here, you have this x1, you have x2. In this case, we assume that x1 is what shows the debt, and x2 shows the income, right? And obviously, these numbers here are in synthetically generated, so you can assume that these numbers can be multiplied by let's say 10,000 or $20,000 or something to be more reasonable. And so the goal here is to develop a machine learning system that can take the coordinates, these x1, x2 values of a new sample and predict the label or outcome for that, right? And in this case, we're going to very soon see that we can use, for example, logistic regression to solve this problem and find this classification rule, meaning that this dotted line that you can see here that separates these two classes. But something that we have to think about, and this is one of the main distinctions between machine learning today and machine learning 10, 20 years ago, is that in many cases, we may have a lot of features. So instead of just debt and income, we may have debt, income, gender, occupation, location information, etc. And therefore, in these cases, we have a very special type of data that we call high dimensional data, right? So this means that, instead of just having a two-dimensional coordinate system, we may have thousands or millions of dimensions or features. And this is exactly why, deep learning methods are becoming extremely popular, because they are very good at both finding rules and also at finding good data representations, meaning that if we have, very, very high dimensional data sets, they're able to extract the key information from this high dimensional data and then learn, rules that can, for example, separate classes in that reduce dimensional data. And also we have other, again, applications or considerations here too, such as like limited data availability, for example, for the medical image data analysis that we mentioned. Usually, it is, difficult to have large amounts of labeled data because data labeling costs a lot because of the need for domain experts and people who understand these medical images. And also, a lot of these machine learning applications are really high risk, high reward type of investments, meaning that they are costly, but if they work, they're going to be very, very helpful and high rewards. So that's something to keep in mind. So now let's go get a little bit deeper into the underlying foundations of machine learning methods and deep learning models. That's also something we're going to cover in this course. So in general, we can follow this framework that we have here. I mean, obviously there are minor differences between different methods, but the general rule is this, that we start with the features, and from now on, I probably just gonna call them inputs. So inputs and features, we use them interchangeably. And we send them through some layers or data transformation. So this means that you get your input data, you transform this, You can do this multiple times, so it's not just like one time. This is the main distinction between machine learning 10, 20 years ago and machine learning today, is that we may have multiple levels of data transformation. And what this does, it gives us at the end what we predict as the output for that very specific input that we provided to the system. And the nice thing is that in most cases, for this data that we provided, these inputs, we do have the labels or the actual true outputs or expected outputs. So this means that now, at this point, we can compare these two. And this is what we call it as a loss or cost function, which really measures the discrepancy or disagreement between what we predicted and what the underlying or true outputs are. And this allows us now to send this information to some optimizer that can update the way that we transform the data. So usually these data transformation layers that we have, they have some weights or coefficients, and this optimizer tells us how to update the way we do those transformations. So this is very much similar to the example of linear regression that we had before, where we get some inputs and then we find a weighted sum, right? We had those coefficients that we used in previous lectures. And the key question here is that what those coefficients or weights should be to get outputs that are as close as possible to the true outputs. And the way that we measure that is using this loss or cost function. Okay, so let's talk about categorization of machine learning algorithms based on two criteria. So one is based on data supervision, which refers to the data labeling process. So supervised learning algorithms are trained on labeled data, which means that each input data is paired with a corresponding output or label, right? So for example, in the case of medical image data analysis, meaning that for each medical image that we have, this can be a CT scan or something like that, we do have a label that says, for example, if this is normal or abnormal. So this is what is called as label data, and supervised learning means that we are training them on labeled data. The other type of machine learning algorithms is unsupervised learning. And in this case, these algorithms are trained on unlabeled data. So this means that in this case, you may have some CT scan images. You do not know which ones are normal or abnormal. So nobody has labeled them. That's why we call them unlabeled data. But the goal is to automatically find some interesting patterns or structures in the data. For example, can we automatically group them into two clusters, where one cluster are the ones that are more likely to be normal and another cluster are the ones that are more likely to be abnormal. So in this case, we don't have any supervision, but we do want to learn these types of structures. And as you imagine, we have a third approach, which is semi-supervised learning, which is a combination of supervised and unsupervised learning, where the algorithm is trained on a mix of labeled and unlabeled data. So some of the data points come with the input-output pairs, and some of them are just inputs with no outputs. We also can categorize machine learning algorithms based on model complexity. So in this case, linear models are the ones that they assume a linear relationship between the input features and output, right? For example, linear regression. That's a very classical example of this. We also have nonlinear models that can capture more complex relationships between inputs and outputs. And something I want to emphasize here is that neural networks are not necessarily the only nonlinear models that are becoming very popular and very important, but there are also other ones too, such as like decision trees and so on. And therefore, this is just to keep in mind that we have a wide array of nonlinear models. But a subset of this is what is known as artificial neural networks, neural networks, deep neural networks. In many cases, we just use these interchangeably, although there are technically differences. For example, when you say deep learning, it is supposed to be neural networks that they have many hidden layers, whereas just neural networks usually like have a few hidden layers. But these days, in many cases, we use them interchangeably, and these are a subset of nonlinear models. And the cool thing about them is that they learn hierarchical features, as we're gonna see very soon in this course. However, in this course in general, we are focusing on supervised learning, meaning that in cases that we do have label data, each input data point is paired with the corresponding output. And this is the most common type of machine learning, and usually the sort of like the backbone of many other types of machine learning algorithms. So one way to think about supervised learning is that you always want to make predictions, right? So meaning that you want to predict some outputs, and depending on the type of output, these supervised learning methods are divided into regression and classification. In regression, we have quantitative labels. However, in classification, we have qualitative or categorical labels. To show the difference here, on the left side, you can see that this is a regression problem. Let's say you have years of experience as your X value or input, and here the output or the Y value is the salary, right? So you want to see if you have a new employee with a number of years of experience that you have, if you can predict the salary for that new employee, right? And in this case, we do have these data points that are already given to us, and we want to use this to develop a model to figure out, well, what is a reasonable salary for this new, new employee with let's say 20 years of experience. But in this case, we are trying to predict a quantitative label. On the other hand, on the right side, you can see that with the classification, right, you may have, again, like bank loan default, where the answer is yes or no, or like if you have an email filtering system where you want to label each email as a spam or not a spam, or a medical image analysis where you want to label each or predict labels for each image as being normal or abnormal. So in this case, we do have qualitative or categorical labels. And in future lectures, we're going to first talk about regression, and then in the subsequent lecture, we're going to talk about classification. So let's very quickly talk about mathematical building blocks of machine learning. So in supervised learning, which is the main focus here, the goal is really to find a mapping or function from inputs, which we also call these features, or in statistics, we like to call them predictors, to some outputs. And remember, these outputs are the ones that we just mentioned, that either they can be quantitative or qualitative. And in general, we assume that we have a data set with n input-output pairs, and we use this small n to index these data points, right? And this n goes from 1 to uppercase n. So the uppercase n is the total number of samples that we have. And then we also assume that each of these inputs xn is a d-dimensional vector or array, meaning that we have d features. In the case that we have, let's say, only income and debt information, that means that d is equal to. But as we said, in many interesting machine learning applications, we have high dimensional problems. So this d can be thousands or millions, in the order of thousands or millions. And then in the case that we have a classification problem, these YNs are categorical, and therefore in the multi-class classification with C classes, we can give them these labels 1, 2 through C. Although I have to say that these labels, when you do classification, do not have any numerical value anymore, meaning that in that case, just the difference between 1 and 2 is that all the data points with label 1 belong to the same class, and all the data points with label 2 belong to another class. But obviously, this doesn't mean that one class is 2 times the other one. So we do not really assign any numerical value to these. It's just more to distinguish between them. And if you have a binary classification problem, which means that we only have 2 classes, the situations where we have yes and no problems, then the labels are either 0 or 1, or sometimes we also may label them as -1 and 1. And as we just mentioned, there is really no numerical interpretation of these numbers, and as long as we just use 2 distinct values to represent these 2 classes, then everything should be fine. Okay, so now let's talk a little bit about model fitting, or also known as model training, right? Because we said that these machine learning algorithms are trained on data. So the first thing that we need to do for model training is to form something known as empirical risk, which is simply the average loss on the training data. So what this means is that we need to have a loss function, which we show that using this L. This function accepts 2 inputs, the true or expected output and the predicted output. And remember, the predicted output is the function of the input. And this theta here shows all the parameters that we have in our model that we need to find them. So that's why we use this semicolon here. So just to explain this, let's go back to the framework that we have here. So here we have the x, which is the input. This gives us f of x, which is the predicted output. We compare this with the true output, which is y. And this loss function, or L, measures the difference between the 2. And all these weights or parameters that we have here, these are known as theta. So in this case, we have our input, thetas, and also the true outputs. And since we're using the small n here for indexing, we take this from 1 to uppercase N, and this is what is known as the empirical risk. So let's talk a little bit about this loss function that we have here. If you have a binary classification problem, we can use a loss function, which is an indicator function. So when you have an indicator function, this I function, if this condition is true, then we get 1, meaning that if y is not equal to y hat, and otherwise we get 0. So what this does, if we plug this back into what we have here, is that if the true output and the predicted output are not equal, right? In this case, we get 1. So this means that we have 1 misclassification. And this summation overall gives us the total number of misclassified data points. And divided by the total number of data points, that gives us misclassification rate. And obviously, when you have a machine learning system, you want to reduce or minimize the misclassification rate. And you do that by finding the best choice for this parameter theta. Therefore, putting back everything together, this is what is known as empirical risk minimization, or ERM, which means that you want to find parameters theta that they minimize the empirical risk, right? So this is what we just talked about as the empirical risk. And now we want to find the argmin with respect to theta. And as we're going to see right now, there's a big difference between argmin and min, because when we are using argmin, what we are saying is that we don't want to necessarily find the minimum value of this function, but we want to know what value of theta leads to the minimum value of this function. This is very similar to when you working with NumPy arrays, we use min and argmin, right? Remember, min of a 1D NumPy array is the minimum value that you have, but argmin gives you the index where that minimum value resides, right? So that's kind of like the difference. And we can do the same thing here, and you can see how we can use different libraries. So we use import NumPy as NP, we are gonna use Matplotlib. We know about customizing figures. So here we are customizing the font size and figure size. And then we're using np.linspace to create 1,000 data points from -3 to 2. And then we're going to generate the outputs, which are related to the inputs via this equation, x squared plus 2x plus 3. And then we plot these xy values to see how this looks like. We're going to use the np.argmin to find the index for the minimum value. And using this, now we can plot actually where the minimum value is. And also, we're going to use plt.annotate to actually, annotate our label and show exactly where the minimum value is. So if I run this cell, you can see that as we expect, this is our function that we have. The minimum value is 2, the minimum value of this blue function, but the argmin is -1 because the value of -1 leads to the minimum value, which is 2. So that's something you always have to keep in mind when you're working with machine learning models. We really want to find the argmin with respect to the model parameters to know what model parameters give us the lowest disagreement between true and predicted outputs. Okay, so we just talked about a loss function for classification problems where we have categorical labels. But as you imagine, that approach does not really apply to regression problems where the output is quantitative and it can be any real valued number in general. Therefore, the main reason that we have to study classification and regression tasks separately is that the loss function for these two different types of tasks are usually very different. And therefore, let's look at one example of loss function for classification problems, which is the quadratic loss function. So what this loss function does is subtracts the true output from the predicted output, and then we find the residual and raise this to the power of 2. Obviously, in this case, it doesn't matter if we use y hat minus y or y minus y hat, but the idea is that we have to find the difference between true and predicted output and find this residual and raise it to the power of 2 to make sure that it's also not negative. Because in that case, if this becomes negative, when you add these disagreements or these values of loss functions, they can cancel each other, and that's not a really good idea. So therefore, in general, as you can see, one of the properties of loss functions is that they should be non-negative. And therefore, based on this, if we plug in this back to the empirical risk that we had, you find this 1 over n, sum over n of these residuals raised to the power of 2. So this fx and theta is now, in the place of y hat. And this is what is known as mean squared error, or MSE, which is a very well-known function. And the underlying assumption for linear regression, it's simple, is that when we have some inputs with the features, so these x1, x2 to xd are the features, we can find a weighted sum, or also known as a linear combination. And here we can also simplify these by writing these as dot product of two vectors w and x, because if we have two vectors and find the dot product as we have done before, that's equivalent to the sum of the element-wise products, which gives us this dot product or inner product. And therefore, in this case, all the values that we have for this w1 to wd, and also this w0, which acts as the bias or the y-intercept, they are considered to be the weights of the parameters of the model that we have, right? So this theta that you see here are all these unknown parameters that we have, this w0, w1, wd, and the goal is to find the best values for these such that we minimize the value of these mean squared error. Something that is important in machine learning is that what we really care about is the generalization of machine learning problems. And just to show the difference, so when we do training, we can, develop machine learning models that they can literally memorize the data that they have seen. But what we really care about is that how well this machine learning model that we have trained generalizes to new or unseen data points. And this is the main idea behind generalization. And one of the main challenges that we have is that the model can become overly sensitive or specialized to the training data during the model fitting or training process. And therefore, it may not perform um, comparably when applied to new data points. And therefore, for this reason, we always want to make sure that we can evaluate the generalization performance of machine learning models, which means that at the minimum, you have to always have two data sets, one for training and one for testing. And this is the idea behind train test split. So in this case, as the name suggests, we are going to divide the data into two parts, a training set and a test set. And then the training set is used to train the machine learning model, which means that we find those unknown coefficients or weights, like for example, the W0 through WD that we just saw. And the test set is used to evaluate the performance on new or unseen data, which is a holdout data set. And in this case, you can find the training risk, which is the sum of the loss functions evaluated for the data points that belong to the training data. And then we can find the test risk, which is the sum of the loss functions evaluated at the test data points. And these two values should be comparable. Overfitting happens when the test risk is much greater than the training risk, which is not desirable. So overall, once you find this L train and L test, you want to make sure that they're comparable. And if for some reason the L test is much greater than L train, then we know that we have a model that is overfitting and not generalizing well to new or unseen data points. So here we can show this or illustrate this. So you get your original label data and you divide this into training and test set. One caveat here is that if you do this train test split and use the test set multiple times, you may actually end up overfitting to the test set itself. So a good practice is to just use this test set only one time. But that really depends on the application because in many cases, you may only have one training and one test set. But that's something that we will talk about that more later. But for now, the main thing that we have to consider is that once we have a given data set, we need to at least create two data sets from that, training and testing sets, to be used, one for training and the other one for evaluation purposes. So at this point, let's put everything together by creating a synthetic data set for a regression problem. And we're considering a 1D regression problem, meaning that we only have one input X and we have one output Y. So this is what is, matches very well with what we know from linear regression, which is Y equals mx plus b, where m is the slope and b is the y-intercept. And even to make this simpler, we are going to assume that we do not have an intercept, and the goal is just find the slope. So when we create the data in this case, we are going to make sure that we just use y equals mx. There is no b here, and we just want to find the slope. During the case that we want to, the step that we want to, generate this data, we also add some Gaussian noise. This is just to make this more resembling real-world data sets, because in general, in real-world problems, we always have some measurement noise or observation noise. So as we're going to see when we create our data set using this equation, we're going to add also some Gaussian noise. And then we're going to split the data into training and testing sets. And one way we can find this slope m here using the derivative approach, meaning that once we find the loss function, we can actually find the derivative with respect to m and set that equal to 0, because here we only have one unknown during the training part, which is this m. And this is doable in this case. But in general, if you have multiple of these, unknowns, we cannot easily use the derivative approach. And for that, we can use the scikit-learn's method or linear regression class, which can help us to solve this linear regression problem. So in this case, we want to one time solve this problem from scratch by using the derivative approach. And then we're going to utilize linear models, linear regression from scikit-learn. And just to put this into context, we know that, in this case, scikit-learn is the library or package. Linear underscore model is the module. And linear regression is the class that is included inside this module, right? So this connects us with I believe lecture 9, where we talk about modules and packages. So now we understand the hierarchy here using this dot notation. And then once we find the slope, now we can predict the output or y values for the testing set. Okay, so let's start with the step 1, which is generating a synthetic data set. In this case, we're gonna import NumPy as NP, import matplotlib.pyplot as PLT. It's always a good idea to set the random seed for reproducibility, so you don't have to do this, but if you use this line, you'll see that you get consistent results. Then we're going to generate our synthetic data set. And I want to be clear, the reason that we are generating synthetic data set here is because we don't want to use a real world data set. In practice, we usually have a CSV file, we have a data set that we import, and we don't really know the true underlying equation that generated the data. But in this case, we want to really simplify the process. So we use this known equation to generate the data. And the goal is that, well, can we now estimate this m true or not, or the truest slope? And in order to do this, we're going to use the NumPy's random module. And inside that, we're going to use rand, which gives us 100 data points in 1D. And then we're going to set the m true to be 5. And we're going to generate these outputs by simply multiplying m true by x, right? So this is that linear relationship with no intercept. To make this a little bit more interesting, we're going to add some normal or Gaussian noise. There we have this SKL, which is the standard deviation for this normal distribution. And after that, we can use plt.scatter to have to visualize the relationship between x and y. So that's what we talk about when we had Matplotlib. The plt.scatter is great for visualizing relationships. And obviously, we use the x label and y label to make the figure more readable. So here we can see that this is the data that we created, right? So this follows a linear trend, but also we added this Gaussian noise to make sure that this is not trivial, because if you don't add that, you can literally pick 2 data points and draw a line that goes through them, and that's the solution. So it becomes almost a trivial problem. Just to make sure that this problem has the right shape or size, you can see that we can look at x and y values, and they both have 100 elements, right? So this means that each input is paired with a corresponding output, right? So if you have this 2D coordinate system, that we have an x value and we have a y value. The next thing that we have to do is to split the data into training and testing sets. In order to do that, we can use scikit-learn, and inside that we have a model selection module, and inside that we can use train test split. And the way that this works is that for train test split, which is a built-in method in scikit-learn, you can pass in the x, y values and the desired test size that you want. So 0.2 2 means that you want to have 20% of your data for testing and 80% for training. Also, because this involves generating a random number to separate the two classes randomly or the two data sets. So we can use this thing called random state. So again, you don't have to specify this, but if you set this equal to any number that you want, you will get consistent results if you run this cell multiple times. And so if you use 0 here and use np.random seed that I used before, you should be able to get exactly the same results, even though these are random numbers, they are generated in the same way. So that's the idea behind random state. So if you run this cell, you will see that now xtrain, the training data, we have 80 samples. And this makes sense because 80% of data should be for training, and we have 100 data points. And then for testing, we have 20 data points. And then their corresponding labels or outputs, like 80 for training and 20 for testing. So let's say now we use two scatter plots to individually look at training and testing data points. And I'm going to use different colors. So blue for training, red for testing. We also give them labels. And we're also using plt.legend. So you can see that why knowing Matplotlib is essential for machine learning and data science, because we can use them a lot for visualization purposes. So you can see that here we have the training data points, we have the testing data points. Everything looks fine here. We do not have any of abnormalities. You can see that the blue and red dots here are distributed almost uniformly, which is great. And remember that in many cases, you're already provided with this training and testing data set. So you usually do not want to generate your own data. But again, this is just for illustrative purposes. So now let's look at how we can find the slope using the derivative approach. So in this case, you have to form that empirical risk by having this average of loss function. And in this case, the predicted value is simply m times the input, and true output is yn. And now we can take the derivative of this with respect to the slope, which is m. So if one way to do this is to call what we have here as, let's say, z or something like that, to be able to use easily the chain rule. And then we can take the derivative of this with respect to m. So then we get derivative of z squared, which is 2 times z. And then we have to take the derivative of this z with respect to m, which is xn. And once you find this derivative, we set this equal to 0 and solve for m, which gives us this somewhat familiar equation because we have used this before, which is the sum of the products of xn and yn. So each xn and each yn is one data point that we have, one input-output pair. And then in the denominator, we have the sum of the squares of inputs. So in this case, we can just write exactly what we have here to implement this. So we can multiply xtrain and ytrain, use np.sum to sum that. And in the denominator, we have np.sum xtrain raised to the power of 2. And then we can run this cell, and you can see that it tells us that the estimated slope is 5.18, which this is a good result, right? Because we know that since we generated the data, the true value should be 5. So this is, reasonably close to that value. But let's see how we can use scikit-learn, like especially if we have a more complex problem and we want to solve this, how can we use scikit-learn's linear regression? So remember that this scikit-learn.linear model is a module in scikit-learn for using linear models. And inside this, we have a bunch of linear machine learning algorithms, such as linear regression, logistic regression, etc. In this case, we can import linear regression from this module. And the way that this works is that, remember, this is a class. So you have to first create an object. And in order to do this, you have to instantiate this. And once you want to instantiate these, there are some options. In this case, we know that we don't want to have the intercept term. So we can set that to be false, meaning that we just want to find the slope. So this is the object. This object does have a method called fit, which accepts the training data, X train and Y train. And once you do the training, one attribute of this is this dot coef or coefficient, which gives us the coefficient or that slope term m. And that's why I call it as m scalar. So this is the m value that is estimated using scikit-learn, and the other one was m that we estimated using the equation that we derived ourselves. So let's see what we get here. And you can see that we can get 5.18, which is very close to what we had before. So this is great. This means that now, even if we have a more complex problem, we do not have to use, this analytical approach that we did here. We can just simply instantiate this object, use .fit, and then use .coef to find the coefficient. And if you want, we can even, although we know that these slopes are very close, we can even visualize this, right, by making predictions. So what this means is that when we have X test, we know that in order to predict the output for that, we just simply have to multiply the estimated slope by the input. So that's the m times x. And we do that one time for the one that we use the derivative approach. And we can also do this one time with this scikit-learn approach. And if you run this cell, you can see that this is the prediction model that we have. And the red dots here are the task data points. And you can see that both cases, they are identical, the derivative approach and the scikit-learn linear regression approach. This is the best we can do in this case with the linear model, because obviously if we have a nonlinear model, we might have been to better, approximate or go through these, red dots that we have. But since this is a linear model, the only thing that can really do is to go through, kind of like the middle of the data that we have. So this is a reasonable model for a linear regression problem. And we do have these issues with these scattered data points not being directly on this line because of that Gaussian noise that we added. So we can reduce the amount of noise to get closer, or we can increase it to make it even more difficult to solve. So all in all, the goal here is to show you how to use scikit-learn. So in many cases, you may know the model assumptions, but you don't know exactly how to do model fitting. But this is no problem because you can use scikit-learn. And the steps that you have to take are as follows. First, you choose a model. So obviously, as we go through these lectures from now on, you can see that we have multiple ways of solving problems, depending on whether you have a regression or classification problem. For example, for regression, you can use linear regression. For classification, you're going to use logistic regression, and we're going to talk about this later on. We have not discussed this yet. Then you have to import the model. For example, for linear regression, we said from sklearn the linear model, import linear regression. Then you have to prepare the data, and this usually means that you need to find the features or inputs or independent variables, and then the target or the dependent variable, what you're trying to predict. And remember that the features, the one that are inputs, they're supposed to be 2D arrays. And the targets are usually a 1D array. So that's kind of like the distinction here. And then for the features that are 2D arrays, each row corresponds to one data point, and each column corresponds to one feature, right? So that's something that we have been using so far as the main assumption that we make, that features are usually in a 2D array where each row is one data point, each column is a feature. And the targets are usually 1D arrays because we are here trying to predict a single quantity or target, and it can be quantitative or qualitative, but anyways, it's one element that we want to predict for each input. Step 4 is to split the data so that we can measure the generalization performance. And for that, we can use scikit-learn's model selection. And then we use train test split. Remember, this model is a class, so you have to now instantiate this and create an object. This object is equipped with a method called .fit, where you have to provide your training data. And finally, once you train your model, you can use .predict method and provide these testing data points to get predictions. So in the object-oriented programming lecture, we actually had a homework problem where you had to develop your own linear regression model, and you did exactly the same thing. You calculated coefficients, and then you made predictions. So you can see in that case, you had a very like simplified version of this to show you how this works in terms of like the big picture. And finally, you have to evaluate your model. So we're going to talk about this in the next lecture more, but there are different ways of evaluating models. If it's a regression problem, such as mean squared error, mean absolute error, or if it's classification, you have like things such as accuracy, precision, recall, and all of these are inside this module, which is called sklearn.metrics. So that really helps us to understand how scikit-learn works, right? So we have these different modules like linear model, model selection, metrics, which, these modules provide different functionality. And then for the homework for this problem, the main one is in one case, you want to manually implement the train test split. And in this case, you can use all the NumPy's functionalities, but do not use exactly the train test split, which is included in scikit-learn, because that's our goal to replicate its functionality. So this function should be called custom train test split. You assume that you're given a set of input features, and that's a 2D array, as we said, a 2D NumPy array. You have the corresponding outputs, which is a 1D NumPy array, and then the test size, right? And in this case, you can see that what you can do is to randomly shuffle your data or permute your data. And then based on that, you can split your data into a training and testing sets. And then you can return the values for xtrain, xtest, ytrain, and ytest. And as I said, the main thing here is that do not use scikit-learn's train test split. And here we have one example that we have X, which has 4 rows and 2 columns, and Y is a 1D array with 4 elements. And so we want to here divide these data into training and testing such that the testing set size should be 25%. And then in the third problem here, you again create a one-dimensional synthetic data set like the one that we did. And you apply the linear regression model from scikit-learn to this data set. This means that you have to do model fitting, you have to print the slope. And also in this case, you can see that we have this intercept term or y-intercept b. So that's kind of like the main difference. But other than that, you can see that we will follow the same procedures to instantiate linear regression and do model fitting and model training. And then also we have a variant of this where instead of linear regression, you're going to use ridge regression. And again, the goal here is to show you once you understand the basics of how scikit-learn works, we can use different implemented algorithms or built-in algorithms because they very much follow the same procedure. You just need to know how to instantiate them, and then you have to do model fitting and model training. Therefore, in this problem, we just want to show you how, you can use the knowledge that you have and extend this to solve another problem where you are here using this ridge regression. So here you have the documentation, some information that provided here that you have to provide this information about an alpha parameter. But this gives you a really good idea of, how you can apply your knowledge to use, other existing machine learning algorithms in scikit-learn. Hello, everyone. In this video, we discuss regression in machine learning using scikit-learn. But before discussing about the scikit-learn implementation of regression models, including linear regression and polynomial regression, we are going to very quickly discuss problem formulation and some of the assumptions that we make. Also, we talk about the model training aspects of regression models, such as loss function and gradient. And also at the end of this video, we talk about several evaluation metrics that we can use to assess the performance of regression models. So let's get started with the simplest case, which is univariate linear regression. So univariate here means that the input that we have to our machine learning system is just a scalar. And this is exactly why here we are not using boldface letter. So therefore, in this case, our training data, which is a labeled data set, consists of input-output pairs, where the input is a scalar or a single number, and output is a scalar too. And because it's regression, this means that yn is actually a quantitative label. And in general, it can be a real valued number. So in this case, we have a parametric model where we assume that the predictions that we make are in the form of theta 0 plus theta 1 x. Something I want to mention about the naming of these variables. So here we have a lot of flexibility in terms of what we want to use to name these variables. Before we call this mx plus b or w1 times x plus w0. And like any other mathematical equation, we can use different names for these variables and then estimate them. So this name doesn't really change anything. And in this video, we are going to use theta 0 and theta 1, where in this context, theta 1 represents the slope and theta 0 is the y-intercept, also known as bias in machine learning. So therefore, the goal of machine learning, or I would say here, training a regression model, is to choose theta 0 and theta 1 such that the predictions that we make for each input xn is as close as possible to the known output or label. And this is exactly the idea of using empirical risk minimization that we mentioned earlier in the previous video, where we have to find a loss function that measures the difference between the prediction and the true value. And in the case of regression, the most popular option is the quadratic loss function, meaning that we find the difference between true and predicted value and raise this to the power of 2, and then we take the average across all data points that we have. And therefore now, this is a function of theta 0 and theta 1, meaning that every configuration of these two will give us a different value of the loss function, but we are looking for the configuration that gives us the lowest possible value for this loss function, and that's the optimal solution. As we said earlier, in these cases where we only have a few parameters, we can use the derivative approach and start by finding the derivatives, or in this case, because we actually have two unknown variables or two optimization variables, better to say, we need to find partial derivatives and then set them equal to 0, right? So that's how we can solve optimization problems of this form. And when you want to find the partial derivative, and that's the notation that we're going to use of this loss function with respect to theta 0, you can assume that theta 1 is fixed, right? So it can be any number like 2, 5, 10, anything you want to consider. So theta 1 is not variable. On the other hand, when you want to find the partial derivative with respect to theta 1, you assume that theta 0 is fixed. Based on this discussion, then what we really want to do here is that you want to use the chain rule, if you're familiar with the chain rule of calculus, and call this term that here you have inside these parentheses as Zn, or some variable name that you want. And then when you take the partial derivative with respect to theta 0 or theta 1, you have this term which is like z squared. And so the derivative of that is 2 times z. So that's why you can see here we have this 2, and then we have this term inside the parentheses. And if you're wondering why we get this theta 0 and theta 1x, that's because that's the value of f of xn, right? So if you find f of xn here is theta 0 plus theta 1 xn, and we have a negative sign here too. So therefore, you get negative theta 0, negative theta 1 xn. So you can definitely pause the video here and put all these pieces together. But that's sort of like, the first step. And then you have to find the partial derivative of the term you have inside this parentheses with respect to theta 0 and theta 1. And you can see that when you do this with respect to theta 0, you just get a negative 1, and that's what we have here. And when you do with respect to theta 1, you get negative xn. So that's the constant that you have right next to this variable theta 1. And you can see that here, that's what we get. We get a negative sign, which is here, and we get xn. So these are the two partial derivatives with respect to theta 0 and theta 1. And now the idea is that you have to set this equal to 0 and find values of theta 0 and theta 1 that will give you these two terms to be equal to 0. So something that here we have to pay attention to in this very simple problem of univariate linear regression, we only have 2 parameters. But in a real world problem, like for example, neural networks and deep learning, you may have millions or even billions of these parameters like theta 0, theta 1, up to theta 1 million, for example. So in that case, this is really not anymore feasible, and we have to find a better way of finding these partial derivatives. And that's where the idea of gradient becomes very important. So the idea of gradient is that we can extend derivatives to handle vector argument functions, meaning that when you have a function that accepts more than one variable, like the one that we just saw, where we have theta 0 and theta 1, and possibly even more variables, we can find a vector where each element is partial derivative with respect to one of these elements. So this means that if you have a function that accepts d variables, then the gradient, which we use this notation, this upside triangle that you can see here, and you can see that in this case, we have all these partial derivatives with respect to the d variables that we have, theta 0 to theta d minus 1. Which means that if you want to find a gradient for the very specific case that we have, we can put everything back together in an array. So we have this 2 over n, which is shared across these 2. So we can factor this. And then you have the 2 summations. And remember, the difference is that one of these summations has this extra xn here. And now this is a 2-dimensional vector or array. Something which is very important to understand in machine learning is that in many cases, you can actually write this gradient in terms of compact representations of your data. So what does this mean? Let's say here in this example where we have these n data points x1 to xn, so these are our inputs. Let's put them in a matrix of size n by 2, where right now each row corresponds to one sample, and each column corresponds to one feature. So we have this first column where we have all ones, and we're gonna discuss that why we get that. But you can see that in the second column, you get exactly all the input features that we have for our n samples. And why do we get these extra ones here? So this becomes from looking at our model, that you can see that where we have this theta 0 plus theta 1x, you can write this actually as theta 0 times 1, and that 1 is a feature that is shared across all the samples. So it's never changing, it's a constant, but you can assume that that's one feature. So therefore, even in the case of univariate linear regression, we can actually assume that we have two features. So therefore, we have two columns. But the first column is always a constant. It's not really a variable. But the second column is the one that really depends on the input that you have, and it's definitely a variable. And then you form a vector theta, which includes two elements, theta 0 and theta 1. And then the corresponding outputs for these inputs that we have, which should be a vector of size n. So this is consistent with what we talked about earlier about scikit-learn, where we expect that the input data matrix, this x, should be of size n by the number of features, where n is the number of samples. And then y, which is the target vector, should be a one-dimensional array with n elements in it, which contains all the corresponding outputs. And here you can show that if you multiply x by theta, so this is a matrix vector multiplication, and subtracted by y, you get all the residuals that we were looking for, like this f of x1 minus y1, f of xn minus yn. And the next slide gets a little bit complex, and it is not necessarily for this lecture, but it is important to kind of like show that the gradient that we have here, this gradient that we found, can be actually written solely in terms of x, theta, and y. So you can show that if we have this x transpose, which means that now you're going to switch the rows and columns, which gives you a row of all ones and a row of all these x values, multiplied by x theta minus y, which we have here. This is the vector of our residuals. If we do this multiplication, right, then in this case, we can show that we are multiplying this first row by this column vector, which will give you the sum of all fxn minus yn from n from 1 to n. And similarly, we can do the second multiplication here, which is this second row by this column vector, which will give us this one. So you can see that here the main difference is that we have this xn for each f of xn minus yn, and n goes from 1 to n, which is the result of this multiplication or this dot product, because technically here we have two vectors. So therefore, this means that this is our gradient that we found. And the nice thing here, the interpretation of this is that even if we have a lot of data points, let's say we have like 1 million data points, the only thing that we really need is to form this data matrix X and then plug in it into this formula that we have here. And the same thing with theta. The one that we just showed, theta has only two elements because we have univariate linear regression. But you may have a theta vector, which is really, really large, meaning that you may have like thousands of elements inside this vector theta. And therefore, the nice thing is that now, in order to solve this problem, to find the optimal values of theta, you can set this equal to 0. And if you're familiar with topics in linear algebra, you can show that you can do this multiplication and then solve for theta. So if you do the multiplication, set this equal to 0, on one side, you get this x transpose x theta, and then on the other side, you get x transpose y. Now remember, x and y are given. That's what you provide to scikit-learn. And the unknown here is this theta. And therefore, now the only thing you really need to do is to solve this system of linear equations. So you can see that that's why linear regression is very popular and simple, because at the end, we have a very nice analytical way of solving this problem. Okay, so now let's see how we can actually implement this, even before using scikit-learn. So we're going to start with importing NumPy, Pandas, Matplotlib. You can see that now why we are using all these data science libraries in Python. And also we have a data set, which is called life satisfaction, which is a CSV file. And we're going to import and read this data and look at the first few rows. So this may take a little bit of time because you actually have to find these on this website and then read this CSV file. And you see that this is very familiar, right? This is the data set that we've been using before, where we have countries, GDP, and then life satisfaction, where the goal was to find a connection between GDP and life satisfaction. So let's pre-process this data and make it ready for analysis. So we're going to look at the GDP column, and that's our input to the system, right? So you want to create a machine learning system where the input to this machine learning system is this GDP information, right? So that's our X. And then the output here is this life satisfaction, which is Y. And we want to see if we find a model that now, if we provide a new GDP, we can predict the corresponding life satisfaction score. So in this case, we're going to look at this column of the data frame, convert this to a NumPy array, and similarly for Y. So you can here always print the shape to make sure that you have the same number of data points. You can see that here that's the case. You have 27 samples. And then if you want to implement this from scratch, remember we have this column of all ones here. So we have to add that manually. So in this case, we write a function to add this column of all ones, and we can do this using numpy.concatenate that we have used before. So you're gonna create a array of all ones, and also you're gonna reshape this matrix X that we have to make it a 2D array where we have n rows and 1 column. And then we concatenate them across axis 1, which means that we want to concatenate them and put them next to each other. So we have a, again, just to show this means that we have this vector of all ones that we created. And then we have this vector of all these X values. So this includes X1 through Xn. And now if we concatenate them, we get this n by 2 array where n is the number of samples and 2 is the number of columns, right? That's why we use axis equals 1 here, because this is the direction of axis equals 1. Okay, so now if we run this and look at the shape of the concatenated array, you can see that now this is 27 by 2. And you can obviously even look at some of the rows of this matrix to make sure that that's exactly what you're looking for. And we can see that that's the case, right? So we have this column of all ones. Here I'm looking at the first 5 rows, and you can see that this second column is the one that get different values, right, corresponding to different inputs. So now that we have done this, we have to implement what we have here. So we have X transpose X, which we call it A, and then X transpose Y, which is B, and then find an appropriate way of solving this equation in Python. So in this case, we form A, we form B, and in order to find theta from NumPy linear algebra module, you can find this class, which you can use for solving least squares problem, which you provide A and B. You can also provide some additional information to deal with some of these singular values of this, this matrix that we have here, this A. But again, that's something that is beyond the scope of this course, and it's kind of like optional here. But you can see that if we solve these least square problems, that's what this stands for, you can see that we get this information where it tells us this theta, which is now a vector with 2 elements. Theta 0 is 3.7, and then theta 1 is this 6.7 times 10 to the negative 5. So if you're wondering why this is really, really small, is because if you look at the column that corresponds to these features that this number will be multiplied to, you can see these numbers are really large, like they're like 10 to the 4. And therefore, this value here should be very small, right? So that when you multiply them together, overall, it gives you something that is in the range of these y values. You can see that these y values are like, in the range of like, 5, 6. I believe based on what we did before, the maximum value is close to 7, right? So obviously, if you don't have a very small theta one, when you multiply by this very large number, there's no way you can get anything close to here. So that's why you get this very small theta one here. And once you solve this problem by finding this theta, now, if you remember, we said that in order to make predictions here, actually, one thing that you can do is to multiply this x and theta, and that will give you all these f of xn to f of x1 to f of xn, right? So you just need to multiply the metrics that you have for your data by this data that you just found. And if we do that here, right, so we create some test data points, the variables that we have here for the GDP are from 25,000 to 60,000. We also add the column the column of all ones, because you have to do the exact same pre-processing. And then we can feed it into this function that we have here. And you can see that that's the regression line, or the line of the best fit that we have for this problem. And these, blue ones here are our training data points that we have. So overall, you can see that this is a really good model. And remember that here I'm using some of the customization in Matplotlib to create a figure that is easy to read, increasing font size, figure size. These things are very helpful, and also adding legend to show you that, this red dotted line is our prediction line. So now with this example that we just work on, now we can talk about linear models for regression in a general case. And by general case means that in this case, this xn, which is the input, can be more than just one variable, right? So before we just had GDP information, now we can have tons of more variables, right? We can have, for example, like lifestyle factors. We can have like, education factors, etc. Right? That's definitely a much better model than just looking at GDP and life satisfaction. And therefore, in this case, we can just extend the model that we have, that, this is what we just had before, but now we have more variables, and for each variable or feature, we add a corresponding coefficient that we have to learn. And you can see that, again, this can be written as a dot product or inner product. And as we said, we can assume that this theta 0 is multiplied by 1, which means that in this case, our data set, that in terms of features, now we have d plus 1 features, which starts from x0 to xt. And therefore, we have d plus 1 parameters that we have to find. And the prediction model, the way it works is that you find the dot product or inner product between theta and x, which is this weighted sum, and that's our prediction. So this is the generalization of y equals mx plus b that you have seen in 2D spaces to higher dimensional spaces. And we can replicate the same analysis where you have your loss function, and you can write your loss function in terms of this compact representation, where this x is the data metrics, where each row is a data point, or sample or observation, and each column is a feature or predictor. And therefore, this is of size n by d plus 1. And that's exactly how scikit-learn expects you to provide this input data. Now we have this vector of unknowns that we have to estimate them. And these are the ground truth outputs. And therefore, we have an optimization problem that we have to solve that we can use scikit-learn. As we said earlier, we can show that the gradient, which is the vector of all partial derivatives, has this very nice format. Obviously, if you have no linear algebra, this is not too difficult to show in a general case, but we already have done this for the 2D case. And you can solve these using this closed form solution, which is known as the normal equation. But what we really want to do in this video is to understand how to implement this using scikit-learn, because this course mainly focuses on programming aspects. So make sure that you look at the documentation page, because that's where you find a lot of information about what input arguments you can provide for this class. Remember, this linear regression is a class, so you have to instantiate it to create an object. So you understand the parameters that you can provide, the attributes that this object will have, such as the coefficients, the intercept or the bias term. You can also, for example, find the rank of the data matrix X if you're familiar with that topic from linear algebra. So you get a lot of useful information. And also, if you look at here, you have these methods that we saw some of them before, like .fit, where you can fit, which means that you train your model and finds data. The predict method, where you can make predictions. And if you look at it, there are also other options too. So we don't really need the other options very much in this course, but it is always a good thing to look at them just in case when you need them. So going back, I just summarized this information here in terms of the differences between parameters, attributes, and methods. These are the three things, regardless of what you're using, whether it's linear regression or ridge regression that you used for your homework before. You need to understand and read these important pieces of information. And for linear regression, the fit method, as we said, it expects the data matrix X, which is n samples by n features, meaning number of samples by the number of features. And number of features here is the number of variables or predictors that we have. And Y is the one that represents the target values or labels associated with the input data matrix. So in this case, we can print the shape of X and Y. So something here that we say, which is very important, is that even though you have one feature, this n features is one, make sure that actually that's reflected in the shape that you have here. Right now, based on what we see here, x.shape, NumPy assumes that this is a one-dimensional array with 27 elements. But what you really want to have is to see that X is a two-dimensional array with 27 rows and 1 columns to make sure that this matches this definition here. So in order to do that, you can always use x.reshape and put -1, which means that you don't want to calculate the number of rows, but you want to enforce to have 1 column. So in this case, if I run this, you will see that now I get something very similar to what's inside X, but now we have these 2 square brackets, which, this tells us that now we have a 2D array. We have 1 column and 27 rows. And if I use dot shape here, you can immediately see the difference. Now, this version of X, where you reshape it, is actually 27 by 1. And to make this again clear, if you don't want to use -1, you can use 27 and 1. And that's the same exact thing, but it is more helpful if you just use -1. So now let's revisit the GDP data. So in this case, from scikit-learn's linear model module, we're going to import linear regression, and then we're going to instantiate it. And then, as we said, you have to reshape this X to make sure this is a 2D array and provide both inputs and outputs and use that fit method. And after that, now you can look at these attributes where the first one is the intercept, the second one is the coefficient. So you can see that here we get very similar values to what we had before, 3.7 for the intercept, and this number, which is in the order of 10 to the -5 for the coefficient. So something that you may say is that, well, why this coefficient is too small, right? This is not a good idea to have like this very, very small number compared to this number, which is a few orders of magnitude larger. So that's where you can use the idea of pre-processing. So if you remember, in one of the lectures, we created a version of this min-max scaler, where if you provide a bunch of numbers, it scales them so that they're always from 0 to 1. So we can do the same thing here actually. And for the data matrix X that we have, we can use this min-max scaler. So very similar to any other ways that we can use object-oriented programming. You first instantiate it and then use a suitable method here, fit transform, to transform this. And now we can repeat the same exact process to train a regression model. And you can see that now we have a much more, I would say, sensible result where we have intercept 5.5, and then the coefficient is 2.28. And just to show the difference here, we can look at this x min max to show that actually how it works. So you can see that before, when we look at x, I think we have a version here, you got these numbers that, you know, they were like 26,000 something, 27,000, right? So they were extremely large. But now when we look at this x min max, because we use this min max scaler, they're all from 0 to 1. So you can see that the maximum is 1 and then the minimum is 0. So this is somewhat easier to work with because you don't have to deal with these large numbers. Okay, so now let's look at how this model performs. In this case, we are using the version that is scaled using that min-max scaler. And so this means that for your test data, you have to use the exact same thing. You have to reshape it and then transform it. And if I run this, so you can see that now the GDP, the scaled version, is from 0 to 1. As we said, that's our input. And this is our regression line. And as you can see, the intercept here is 5.5, and the coefficient is, the slope is 2.28. So we didn't really change the problem, but just scaling the data, we find results that are more stable and easier to work with. So now once you train your model, in these cases that you have a 1D problem, you can visualize the regression line and see whether this is a good model or not. But in many cases, if you have like, a high dimensional problem, you cannot visualize anything more than a 3D problem, right? So we need to have quantifiable ways of measuring the performance of regression models. And in order to find the list of all evaluation metrics, you can go to this link. So as you can see from now on, I can point you towards like the relevant part of scikit-learn to read and understand what possible options we have. Obviously, we cannot cover all of them in this course, but you can see that, for example, for regression, we have a lot of metrics that you can use. So whenever you want to use one of these, you can further, go towards the, user guide or documentation page and, understand how this, in this case, evaluation metric is working. So one of the ways of measuring performance is using mean squared error, where we have these true and predicted values. That's why we're using hat for predicted, which is the average loss, and the loss is measured using the quadratic loss function. And so the value you get after calculating MSE is a squared unit of the output. For example, let's say if it's a physical quantity, this means that now the error is in the units of the error is squared of the original output. And therefore, one possible way of handling this problem is to look at the root mean squared error, or RMSE, where you take the square root of the MSE that we did before. So in this case, the error that you find has the same units as the original output. And as we said, in this case, the best possible score is 0 if you have perfect predictions. But in general, this is a non-negative quantity, and larger values show more disagreement between true and predicted values. So you want to reduce this mean squared error or root mean squared error as much as possible. And just to show you how this works, we here create like a true versus predicted list, and we feed this to this mean squared error. There is an option inside this, which is called a squared, which is by default set to be true to return mean squared error. But if you set that squared to be false, then you find the root mean squared error. So here you can actually calculate this by hand too to make sure that we get the same results, but this should work properly. Another thing which is very important to measure the performance of regression models is known as the coefficient of determination, also known as the R2 score. And that's the formula for R2 score. So it's 1 minus, and then we have this term here, where in the denominator, we subtract each true output by the mean of the true output. So this y bar is the mean or average of the true outputs. And in the numerator, we have the sum of the residuals, right? So yn minus y hat n, where y hat is the predicted value. So this metric is very helpful because if you have a perfect model, then these residuals, they're all zeros, which is in the denominator, inside is in the numerator of the second term, which means that then the coefficient of the determination is 1 minus 0 or 1. So that's the best possible score. In this case, higher scores are better. So it's kind of like opposite of MSE. And you can see that if these y hat ends, they're all equal to y bar, meaning that the predicted value is just simply the average of the output in your label data set, then you get 1 minus 1, which is 0. And this metric can actually be negative too, meaning that you can get a situation where this fraction that you have here is greater than 1, which means that the whole thing is less than 0. But ideally, you want to be as close as possible to 1 and not below 0, because then means that you have a much better solution where you can just predict the average of output for all your training data points as the prediction for any new data point, and that will give you R squared of 0. And this quantity, again, the numerator is very important because it also has a very specific name, which is called residual sum of squares, or RSS. So that's the one that measures the amount of variability that is left unexplained by your machine learning model. And remember, the best possible score is 1, and a number near 0 indicates that the model doesn't explain much of the variability in response, because in that case, you can simply just always make predictions by looking at this y bar, which is the average of the output in your label data set. And you can see that in this case, if you find R squared, because these two lists are somewhat close, you can see get something which is close to 1. So in this case, we have reasonable value for R squared. The last topic we want to talk about today is about polynomial regression. So as we said, the linear model that we have is a really good thing if you have a linear relationship between inputs and outputs, but definitely it does not work if we have nonlinear relationships. So one way to get around this is something known as polynomial regression, which is a very simple trick. So as we said, the prediction model here is the dot product between these unknown parameters and the vector that you have for your inputs. And one thing you can do is actually you can apply a transformation on your input data. So if you remember, we had this framework before where we talk about data transformations, where you have polynomial terms, meaning that if you just have one input x, which is a scalar, then you get 1x, x squared up to x to some degrees. And if you have higher order terms, like let's say x and y, or x1 and x2, then you get x1 squared, x2 squared, x1 times x2, etc. And in order to do this transformation is actually something that is built in scikit-learn inside the pre-processing module, which is called polynomial features. To just show you how this works, we can actually look at like a synthetic problem where we create this data matrix called X, right? And this X right now has 3 rows and 2 columns. So if you use these polynomial features, and this is a class, so you have to instantiate it, and we set the degree to be 2, so we want to look at degrees up to 2, and transform these data metrics that we have here, you can see that we get the original features, which is like 0 and 1. Let's right now look at the first row. Then we get 0 squared, 1 squared, and 0 times 1. So that's what we explain here. And the same thing for the second row. So you can see that we have 2 and 3 that we had before. Now we have 4 and 9, and then the multiplication of these two, which is 6. And the same thing for the last row. And here I put include bias to be false, but if you set that to be true, you also see that extra 1 that is here, right? So that's exactly consistent with what we have here. In general, you can set this include bias to be true, and you get this extra 1. And after that, you get your original features, which we have before, and then the higher order terms. So to see how this works, let's create a synthetic problem, where in this case, we have these X values, and we use this quadratic function to generate the data. So if we plot this data, you can see that that's how this training data looks like. And the goal is that can we find a nonlinear regression model using these polynomial features? So in order to do that, you need polynomial features that we just discussed. You also need to incorporate these polynomial features with or into linear regression. So in this case, we can use something called pipeline. And in the next slide, I'm going to talk more about pipeline and why it is so critical in data science and machine learning. And also, we're going to import linear regression. So pipeline is kind of like a glue. What it does, it says that we wanted to do 2 things. For any input, we want to first apply this polynomial transformation. And then on top of that, when we get these new higher order features, we want to apply linear regression. So although we are using linear regression, because before applying linear regression, we have these polynomial features, our model can indeed now be nonlinear. And we call this object now any name you want, for example, like pipe. And very similar to linear regression, now you can use .fit and then .predict. And if you follow here, the rest of the code here that we have for plotting, you can see that these are the data points that we had, and this is our regression curve that we have. So right now, this is not anymore just a linear model, and it can actually be a nonlinear curve, as you can see here. So what is exactly pipeline? So pipeline is extremely helpful because in many advanced data science and machine learning problems, you want to do multiple transformations and you want to do this in a very efficient and compact way. So what you can do is that you can create this object, which includes this chain of transformations. And as we said, it can be more than one. And at the end, you put what scikit-learn calls an estimator, which is basically a regressor or classifier. So these transformers are like polynomial features. Min-max scalar are classes that implement both fit and transform methods. And estimators, as we said, are the ones that they learn from data, meaning that, in general, like classifiers or regressors, these are the ones that implement the fit and predict method. So that's why when we said pipe.predict, it knows that it has to call the predict method of the last part. So this is very a smart way of doing this sequential transformation of data and then applying an estimator. And the last part of this lecture, what we're going to do is we're going to look at the impact of the degree of polynomial on the predictions of your model. So in this case, we have this for loop. We go through 3 cases. And you can see here we are considering degrees 30, 2, and 1. So three values for the degree parameter. And then the width of the line that we want to plot and different colors. And in each case, we use the degree that we have from this for loop. And also in this case, we're going to add more transformations. We're going to add the standard scalar transformation, which is the one that makes sure that the inputs are centered at 0 with variance 1. We do the polynomial features and then linear regression. So that's the pipeline that we have to just show you that we can indeed have more than one transformation. So right now we have 2 transformations and 1 estimator. And if we follow the same path and do .fit and then .predict, you can see that we get this very interesting curve, right? Which explains 2 very important topics in machine learning. So you can see that in this case, because the data that we created, we actually are here using this side information that we know that it's coming from a degree 2 polynomial. The curve that we find for predicted values according to degree 2 matches this data set very well. But obviously, when we use a degree 1 polynomial, which is just a linear regression model, you can see that this model does not fit this data very well. And in fact, it has a lot of bias, meaning that it does not capture the variability in the data. So this is what we call as underfitting, meaning that when the model is too simple to capture the underlying structure. But on the other hand, we have something else which is even more important, which is overfitting. When the model is too complex and it starts to capture not just the underlying trend, but also the noise present in the data. So you can see here, when we set the degree to 30 using this green curve, yeah, this curve is going through almost all the data points, but obviously has a lot of oscillations and abrupt changes, especially you can see in these areas at the beginning and at the end. And that's really bad because now if you have a test data point, which is around, let's say, 2.6 or 7 here, then you may end up with really, really bad predictions that are far from where, these data points are. And therefore, this is something always important to consider, that you have to use the train test approach that we said to make sure that the error on the test data is comparable with the training data. And if it's not, and in this case, the error on the testing data should be much greater than the training data, that's we call as overfitting, which means that the model does not generalize well. So that's something very important to consider when working with nonlinear models to make sure that the model generalizes well. So in this case, again, we have some interesting homework assignments working with a data set that is included inside scikit-learn known as diabetes. We want to here, train regression models and be able to evaluate the model. We also have another data set called empty cars data set. So in this case, we want to use horsepower and weight of the car to estimate MPG or mile per gallon. Also, we are working with California housing data set. So this is a point that we can use these real data sets to extract knowledge and perform data analysis using machine learning methods. Thanks for watching. Hello, everyone. In this video, we talk about classification in machine learning. And in particular, we start with the problem of binary classification. In this case, we have 2 possible outcomes or labels, and we can represent these using 0 or 1, where 0 is one class, 1 is the other class. As mentioned in previous videos, in this case, 0 and 1, they do not have any numerical value, and they're simply 2 different numbers that we use to distinguish between data points that belong to one class versus the other one. Therefore, it is common, depending on the context or textbook, that sometimes these 2 classes are labeled as -1 and 1, or positive and negative. For example, in the version that we have here, 1 can be considered as the positive class, and 0 you can think of that as the negative class. Among classification algorithms, we mainly focus on logistic regression for this notebook. And because it's one of the most widely used classification algorithms, and it's a direct generalization of linear regression that we just had. However, there are some clear differences between linear and logistic regression in a sense that in linear regression, we are trying to predict a continuous label, but in this case, we are trying to predict a discrete label, right? So this is, either 0 or 1. And also, as we're going to talk about in this lecture, loss functions that we use for classification problems are typically very different than their regression counterparts. To get us started and define logistic regression involves a probabilistic model of the form py given x and theta. So this is what is known as conditional probability, meaning that we want to find the probability that the data point belongs to one of these two classes given the input, right? So remember in the lecture or 12, we had the example where we wanted to predict bank loan default based on income and debt. So in that case, income and debt, there were two features that they were given as inputs. And so that's what we have here for X. And Y in that case was whether an applicant will default or not. So it's either 0 or 1. And theta here is very much similar to the theta we use for linear regression. It is used to represent the unknown model parameters. So in order to understand logistic regression, we need to recall the probability mass function of the Bernoulli distribution. Just to recap, Bernoulli distribution is a random variable which is discrete and has two possible outcomes, 1 and 0. This is something we can use, for example, to model the outcome of a coin flip, right? So in this case, we get either heads or tails, and we can call this like 1 and 0. And Bernoulli distribution is very simple and useful because it has only one parameter theta, which tells us the probability that y equals 1. And obviously, because we have a binary case, then we also find the probability that y equals 0. So in this case, the probability that y equals 1 is theta, which is the parameter of the Bernoulli distribution. And since the sum of probabilities must equal 1, the probability for y equals 0 is 1 minus theta. And in fact, we can write this in a very compact form. As you have seen, this is something that we always want to do in machine learning and data science, to write functions in very compact forms. And we can write this in this form of theta raised to the y, 1 minus theta raised to the power of 1 minus y. So in this case, you can see that if y equals 1, right, because y can only take two values, 1 or 0. If y takes the value of 1, then we get theta. And here, because we have 1 minus y, we get 0, and any number raised to the power of 0 is 1. So this whole thing is theta. And if y equals 0, then we get 1 minus 0 here, and we get 1 minus theta. So that's why you can write this step function here, or say this piecewise function here in this compact form. And therefore, the model that we use for logistic regression is based off of this Bernoulli distribution. We say that the probability that the output y given x and theta is this Bernoulli distribution, where the theta, or the probability that we need to define the Bernoulli distribution, is coming from this function of the input applied to the sigmoid or logistic function. So that's why we call this method logistic regression. So we have to explain a couple of things here. The first thing is the sigmoid or logistic function, to define this and understand why we have to use this. Here we have the mathematical expression for logistic function, which is 1 over 1 plus e to the negative a, or as we have written here, exponential of negative a. So we can use mathematical tools to find the limits of this function and horizontal asymptotes and things that we have, we see a lot in calculus. But again, this is more a programming course, so we want to use tools such as NumPy and Matplotlib to be able to visualize this function. And therefore, we import NumPy as NP, we import Matplotlib. Also, we select a range of a values from -10 to 10. And here is where we define this sigmoid logistic function, which is 1 over 1 plus e to the negative a. And then we plot a and the values that we get from this sigmoid function. So if you run this cell, you can see the shape of the sigmoid logistic function. So here we have restricted the x-axis, or here we call it a, to be between -10 and 10. This, in fact, can be from -infinity to infinity. But the most important thing is the shape of this function. And one thing that we have to pay attention to is that the range of this function, and the range is the set of values that this function can take, as you can see here, is from 0 to 1. So this is why we need the sigmoid or logistic function for classification purposes. Because if you look at what we have here, this sigmoid or logistic function acts as the probability parameter for the Bernoulli distribution. And we know that the probability of a random variable is always between 0 and 1. So if we do not use this sigmoid or logistic function, we can end up with a value of this function f, which is outside the acceptable range of 0 to 1. Therefore, in this model, we assume that we can have any function of x parameterized by this theta. But after we find this function, we have to pass this through this sigmoid or logistic function. And this sigmoid or logistic function, if you look at the y-axis, is always from 0 to 1, which means that now we get a valid probability score. So that's one very important piece here. Now you may wonder, well, why should we use, this sigmoid or logistic function? There might be other options as well. So here it gets a little bit technical, but I wanted to include this information here, that the sigmoid or logistic function has a very nice property in the sense that once you find its derivative, so you see that this is the function that we have, we can write it as 1 plus e to the negative a raised to the power of -1. Once you take its derivative with respect to its input, which is a, and you simplify this, you can actually see that the derivative can be written as the sigmoid function times 1 minus the sigmoid function at that point a. So this is a very useful property because this function has a very nice closed form derivative. And in practice, yes, you may be able to define different functions that they have the same range, meaning that the output is always from 0 to 1. But then those functions may not have such a nice property. And since we need to find gradients and derivatives that we talked before, this means that this can be extremely helpful to have this knowledge. So in this cell, again, we want to use programming here mainly rather than going through math in a very comprehensive way to get a sense of these results. So in this case, we're going to plot the sigmoid function and also its derivative, which is sigmoid times 1 minus sigmoid, as we just have here. So you can see that here we get the derivative plotted in red, and this makes sense because where we are, for example, at 10, you can see that the slope of tangent line is, almost 0, and that's what is shown here. And the same thing with -10, and you can see that the max derivative or the slope of the tangent line is actually at 0, which is 0.25. Okay, so now we know that this is the sigmoid function, this is its derivative, and its derivative has a very nice format. So what does this mean in terms of binary classification, which is the main topic of this video? So you can see that now we can actually find these probabilities of the data belongs to class 1 and the data belongs to class 0. So the probability that data belongs to class 1 is the sigmoid of A, right? That's the parameter of the Bernoulli distribution, which is 1 over 1 plus e to the negative A. If you want, we can multiply both numerator and denominator by e to the A to simplify this, and that's what the result that you get. And remember, since these two events, y equals 1 and y equals 0, are the two only possible cases, the sum of probabilities must equal 1, which means that the probability of y equals 0 is 1 minus the probability of y equals 1, which is sigmoid of A. And you can simplify this based on subtracting this value from 1, and that's what you get. And similarly, you can multiply this by e to the A for both numerator and denominator. Something also important to keep in mind here is that if you divide this probability of y equals 1 by probability of y equals 0, they have the same denominator, as you can see here. So this means that these two terms will cancel, and you just end up with e to the A. And now if you take the log of this, now you just get what you pass through the sigmoid function. So what does this mean? So this means that if you want to find the inverse of the sigmoid function, which is called the logit function, you need to find log of p over 1 minus p, right? Because p is the probability that y equals 1, and the probability that y equals 0 is 1 minus p. And this is what is known as the logit function, which is the inverse of the sigmoid function. Since these functions are very useful and popular in machine learning, you can see that they're actually already implemented and they're part of the SciPy package or library. And inside that, there's a module called a special, and we have these two functions. So this exp_it that refers to the logistic function, and logit obviously is the logit function that we have. So these two are inverse functions. And we can actually plot them, right? So here we use subplots that we learn when talking about Matplotlib. We create a 1/2 grid, and you can see that in one case we are plotting this logistic function, and then in the second plot the logit function. And if you run this, you see the familiar logistic function and then the logit function. And you can easily interpret this, right? So you know that if you pass 0 to the logistic function, then you get probability 0.5. And the same way, you expect that if you want to find the inverse function, if you provide 0.5 to this logit function, then you get 0, right? So this means that the logistic function is a very nice function because it has closed form derivatives. It has an inverse function. So if you want to know what input to the logistic function will give you 0.5, you can actually use the logit function and then find this value. So these two together will give you a lot of information. So now we are at the step that we can formally define logistic regression. So remember, in logistic regression, the logistic refers to the logistic function. And the reason that we call this logistic regression, even though it's technical classification problem, because it does look very much look like linear regression, right? So this function f that we have there is actually assumed to be the dot product between the input vector and the vector of parameters. And so overall, for logistic regression, the probability of y given x and theta comes from a Bernoulli distribution with this parameter sigmoid of theta transpose x. Which means that what we really need to remember and keep in mind is this final formula that we have here, that the probability of y equals 1 given x and theta is the sigmoid or logistic function of the dot product between x and the vector of unknown thetas. And that by definition is 1 over 1 plus e to the negative theta transpose x. And when you find this probability, you also have probability of y equals 0 because that probability is 1 minus this value. Okay. So the next question is, how can we find this theta, right? Because that's the whole point of model training or fitting. We need to be able to find unknown parameters. And for that, we need to define a loss function. And in this case, we cannot use the quadratic loss function because, again, these 0 and 1 are just some labels and they do not have any numerical value. So one idea is to use the loss function that we had in lecture 12, which was the misclassification rate, where we use the indicator function that measure whether the true output or the true label is equal to the class label that we predicted. But it turns out solving that problem is not an easy problem. So we need to find a loss function that can be easier to optimize. And the loss function that we mainly use for logistic regression is the one that is provided here. That if the true output is 1, then the value of loss function is negative log of mu n, and mu n is what we get from the logistic function. And if yn equals 0, if the true class is 0, then we get negative log of 1 minus mu n. This is somewhat complicated to figure out why this works just by looking at this equation. But again, in this course, we can use Python for visualizing this loss function and making sense of what it does. In order to do this, we're going to define this loss function, and it's called cross entropy loss function. That's what this CE stands for, which it takes two inputs, y and this mu. And remember, mu is the probability. If y equals 1, then we have to return negative log of mu. And else, which means that if y equals 0, then we have to return negative log of 1 minus mu. And in order to find mu, we're going to create some numbers from negative 10 to 10 and pass them through the sigmoid function or logistic function to find this mu that we have here. And from now, we can just visualize these two loss functions. Let's start by looking at the case where y is equal to 1. So the true label or true output should be 1. So in this case, if you find that the probability that y equals 1 is also 1, that means that you're 100% confident that what you're predicting should be 1, and that matches with the true output, which is 1. And therefore, in this case, the loss or cost of this prediction is 0 because we are not making any mistakes. However, the cool thing about the cross entropy loss function is that as we get this probability closer and closer to 0, which is undesirable because that means that we are making a worse prediction, then the cost for that increases substantially. You see that this is almost going to infinity, right? So that's why this is a very nice model for training classification problems. And the same thing happens with probability with this second case, which is y equals 0, the blue curve. So in this case, something you need to keep in mind is that probability of y equals 1 and probability of y equals 0, they're complementary, meaning that one is 1 minus the other one, because the sum of probabilities must equal 1. And therefore, in this case, if probability of y equals 1 is 0, this means that probability of y equals 0 is 1. And the data point that we have belongs to class 0, so there is no penalty to pay. And as we make worse predictions, meaning that now the probability of y equal 0 gets closer to 0, because now you have to use 1 minus this number. Now this value of loss or cost function increases substantially. However, in general, in my opinion, it's just easier to focus on one of these two. For example, y equals 1, the orange curve, because that matches better with what we have here as the label. And here it's very clear that when probability of y equals 1 is 1, and the data point belongs to class 1, there is 0 error. And as you get closer and closer to this probability being 0, then obviously we are making worse predictions and the cost should increase substantially. And this is consistent with what we have here. So you can look at the behavior of these functions as, this mu gets close to 1 or 0. But overall, in this course, we can always plot these functions, and it's much easier to interpret them. Okay, so now in terms of using logistic regression in scikit-learn, the nice thing is that it follows the same path as what we did before. So the very first thing, we need to import the logistic regression class from linear model. It's a linear model because, as you saw here, the assumption that we make is that this function, which is inside the sigmoid function, is a linear function. And we can do this by importing logistic regression from scikit-learn.linear model. And then we need to instantiate this class to create this object, which I call here model, but this can be any name you want. And here there are some parameters that also you can choose from. For example, you can choose the regularization strength, which is an important way of avoiding overfitting that we had in the previous lecture. Also, the exact optimization technique that we want to use. And since the optimization technique here is an iterative process, we can set the maximum number of iterations. So depending on how much you understand the underlying mechanisms of logistic regression, you are more than welcome to adjust them. But if you don't know very much about them, you can use them as is without providing extra parameters. And after that, we use model.fit. So that's the part that we are going to minimize the loss function that we have. This cross entropy loss function average on the training data. And then in the prediction stage, now here is the main difference with this one and regression problems. We have two methods. We can use predict to predict the class label, or predict proba to predict the probability of each class. Because remember, what really logistic regression does is to give you this probability that y equals 1. And this means that you have the right to say that, well, I only assign label 1 to a data point if this probability is above some threshold. So if you don't have any kind of preference, you can put the threshold at 50%, meaning that if it's more than 50%, then I'm going to assign that to class 1. But if for some reason class 1 is a very important class and you want to make sure that you are not misclassifying data points by saying that they belong to class 1 when they don't, then you can increase the threshold for the probability and say that, well, I only assign a data point to class 1 if this probability is above 80 or 90%. So therefore, in scikit-learn, you have the option to find the probability if you want to decide yourself how do you want to assign these data points that you have in this test to the classes, or just use .predict, and this is by default will use 50% or 0.5 as the threshold. And similar to regression problems, we also have to evaluate this model using some metrics. And here we have several metrics such as accuracy, precision, and recall that I'm going to explain them in the next slide. So in order to evaluate classification models, especially in the case of binary problems, it is very common to form something called a confusion matrix. So this confusion matrix, as you can see, the rows are the true labels. So these are the labels that we are given in the data set that we have. And the columns are predicted labels. And here we use the more conventional notion of positive and negative classes. So instead of 0 and 1, we call this -1 and 1. And therefore, if a data point really belongs to the negative class or the 0 class, and it is predicted to be negative or 0, then that's considered a true negative. And the same thing with true positive, right? If a data point belongs to the positive class and it is predicted to be positive, that's true positive. And now the misclassifications happen in these off-diagonal terms. If a data point is supposed to be negative and predicted to be positive, that's a false positive. And similarly, if a data point was supposed to be in the positive class and now it's in the negative class, that's a false negative. And based on this, now you can define various metrics. So what is accuracy? So accuracy is the total number of correct predictions divided by the total number of predictions. So this means that it's true negative plus true positive over true negative, true plus true positive, plus false positive, plus false negative, right? So that's the ratio of correct predictions. But then we can also define these more appropriate metrics depending on the application, where we look at precision, which is false positive over false positive, precision, which is true positive over true positive plus false positive. That's the equation that we have here. And what this tells us is that among the data points that are predicted to be positive, how many of them are actually positive, right? So it looks at this column that we have here. Or in other words, it's really trying to look at the number of false positives. On the other hand, we have something called recall. And recall is what we have in this row. So it's true positive over true positive plus false negative. And this tells us among the data points that are actually positive, how many of them are correctly classified. That's what is also called true positive rate. And in some domains, for example, medical domains, this is what is mainly referred to as sensitivity. And again, in medical domains, also they like to define something called a specificity, which is the true negative rate. So this means that among the samples that are actually negative, how many of them are predicted to be negative? So it's true negative over true negative plus false positive. And this is what is known as the true negative rate. So I would definitely recommend you to have this picture in mind, because that really is going to be helpful to figure out what precision, recall, and other metrics are. So that really is helpful. But let's see how this works when we are using scikit-learn. So in this case, we're going to use that iris flower data set that we have used before. And now if you look at here, you can see that this data set, which is part of scikit-learn, has multiple portions. So we have data, target, and the data means that that's the X matrix, target is the Y vector, Also, we have the target names, feature names, etc. So just to show this is what we have in iris data, right? So this is just the data or features part. So we have the sepal length, width, petal length, and petal width. And in this case, we have 150 data points, and each one has 4 columns of features. Then we can look at where we store the outputs or the class labels, and especially we can use value counts. You can see that this is a very well-balanced data set in a sense that we have 50 data points with class label 0, 50 with class label 1, and 50 with class label 2. So this one is actually 3 classes, but you're going to see that we can convert this to a binary classification problem. So these are the target names, the names of 3 species of the iris flower. And the way that we convert this to a binary classification problem is by checking to see whether the flower belongs to this Virginica species or not, right? So once you use this, right, so this is either true or false, which means that now you have a binary classification problem. You want to predict whether the species of these flowers is one of these 2, Setosa or Versicolor, or this Virginica. And in this case, we are only working with one of the input features first, because that makes it a little bit easier to visualize this classifier, and that's the petal width. Obviously, we have more features here, but that's the only one that we want to consider at this point. And as we said, we always use train test split. And in this case, we can instantiate this logistic regression and do model fitting. So this means that now we're going to find parameters that minimize the loss function. Okay, so now we're going to create some test data points. That's what we call it, this, X new. And these are some numbers from 0 to 3 that we use linear space. And in this case, I want to mainly show you the probabilities. So that's why I'm using predict underscore proba. And if I run this cell right now, so you can see the main idea here, right? So we have this petal width on the x-axis. So this has values from 0 to 3. And then the probability, what we get from this predict proba, is on the y-axis. And we know that probability is always from 0 to 1. So this means that the probability that the flower belongs to this class, this Virginica, it increases as the petal width increases, right? So for example, when petal width is 3, we are almost 100% sure that that flower belongs to the Virginica class. And we have also the other way too, right? So as the petal width decreases, this probability gets closer and closer to 0. As we said earlier, what you can do, you can always put the threshold at 0.5 or 50%. So this means that anytime that the petal width is greater than what number that we have here, then we assign that to the Virginica class. And if not, we're gonna assign that to the other class, because then the probability that you see through this blue curve is greater than 50. And remember, because the sum of these two probabilities must equal 1, that's why they have like this kind of like opposite behavior, right? So in this case, you can see that once one increases, the other one should, decrease. And to show these probabilities for some of these test data points, I'm using this predict proba. And this tells us for the first test data point, the probability that it belongs to class 0 is 0.84 almost, or 85. And the probability that it belongs to the other class is 0.15. So the sum of these two must equal 1. That's the principle of probability. And you can see that now for the test data point, the second one the probability that belongs to class 0 is 0.99. We are very confident. And then the probability that belongs to the other class is now almost 0. And you can see that now we have kind of like the opposite behavior for the third data point. So this means that this X test goes through the linear transformation, goes through the sigmoid or logistic function, and it gives us these probabilities. And if instead of predict proba, we use predict, now we lose all this probability information and we just get some labels, right? So in this case, class 0 is false, class 1 is true. So if we have to assign this to one class, then it definitely belongs to this first class, which is class false, which means that it's not the Virginica species. And the same thing for this one, for the second data point, but for the third test data point, that definitely belongs to the class that we have in mind. So that's true. So therefore, if we want to change this rule, we can always look at predict proba and say that, well, I'm going to assign this, let's say, to the false class, not only if I get at least 50 or 60, but maybe at least 70%, right? So that kind of like changes the way that we assign labels to these data points. So here we have some homework problems to practice more with this iris flower data set. And you're going to use the train test split from model selection with this split ratio. And now you want to evaluate the model using the metrics that we discussed, such as accuracy, precision, and recall. Because in this example that we just had here, we really didn't officially or formally evaluate the model. We just wanted to interpret these probabilities that are assigned to these data points. But in this case, you work with these predicted labels, and you're going to compare them with the true labels using these confusion metrics. And remember that all these precision, recall, they are implemented in scikit-learn, and we know that they are part of the scikit-learn.metrics module. We're also going to work with this Wisconsin data set. This is a very also interesting data set that you can use for training classification models, and we follow the same procedures. We're going to use logistic regression model to predict classes for testing data points and then evaluating the model. And in the last problems, we want to work with these probability thresholds that we just mentioned, right? What happens if we use 0.5, which is the common value to assign data points to classes, to 0.6, 0.7, 0.9, these different values. And in this case, you have to use first the predict proba method to get these probabilities, and then based on those, you can assign labels to data points. Thanks for watching.
Hello everyone. In this video, we talk about the basics of neural networks and deep learning, and also discuss one of the most important deep learning libraries and frameworks known as TensorFlow, developed by Google. So let's get started with the basic definition of neural networks. You can think of neural networks as computational models that they are motivated by the human brain's structure and functionality. They're designed to recognize patterns and solve complex problems in various domains, from autonomous driving to robotics to medical imaging and so on. Unlike simpler linear models that we have seen so far, such as linear regression and logistic regression, which they directly map input features to outputs, meaning that they usually form a weighted sum or combination of input features that are given to us, neural networks introduce what is known as hidden layers between inputs and outputs, and therefore they provide much more greater expressive power. In order to understand the basics of neural networks, I'd like to start with a very simple example. In this case, we create a one-dimensional synthetic data set, which means that we have one input feature and one output.
And we assume that the input-output relationship is provided by a polynomial degree of 2 using this very simple equation. So meaning that here you have an input x, you plug in it into this equation, you find the corresponding output, and a and b and c are constants. Based on the previous lectures that we have, we know that we can use polynomial regression to solve this problem, meaning that we can define a pipeline, use polynomial features, and after that, apply a linear regression to transform features and solve this problem. However, a big challenge there is that you have to directly enforce the degree of polynomial. So what we really want to do here is that can we have a more adaptive approach to solve this problem where we just provide a hidden layer, and then the hidden layer can magically extract this input-output relationship. And once we create this data set, we're going to talk about the TensorFlow, which is a very popular deep learning framework designed by Google. And TensorFlow can be a little bit complex for beginners. Therefore, there is another high-level API or application programming interface which runs on top of TensorFlow, known as Keras. So therefore, Keras and TensorFlow very much are, related, but Keras is much simpler, and I can say it's, low code or high level in that sense, meaning that you don't have to know all the specific details that you need if you want to directly use TensorFlow. But once you get to know one of these two, usually it's easy to use the other one, or also other popular deep learning libraries such as PyTorch, which that one is designed by Facebook. So in this example that we have, so we're going to start importing libraries that we know. So we import NumPy as NP for arrays that we want to create. We import Matplotlib. We import train test split from scikit-learn. And these are these 3 parameters that we just discussed, A, B, and C. And then very similar to what we did before, we create a set of equally spaced data points here from -10 to 10. And we have 400 of them, and we plug in it into this quadratic form. And of course, we can add a little bit of noise. Here we use like a normal or Gaussian noise to make this problem a little bit more interesting. And once you create your data, as we said, usually you want to use train test split to divide the data into training and testing sets. And this is the size of the testing set, which is 20% of the entire data. And then as we have seen this before, it's always a good idea to work with 2D input arrays, even though they are technically 1D, because the way that scikit-learn and Keras they look at these especially inputs is that it should be a 2D array where the number of rows is the number of samples, the number of columns is the number of features. So even if you have one column, we want to make sure that it's actually a 2D array with one column, and that's what this is exactly here for this dot reshape. And then we can plot this data using a scatter plots. So you can see that here we have our training data and we have our testing data, and this is indeed a quadratic form. So the part that is very important is about using, Keras to define a neural network. So you can see here the architecture of a very simple neural network. So you have this input layer, very similar to what we did with linear and logistic regression. You're going to have some weights to connect this neuron or this input to this hidden layer that we have here, to these neurons in this hidden layer. And in this case, we are choosing 5 neurons, but this is usually one of the most important things that we have to decide how many neurons we want in a hidden layer. And in this case, we're going to find, a weighted sum or linear combination of the input. But what is really different from the perspective of neural networks is that you can also apply a nonlinear function, which we call this usually an activation function, because you can think of this as, neurons that they activate, that they pass this information now to the next layer. And in this case, because we only have one hidden layer, the next layer is just the output layer, what we are trying to predict.
And as we said, the basics of training neural networks is what we already know. So we have to have a loss function, where the loss function measures the disagreement between true and predicted outputs. And then we need to have a way of optimizing this loss function. And in this case means that we have to minimize it and find weights, or in this case, connections that will lead to the minimum value of the loss function. Okay, so without further ado, let's start defining this model. So we're gonna use, as I said, TensorFlow. It's common to import TensorFlow as TF, and then from TensorFlow, we import Keras. And then inside Keras, we have these modules where we have like models, like different ways of defining models. In this case, because we have like a sequential model, these layers are all placed next to each other. We import sequential, and also we use dense layers. And dense layers means that each neuron is connected to all neurons in the previous layer. This is the most common form of layers in neural networks, where all these neurons are connected without any specific structure that is going to be used in some other neural networks. And therefore, the way that, again, we think about this is in terms of object-oriented programming. So we're going to start this sequential model, which is actually a class, and we have to instantiate it, right? So it's a class, we instantiate it. So now we have this object, which is called model, which is basically nothing in it because you have not done anything yet. But we have to start to add layers. So in order to add layers, you just call model.add. So this means that you want to add a layer. And as we said, the layer that we want to use is a dense layer. And you can obviously look at the documentation page like scikit-learn or other machine learning and data science libraries. That's the best thing to do. You can see full instruction about what input parameters you can provide. But the most important one is the units, which is the number of neurons that we had in that hidden layer that I just showed you. And then the activation function, which is the nonlinear function that we have. And of course, you have more options here if you want to initialize these networks yourself and etc. So there are a few other advanced options, but as you can see here, the most important thing is this unit, which should be a positive integer, which is the number of neurons that we have in that layer, and then the activation function. These two ones are definitely important, and you should look into them. Okay, so now let's going back to the notebook that we have. So in this case, we want to add the 5 neurons that we have here. Something important to keep in mind is that for the first input layer, usually you do not need to explicitly add a layer. Once you add this hidden layer, you can mention that the dimension of the input is 1. So this is telling Keras that I want to have these 5 neurons. And in the previous layer, I only have 1. If you have, like, for example, like 2, 3, then you have to choose the right number here. And then the activation function. We're going to talk about what ELU means in a little bit, but right now we know that we are using some nonlinear function. And after this, we know that we have only one more layer, which is the output layer, and has only one element in it. And therefore, we use model.add dense 1. So in this case, you don't need anymore to use input dim because Keras already knows that there are 5 neurons in the previous layer. So that information is not needed anymore. So we're going to run this cell too. So one of the nice things about Keras is that it provides something known as model summary, which gives you information about the model architecture. And this means that the number of layers in your model, their shapes, the total number of parameters or weights that you have to learn, etc. So you can see that here, if I run this model.summary, you get a lot of information. So this is telling us, and I have copied that neural network that we want to implement here to show you the similarities or how you can interpret this. So you can see that it's telling us that we have 5-dimensional representation of the input data, and that makes sense because we have 5 neurons here. As I said, we don't usually do this explicitly for the first layer. So this is for the first hidden layer.
And then after that, we have a layer. So that corresponds to this one, which has only one element. And this also counts the number of elements that we have. So the reason, if you're wondering why here we have 10, whereas we are showing here only 5 weights or connections, is that because very similar to linear and logistic regression, we also have the intercept or the bias terms. So all of these neurons that you can see in this hidden layer, they also have a constant that are coming to them. It is very common not to plot those things to avoid any kind of like confusion here, because it can get too complicated. But that's why here we really have like 10 parameters, whereas you see 5. So you can, in this case, multiply that by 2. And in the other case that we have 5 weights here, and there's one extra constant coming to this. I can visualize that here. So that's like the other like bus term coming. So it would be 1, 2, 3, 4, 5, 6, which matches the 6 that we have here. And if you're wondering what this none is here, so remember that, anytime we use scikit-learn or Keras or TensorFlow, we want to have 2D arrays where the first dimension corresponds to the number of samples, right? That's the number of rows. And in this case, because we have not provided any information about the number of samples, Keras decides to use none, meaning that there is no value right now, but it's going to be this information will be given at some point. And this is completely, okay to use. You do not have to be worried about that. So as long as these second dimensions are as expected, that's the only thing we really care about here. So once you define your model, remember that for the model fitting or training, we need 2 things. We need to know the loss function, and we need to know how we want to minimize the loss function. The loss function that we use here is mean squared error, and this is the loss function that we use for linear regression. And for the optimization algorithm, we use something called ADAM, which stands for adaptive moment estimation. There are a bunch of optimization techniques or algorithms that you can use. This is kind of like beyond the scope of this course, but in this case, we use ADAM. You can also use like SGD or RMS prop. So if you go to the documentation of Keras, you can see a bunch of different optimization algorithms, but for now we use this ADAM. And once you compile your model, let's run this cell before I forget. Now this is the part that very similar to scikit-learn. You have a dot fit, which you provide your training data, X train and Y train. The only, I would say, main difference here is that also you have to provide the epochs, which means that the number of times that you want to pass through your data. So this technique, like ADAM, these are all based on an iterative optimization technique, which goes through the data multiple times. And in this case, this means that we want to go through the entire data 500 times. So usually if you increase this, you should get better results. Although there are some complications if you choose the number of epochs to be too large. But for now, just remember that this is something that you can adjust as you need. And here's the nice thing. So once you run this, you see a lot of useful information. You can see that this loss value, right? So that's the value of your loss function that you're trying to minimize. It is indeed actually decreasing, right? So you can see that it started from 2072 and it is indeed decreasing, right? Now it's going under 1,728. And, the number of epochs you can see here, like this is like iteration 111 out of 500 that we provided. So you can see that the error or the value of the loss function, which measured the disagreement between true and predicted values, is indeed getting closer and closer to 0, which is very much desirable. So let's see where we end up at the end if this is already done, which it is. So you can see that we get to 85. So once you run this, yourself, you may get a different result because, there are several other parameters or I would say factors that influence this decay of the values of the loss function. But overall, you should see the same trend that you start from some value and it goes down. But very similar to scikit-learn, we also have a .predict method, which now we can predict the outputs for these testing data points, the input testing data points. And then we can have two scatter plots to visualize the testing data, both inputs and the true outputs, and then the inputs and the predicted outputs, the ypred that we just found here. And as you can see here, using this figure that we generated, it seems that we are doing very well, right? So we had that original testing data points, the red circles, and then this green one is what we predict, and you can see that we can really very nicely capture the connection or the relationship between inputs and outputs here. Now you may ask, well, how neural networks work, or how do we train them? I mean, obviously we understand the main steps, which is defining the model, then compiling it, and then using model.fit. And once you do model.fit, you can use model.predict. But how does this work? So one of the most important things that we saw before when you want to solve these types of optimization problems is that we have to find the gradients, which these gradients extend the notion of derivatives to vector argument functions, right? So we had the example in linear regression where we had theta 0 and theta 1, and then we wanted to find the partial derivatives with respect to them and put them in a vector that we call gradient. So that's the exact same concept here, except that you probably have a lot of parameters that you have to find these partial derivatives. But the very nice thing is that these libraries such as TensorFlow or PyTorch, they come with something known as automatic differentiation or AutoDiff. And what this does is that they allow for the efficient computation of gradients, and you do not have to solve this problem by hand or really worry about it. So that's something that is implemented in the background. And the way that this is done, at least in TensorFlow, is using something called gradient tape, which is a mechanism that watches the operations that executed inside its context. So in order to understand this, let's look at a very simple calculus example, right? So let's say you have two variables, x and y. You multiply x by 2, and that gives you u, another variable, right? So u is 2 times x. And then you have another variable v, which is x plus y. And then these two, u and v, combine together by multiplying u by 3 and v by 5, and give you this gives you this function f. So now if somebody asks you what's the partial derivative of f with respect to x, that's a basic chain rule. Then you need to find partial derivative of f with respect to u with respect to x, and there's a second path, f with respect to v and v with respect to x. And these individual partial derivatives are very simple, right? Because we know that f is 3 times u. So then the partial derivative of f with respect to u is just this value that you have here. And you can do the math. We can show that in this case, the partial derivative is 11. And the same thing with partial derivative of f with respect to y, you can see that it's 5 times 1. So it's once you learn the logic, it's very simple, right? You need to find these paths and multiply these weights that you have. And that's sort of what gives you the partial derivative. And now you can put this together, and that will be the gradient of f with respect to these x and y. So let's implement the exact same thing using TensorFlow's gradient tape and see how that works. So again, we import TensorFlow as TF. We define the function f, which is 3 times u, 5 plus 5 times v. And in this case, you have to define these constants in TensorFlow using tf.constant. So in this case, x, let's say, is 2, y is 3, right? And then we use this tf.gradient tape. So you use a with statement, tf.gradient tape as tape. And in this case, you have to tell TensorFlow to watch for X and Y because you want to perform some operations on them. And this means that, well, see what operations are performed on them. So then you can find these partial derivatives, right? Because otherwise, if TensorFlow doesn't keep track of these transformations or these operations to get to this function f, it cannot go backwards. So we need to make sure that TensorFlow is watching for, what's happening to x and y. And then we're saying that, well, u is 2 times x, right? And v is x plus y. And that's exactly what we do. And then f is applied to u and v, and that's what the result is. So that's our gradient tape. And so once you do this, now you can say tape dot gradient. So that's how you find the gradient. You say that you want to find the gradient or partial derivative of result, the result of that here that we have this f with respect to x and with respect to y. And if you run this cell, you can see the result, right? This looks like magic. You find this 11 and 5, the two results that we had here. So you can see that TensorFlow is very smart, knows calculus 1 and can find, partial derivatives using chain rule. It provides a lot of functionality, especially when you want to find gradients in order to solve the empirical risk minimization problem for model training. So now that we understand how this works, so we want to take this to the next step. Let's, define a simple linear regression model. This is we have done multiple times before. One time when we had object-oriented programming practice, then we used the scikit-learn's linear model. But you can actually use TensorFlow to solve a linear regression model. And the reason is that using this hidden layer actually here is not really necessary, right? So you can have a model that directly connects inputs to outputs and still use TensorFlow. So these libraries are very flexible and versatile. You don't have to necessarily use hidden layers. So let's see how this works, right? And in here, we can really explain the concept of epoch. So that's like one of the main reasons that we are using this. So in this case, again, we import TensorFlow as TF, and we assume that this is our X train and Y train, right? And the result here is kind of obvious that if the inputs are 1, 2, 3, 4, and the outputs are 2, 4, 6, 8, then the weight that we have in linear regression is 2, meaning that if you multiply the input by 2, you get the output, and there is no bias or y-intercept. But we want to actually see this in practice. So in order to do this, because this w, which is the slope here, is a variable and needs to be optimized, we use tf.variable, and we're going to set that to be 0, right? So that's just an initial guess that we think that, well, maybe the answer is 0, but we are going to actually, now use an iterative process to make this actually a better value. And then you need to define how this w translates to the output. So you need to define a function called linear regression, which simply multiplies w and x, and then a mean squared error function, which measures this sum of the square of the differences between the predicted and true values, and then we find the mean, right? So here you can see I use some of these like TensorFlow functions because everything will be performed in the TensorFlow ecosystem, so it is better to use TensorFlow functions. So that's why you can see I use like tf.square. But based on what we know, this is obvious that this is means that we will raise these to the power of 2, right? Very similar to the way that, we can use like a square functions in other libraries. And tf.reduce mean means that we want to find the mean or average. That's how we do the, we define the empirical risk minimization problem. So now that we have these components, now we can actually write a training loop, because remember, these solvers that we have with neural networks, that are iterative solvers. So remember, in each epoch, what we do, we make predictions. We calculate the loss function, And then we find the gradient of loss function with respect to the parameters, which here is just W. And then we have to update W in a way that it reduces the value of the loss function. And in order to do that, we use tf.gradient tape to be able to find the gradient. And once you find the gradient, the way that you can update this model parameter here, W, you just need to subtract what is known as the learning rate or step size multiplied by the gradient, right? So this means that you already have a W and you have to subtract W by learning rate times gradient and update W. And in fact, in TensorFlow, already there is a method or function to do this, which is called assign sub. So this means that you're going to find this and you do W minus this value and you assign that value to W. So that's how you adjust W to give you a better sort of like value of the loss function. And here better means that we want to reduce the value of the loss function. Okay, so now that we want to write this training loop, in this case, I'm using learning rate of 0.01. It is common to use learning rates, very small values such as 0.01, 0.001. Usually you don't want to choose like learning rates that are greater than 1 because, in each step we want to move slightly. We don't want to have huge jumps, right? Depends on the problem, but in most cases, learning rate should be in the order of 10 to the negative 2, 10 to the negative 3. And in this case, because this is a very simple problem, I'm going to just use 50 epochs. So now you write a for loop where for epoch in range of epochs, so this means that now for 50 times, what you want to do, you're going to use this with a statement to record the forward pass, meaning that if you have W, I'm going to multiply that by the input feature to give the predicted value. That's the assumption behind linear regression, because we do not have a hidden layer here. And then we measure the difference between the true and predicted value, and that's what our loss is. And so once you get out of this with a statement, you say that, well, tape.gradient, I want to find the gradient of loss with respect to W, and I call that gradient. And then you're going to update this W or weight or W parameter here, or the coefficient, if you want to use the terminology for linear regression, and use this learning rate times gradient. And then we use an if statement that if the remainder of division of the epoch by 10 is 0, then print the epoch number, the value of loss, and the value of this weight W, right? So in this case, we know that the value of W at the end should be 2 because that's how we generated the data, right? So in this case, this W, if it's 2, then it's perfect, right? It matches the data. But we are going to start, actually, if you look at here, from 0. So the question is, if we start W to be 0 and do these updates, can we get close to 2, which is the optimal solution? So when we run this, okay, so we forgot to run the previous cell. That's why it's important to run all these cells. And if I come back here, this one is pretty fast because it's a very small problem. So you can see that at epoch 0, when we just started, loss value was 30 because this was just, again, like a really bad choice at the beginning. But then as we go to future steps or epochs, you can see that the value of loss function gets very close to 0. This is like 10 to the negative 5. And then the weight is almost 2. It's 1.997, right? So if we really round this is, exactly 2. And therefore, this shows that, yes, this, approach, is able to find the true answer. So let's see what happens if we use a very, very small learning rate, right? So we can repeat the exact same process. Let me run the previous cell too. So in this case, I'm using a very small learning rate. And you can see that in this case, we are still, the weight is very close to 0 where we started, right? Because it takes a lot of time to get away from 0 if the step size or learning rate is small. But what if, let's again run this cell to use learning rate to be large, like 100 or something like that. So you can see that in this case, even we get like NaN, which means that not a number, right? And the problem is that even in epoch 10, the weight is 1 times almost 10 to the power of 35. It's extremely large number, right? Like we get to a point that we cannot even store these numbers. So therefore, you want to choose a learning rate which is reasonable. So in this case, I use 0.01. I think that's a really good choice here. And you can see that once we run this, we get the result that we expected, right? So the weight is close to 2 and the loss function is close to 0. That's perfect. The last thing that we want to talk about here is about the activation functions, the nonlinear functions that I said that they're going to be applied in each layer. And so there are multiple options, but the most popular ones are rectified linear unit, or ReLU. And it's known for its simplicity because it has this very nice formula. It's max of 0 and x, which means that if x is negative, we always get 0. If x is positive, then we get x. So it's basically y equals x line where you're going to, for negative values of x, you're going to set everything to 0. We have a cell here that I'm going to actually plot all these functions. We can, do this mathematically to plot all these functions, but this is a programming course, so we're going to use NumPy and all other tools that we have, such as Matplotlib, to plot these things and visualize them without going through mathematical details. So the problem, as we said, is that with ReLU, for all the negative values of x, we get 0, and that's not ideal because you can have a dying ReLU problem, which means that in many cases, your networks can produce a lot of zeros. And so ELU, or exponential linear unit, tries to fix this problem by changing the equation for the negative values of x, which is this alpha e to the x minus 1. And alpha is what is known as a hyperparameter. It means that very similar to epochs, you have to set the value of this beforehand. It is common to use alpha equals 1 or some other values, and we're going to see how that looks like. And then we have another activation function, which is soft plus. And soft plus has this formula, log of 1 plus e to the x. You can show that for large values of x, this is technically log of e to the x, and log and exponential are inverse functions. So you get very similar to the y equals x function. But obviously, this is very much like a smooth approximation. To show you what this means, let's plot these 3 functions, right? In Python, this is easy. You set some values for x. You define these functions, like ReLU is np.maximum of 0 and x. For ELU, we use np.where, where if x is greater than or equal to 0 is x, otherwise it's alpha. And I choose alpha equals 1 here because that's usually the default value in TensorFlow. And then soft plus, which is log of 1 to the e to the x. And then we use subplots. That's why you can see that why subplots are very important in Matplotlib, because sometimes you want to put things next to each other. And let me also make sure that the value of alpha is 1. And if we plot this, so you can see that the one on the left, that's ReLU. So we have y equals x for x greater than 0, and everything less than 0 is always 0. But as we said, this is not ideal because we get a lot of zeros when we have negative inputs. And then for ELU, or exponential linear unit, we have exactly the same structure for x greater than 0. But for x less than 0, you get this a small amount of negative values that they can pass through. And for soft plus, you can see that we have a smooth approximation of these ReLU. So this dotted function here is the ReLU, just show you the connection with that. And you can see that when x is large enough, for example, here more than like 2.5, it's exactly, matches like y equals x. It converges to that. But then for this area, for example, between like negative 2.5 to 2.5 is much smoother. So you don't have this kind of like edge here. Just to wrap up this lecture, so remember that in Keras, the most common type of layer is a dense layer, which means that all the neurons are connected. That's what you usually want to do, especially if you do not work with like image or time series type data sets. And in order to use that, you need to import it from Keras the layers from this module where you have all sorts of layers. So you can go here and see actually different layers that are available. And then inside this, the most important argument that you have to provide is the number of units or the number of neurons. You also can provide the activation function. And if you do not provide the activation function, then it is assumed to be a linear, which means that it's not doing anything for the input. And then we have different types of activation functions, as we said, ReLU, ELU. We also have the sigmoid activation function, and that's something we saw in the logistic regression where we have to use the sigmoid function. So we already have that implemented. So if you're using a binary classification problem, for the last layer, you do want to add this sigmoid activation function to make sure that you get probabilities. And in this case, we're going to, use Keras and neural networks for two of the data sets that we already have seen. One is California housing data set. And you're going to see that, you're going to use the Keras sequential API. And very much like before, you're going to do train test split, model training, model prediction, and then the Wisconsin data set. So in this case, you again want to kind of like practice working with different architectures. And here we have, all the sort of like instructions that you can define a function to create different models with the number of hidden layers, number of hidden units. And then you can write the for loop where for each combination you perform model training. And you can see that how everything you learn in this course can really be helpful to implement neural networks and be able to perform model selection. Thanks for watching.